Yeah,
Let's
I'll
try.
just there. That's easier. Okay. All right, so we have V is equal to frequency times wavelength. This holds true for any of these three. I mean, basically, this is a generic equation that is always true. So what we've done, however, is normalize it on seconds. And we've normalized it on frequency of hertz and wavelength of meters. So an easy way to remember this equation is V, F, and lambda. You can put them in a circle. For some people, this really helps. And if you basically whichever one you don't know, you put your finger over. So let's say I don't know the velocity. I have a frequency and a wavelength. What's left is that I multiply those. So that's how I would get V equals F. Oops. Times lambda. Let's say instead that I didn't know my frequency. Well, I'm now left with this divisor bar, and I get frequency is equal to V divided by lambda. So if you can't remember, this is a really easy way to do it. And we're going to be doing these circles 3 different times during this class. So once again, we're going to write V equals F times lambda. Okay, so let's say that we were dealing with the speed of sound, which is about 330 meters per second. And we heard a baseball get hit, and let's say that it was a frequency of 330 hertz. All right. So what would be the wavelength in the air of that? So then we have 330 divided by 330 equals 1. And what are our units? Because we have a length.
Meters.
Meters. So we have a wavelength of 1 meter. So as it traveled through the air, that sound of the baseball being hit, each time it went through the 0 point on the same path, 1 full cycle, it would cover a distance of 1 meter. It just happens to be how that works. And that actually has profound impacts as well for, give me some ideas of what that has profound impacts for. Sound and frequency and wavelengths. Any musicians? Anybody? Anyone play any guitar? Yeah, okay. Well, here's a guitar string. If you shorten up the guitar string, what will it do?
Increases the frequency.
Increases the frequency. Yeah. Anyone play any other musical instruments like a flute?
I'm in school for musical theory,
Okay.
so I know a lot on musical theory.
Yep. So what do you know about an open pipe? If you blow into the bottom of the open pipe and you make it a longer pipe, what happens to the note?
It bounces more often off of itself.
Right. But if the pipe becomes longer, think of a pipe organ.
It gets deeper.
It gets lower because the wavelength is longer that it can support. So now we have something called a resonant frequency, which is where it wants to, the frequency at which it wants to oscillate based on how big it is. Okay, well, this is actually really important too. But we're going to go back to our V is equal to F lambda and get used to writing that and get used to seeing that, because that actually is the basis for solving, I'd say half of the problems regarding antennas as well. So how fast do radio waves travel?
Speed of light.
Speed of light. What is the speed of light?
Fast.
Fast, yes. 300 million meters per second, more or less. We call that the letter C. C is equal
Does
to
that
approx-
reduce?
Go ahead.
Sorry, I was just curious. Does that reduce in the atmosphere like light waves do,
Not
or
appreciably.
the speed of light?
Not appreciably.
Okay.
However, depending on what it's traveling through, yes. And then there's something called an index of refraction. And the index of refraction is a combination of your dielectric constant and your magnetic susceptibility that will actually create something called nu. That changes how fast something travels through a medium. So an electromagnetics travel through a medium. So for instance, if you've ever seen, for instance, a glass of water, most people have, and you put a spoon into the water, the spoon will look like this. It'll look like it bends. Anyone ever seen that?
Sure.
Okay, why does that happen?
Refraction.
Yep. And it's in particular the index of refraction of the material. And what that translates to is a change in the speed of light as something travels through. So it appears to be moving slower, which appears to bend the material. And that's why that happens. So yes, radio waves do travel at different speeds through different media. And that will actually be important as well, because let's say that we have air or a vacuum of space. It doesn't really matter in this case because they're almost the same for radio waves. 3 times 10 to the 8th meters per second. And then we get to another material, which is, let's say, polyethylene, which is a type of plastic. And the speed of radio waves in there is about 2.1 meters or times 10 to the 8th meters per second. So what happens is you basically change your velocity from this to this, and your waves will look like this. And then they'll shorten up a little bit in the material.
And by losing that speed, do you also lose, you lose power, right?
Nope.
So the distance traveled can be the same?
The distance traveled will actually shorten up in that material. If you were to, let's say, go from air to PE back to air, what would happen is that let's say that instead of polyethylene, we put in here a material with an index of refraction of 10, something really high. What would happen is your wave would look like this. And as soon as it came back to this, you'd be back to where you started. But in that material, the waves would compress. But they'd still have the same energy. They just wouldn't be traveling. They just wouldn't be traveling as fast, which means that it looked like they would compress. Okay, so continuing on. So let's now look at something called the electromagnetic spectrum, shall we? Okay, so I would like everyone to notice that there are 2 parts to the word electromagnetic. And what are those parts?
Electro and magnetic.
Electro and magnetic. So basically, as an electromagnetic wave travels through space, it has 2 parts. They're the electric part and the magnetic part, and you can't have one without the other. Essentially, that electromagnetic wave is a disturbance of energy in an electric form and a magnetic form, and it oscillates back and forth as it travels. So notice that we now also have this relationship here between frequency and wavelength, as shown on this little graph here. Okay, so what do you notice about all the way at the right-hand side? What letter do we have in the middle there?
X.
Anyone ever heard of an X-ray?
You bet.
Anyone ever had an X-ray?
Sure,
Probably almost everybody in this room has had an X-ray at some point.
the dentist loves them.
They do.
Yeah.
And for those of us who have broken bones. All right, so notice we now have the just to the left of the letter X, what do we have?
Ultraviolet.
UV, ultraviolet, okay. Okay, how about just to the left of that?
Visual spectrum.
Visual spectrum, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And notice on this big chart, we usually think if everyone takes the time to look at their screen or look at the window or look at something around them, how many different colors do you see? I'm just curious, how many different colors do you see?
A boatload.
How many different shades of blue can you see?
Too many to count.
Yeah, too many to count. How about, and that is true for our entire visual spectrum. So now take a look at that graph and realize that that visual spectrum, the visible spectrum, is a tiny, tiny sliver of that big electromagnetic spectrum. Can we see ultraviolet? No.
Just having all the colors.
There you go. Lots of colors.
Because I have a dozen books.
All right. How about to the left of the visible spectrum? We have
Just
IR.
Just going to point out that that's a logs, that it's not a linear scale.
Correct. Correct. And we're going to get to that too. So to the left of the visible spectrum, we have IR. And what is IR?
Infrared.
Infrared. It means longer than red. Or lower than red. Yeah. It's lower frequency than red, longer wavelength. Okay. How about when we get all the way to that thing that says 300 gigahertz, we switch from infrared, those waves are getting lower and lower in frequency. And at some point we switch from infrared to
Microwave.
microwaves. Microwaves are a form of what?
Radio waves.
Radio waves. So I would also, as Tom pointed out, notice that the frequency all the way on the left-hand side starts at 30 kilohertz, which is 30,000 hertz. The next step over is 300. The next step over would be 3 million. These are actually going up by a factor of 1,000 every time. Sorry, these are going up by a factor of 10 every time. So essentially, as we go to the right, our frequency goes up by a factor of 10. So if we were to actually draw it out, if we look at that first gap where the letter R is, right here, the letter R, what is the gap in frequency between 30 and 300?
270
270. And what are the units there?
hertz.
They're kilohertz, which is thousands, right? So it's 270,000 hertz. Okay, so now let's go over to the letter O, where it says radio.
Mhm.
From 300 megahertz up to 3 gigahertz, which is 3,000 megahertz. What's 3,000 take away 300?
270.
2,700.
Yeah.
2,700. And what are the units? Million. So that space in there is 2,700 million or 2.7 billion hertz. And all the way at the left-hand side, we were at 270,000. So we went 1, 2, 3, 4. We added essentially 4 zeros to the size of the space that is shown in that little gap. So if you have what looks like the same size space on this graph, but in reality, it's actually 10,000 times more space inside it, where do you think you could put more stuff?
Yeah, the higher frequency area.
Right.
Yeah.
Yeah. So the higher the frequencies you go, the more stuff you can put in it. So what is that stuff? What would that stuff be? What do you think?
Frequencies.
Anti-entropy.
Well, I mean, what actually is the stuff? If you think about, if you look outside, what is it that you are seeing? You're really getting information, right?
Anti-entropy.
Yeah. But you look outside and you look at the wall and you get information about things that are happening, right? You can see colors. You can see that a light is flickering on and off. Every time you get information and put it and use it to encode something so that somebody else could then see it, that takes up space in the frequency spectrum. The more things that you try to convey, the more room it takes up. So if I were to say, if I had a choice between going to the very left end of this chart and the right end of this chart, where could I convey more and more and more information? I need as much space as I can.
To the right.
All the way to the right, where you have so much room because you have so many unique frequencies. And that is why the cell phone companies are going to ever higher and higher frequencies in order to work, because they have that much more room to work. A signal that allows somebody to talk takes up the same amount of space, no matter where you put it. There's a lot more space up there, which is why those frequencies are so valuable to a lot of the to cellular phone companies and to other communications companies. That's why they're really not interested in doing communications down at 3 megahertz. They'd much rather do it at 3 gigahertz or 30 gigahertz, because there's a lot more space up there for them to convey information. And if you want to have the fastest 5G network that allows you, that allows you 100 megabit connectivity from anywhere you are, you have to put it at really high frequencies because there's a lot more room up there. Okay, so that being said, let us now discuss electromagnetic fields and why they are so useful to us.
My
So,
mom actually has a 5G phone.
there you go. Okay, so we now have that particle that's moving this way. We're going to draw and we're going to draw this. Okay, so we have this axis and then we have this axis. These are actually perpendicular to each other. So the way that this is drawn, our particle is moving to the right. Our electric field is going up and down, and our magnetic field is going toward us, in and out of the page. So this is actually something known as, I'm going to put a letter S here. S indicates the pointing vector. It's actually spelled P-O-Y-N-T-I-N-G for the person who came up with it. But basically, that's the direction of flow of our energy. As the energy moves to the right, electric and magnetic fields are always perpendicular to each other. So I'm going to ask everybody to hold up your right hand. If you do your left hand, it's not going to work right. Okay, so stick out your thumb. Now stick out your your index finger. Now here's the tricky one. Notice you now have a shaped letter L. Now stick out your middle finger so that it's perpendicular to both of the others. This is known as the right hand rule. So this is your electric field, magnetic field, and direction of motion. Your index finger is the direction of motion. And actually, as this travels back and forth, your electric field goes back and forth, your magnetic field goes back and forth this way, and the energy goes into the screen, as everybody just saw. So they're all perpendicular to each other. And when the electric field goes up, the magnetic field goes down. When the magnetic field goes up in strength, the electric field goes down. So basically, in an electromagnetic wave, you have energy that is oscillating back and forth. It's being shared back and forth and changing from electric to magnetic and vice versa over and over and over as the wave travels through space. Okay, so in the book, we are on page 24 because we're starting sort of in the middle. So if everybody wants to flip to page 24, the answer, does anyone have any questions about electromagnetics?
Sure.
Go for it.
Actually, it does make sense because there's 24 people.
It does, but 3 of them are me. So,
2 of them are me.
and 2 are you. Yeah.
When a wave compresses, or when light compresses, when it's going through a different material with a different index of reflection, can you disambiguate which component is responsible for the compression, magnetic or electrical?
Both.
Always,
No,
it can't always be the same. I mean, they've got to be different sometime, right?
they do have to be different sometimes. And it actually comes down to the magnetic susceptibility and the dielectric constant. And they're both going to be different, potentially. So it depends on the material itself. Both of them can have an effect, and both of them will alter the magnitude of the magnitude of the excursion as it passes through.
Right. I mean, well, the end result is the same, but you could get to it through 2 different mechanisms.
Yes, but basically you still have conservation of energy.
Yeah.
So
Beyond the,
Yeah.
beyond
ahead.
the intrinsic interest of how fascinating electromagnetic fields are traveling orthogonally to each other, why does a technician ham with a technician license care?
Why do we care? Why do we care?
Not you.
Yeah.
Not you.
Yes. And the reason being that it is important to understand why something called polarization exists.
Mhm.
And this is a fundamental toward understanding why something called polarization of a wave exists. Because that will determine the function of your antenna and how you build it.
So it boils down to being able to construct something.
And being able to actually have it work is the more important part.
So is that also with regards to if I go out and buy an antenna, I need to understand the electromagnetic fields and how they operate so that I can actually plug it in and get it to work?
Yep.
Okay.
Okay, so on page 24, we will see okay, first question. What type of wave carries radio signals between transmitting and receiving antennas? Electromagnetic wave. Okay, a radio wave is made up of what kind of energy? Electromagnetic energy. And the 2 components of a radio wave are
Electric and magnetic.
electric and magnetic. Okay, so
That's pretty cool.
fundamentally, what is the difference between blue light and a radio wave?
Frequency,
Frequency and
speed,
nope,
velocity. Oh,
velocity never changes because radio
That's right.
waves travel at what speed?
Speed of light.
Speed of light, and light waves travel at
Speed of light.
speed of light. So what that means is that our equation actually just simplified, did it not? Because it always travels at the same speed. So if we go back to V equals F times lambda, well, we know that V is actually C, which is the speed of light. We can replace that with 300 million equals F times lambda. And this is in hertz. And this is in meters. Well, I don't really want to have to maintain all those zeros. Raise your hand if you want to maintain all those zeros, because they don't mean a whole lot to me. It's just a lot of extra zeros to lose. So what we're going to do is take 6 of them. That means we have 300 times 10 to the 6th. 10 to the 6th is a million, represented by the big letter M, which means mega. So we're going to then take this and say 300 M equals frequency times lambda. So now what we're going to do is say, okay, well, we're still going to get a number that's big here. Well, we're used to working in this realm of something called megahertz. So we're going to make this go away. And our frequency is now going to be in megahertz. So our new circle is 300 and F in megahertz and lambda in meters. This is our new modus operandi for that equation. So this actually has really profound implications because we operate mostly in megahertz. And this thing is now calculating our relationship between frequency and wavelength. And notice we never have to cross out the 300 because it is a constant. It's always the same in free space or in the atmosphere. So that means that whichever one of these we don't know, we cross it out. Oops. Let's say we don't know our frequency. We're just given a wavelength. So our frequency is 300 divided by our wavelength. So here we go. Let's say that somebody gives us a wavelength that we measure of 6 meters. Okay, what is our frequency?
50.
That'd be 50. And what are the units? That would be megahertz. Okay. And actually, then if we go back to our frequency charts, we will see that the 6 meter band, as it's called, which is one of the bands that we have access to, actually goes from 50 to 54 megahertz. We colloquially call it the 6 meter band. The frequency range covers from 50 to 54 megahertz, and you have access to that band. So let us instead change that to 2 meters. 2 meters is our most popular band. It's useful for lots of different things. What would our wavelength, what would our frequency be?
150 megahertz.
Nominally 150 megahertz. So colloquially, we call this the 2 meter band. The band in the United States actually goes from 144 to 148 megahertz. That's our 2 meter band. And that's why it's done, because we could say, I'll meet you on 146. I'll meet you on the 146 megahertz band. I'll meet you on 2 meters. That's just easier to say. And historically, this wavelengths have been used for a long, long time to describe a frequency, to describe a band. So let's go to the 20 meter band. What is the nominal frequency, the nominal wavelength for that? 300 divided by 20 gives you
60
I hope
or
it's
6. No,
I hope it's 15.
15. Sorry.
Right. So that would be 15 megahertz. And in fact, the 20 meter band covers from 14.0 to 14.35. So it's not exact. It's the approximate wavelength in meters. So what this really means now is we're going to go backwards. We're going to go
Scott?
the other way. Yes.
Is there any sort of rule like round up, round down, or anything like that
For what?
for equating
Bands.
bandwidth to megahertz? Do you ever like, well, yeah, how does it round?
Okay. There is no official
No
way of
rhyme or
doing it.
reason.
No.
Okay.
And in fact, what it comes down to is this, which is something that I've included, something that I included in all of everyone's packets, which was the band plan. The band plan shows you, notice we have the 20-meter band, and it covers how the 20-meter band is laid out along with the band edges. So 20 meters is not exactly 20 meters. It's from 14 to 14.35. Up here, we go
Which
to the
is never
2-meter band.
15.
It's never 15. Sometimes it does work, but like, but again, that's really done for colloquial reasons. It's a lot easier to say the 20-meter band, and that actually came from the era of shortwave to a certain degree. You know, there's a 13-meter band, a 16-meter band, a 25-meter band. It's an approximate wavelength. So what I'm going to show you now is how this is even more useful, because let's say that we have our 300 and F and lambda again. Here's our circle. Okay, so we're going to say, I have a frequency. I want to build an antenna system that operates at 14.200. All right, does anyone have a calculator handy?
Yeah.
Okay, so we don't know our wavelength right here. So we have 300 divided by 14.200. Somebody please do that for me. I told you this class is interactive.
21.1267.
Okay, all right, and that would be in meters. Okay, so what I'd like you to do now is multiply that by 0.95.
20.0704.
Okay, and because we live in the United States and not in Europe, I'd like you to multiply that by 3.3.
66.2323.
Okay, that is the length of an antenna that would be tuned to operate on this frequency.
Wow.
So you want a band that you want a free antenna that you designed to operate on this frequency. This is how long to make it. This is why they're so important, because again, what did we start with? We started with a particle traveling through space, oscillating up and down at the speed of light. This is how long, I'm sorry, this is actually how long that wave is. This is how much, how long, what distance it traces out as it travels. Okay, but now we're going to say that we instead want a half wave antenna, and we'll get into that shortly. So now I need you to divide it by half. Divide it by 2.
33.1161.
Okay, there you go. So a half wave 20-meter antenna, we would make 33 feet long, plus or minus a little bit. And you always want to start a little long so that you can trim it, because it's a lot easier to trim it than to add and solder to it.
Hey, Scott,
Yes.
I had a question. Please explain the 0.95 and the 3.3. I think I got
Okay.
lost with where that came from.
Okay, so 3.3 is because we live in the United States. This is feet per meter. So I'm converting from meters to feet. 0.95 is something that we do because physics doesn't permit reality to match theory. And this is due to capacitance, which we'll get to, and inductance. The fact that because there's no such thing as an infinitely narrow piece of wire, and the end of an antenna will always exists unless you're in space. It always exists with something around it. There will always be the end of an antenna and the beginning of something else, either the ground or a house or a car. And you have a voltage here and a different voltage here. And what do you have between those two things?
Space.
You have space. Okay. If you have a something here and a something here, and they're at voltage 1 and voltage 2, for those of you who've done physics, what is this thing called?
Capacitor?
This is called a capacitor. That's right. And inside this, because you have two different voltages, you have an electric field. which means that you at AC or alternating current, you actually get a little bit of coupling between the two things. And that factors into this 0.95. Essentially, because there is there has to be a fudge factor that allows this antenna to work in reality, which is another reason why theory and reality don't always match. Which is another reason why, for instance, there are lots of physics and engineering textbooks that will tell you exactly how long to make something antenna wise. But in reality, the Bible of making antennas, believe it or not, is the ARRL handbook, not that physics or textbook. And the reason that's true is because the ARRL handbook is based on physics, but then based on real world experience.
So does that mean you need to have, when we're looking at your band plan, right? So if somebody, well, let's ask a simpler question
Sure.
first.
Yep.
Can we operate, where, as a technician, what are the meters we can operate on?
Okay, so what I've done, I brought up the band plan again. Okay, so you see the 6 meter band, 2 meter band, 1.25, 70 centimeters, 33 centimeters. Basically, if it's 6 meters or shorter in wavelength, you have full privileges as a technician. In addition, anywhere that this, you notice this says novice technician voice,
Right.
novice technician CW. So the green hatched or the blue hatched, you have access to those frequencies as well. So up here on the 10 meter band, you have CW on 15, CW on 40, CW on 80 meters.
So that implies then that you either need to have multiple antennas or you've got a coil of wire that you can run out further and shorter.
That is actually very, very perceptive. So I wasn't planning on getting to it yet, but now this is a good segue into it. So again, this is kind of a teaser as to what we're going to do, but let us now draw this wave. All right. So this wave, what are two fundamental things about, actually three fundamental things about the wave? We have its speed at the speed of light, its wavelength in meters, and its frequency in megahertz. So the really important one here is its wavelength, because it turns out that what we're going to do is split this in half. And notice that it goes through, if we were to draw this axis, it goes through 0 right at the left end and in the middle and at the right end. How long is this section right in there in wavelengths?
Half a wavelength.
Half of a wave. So it's the wavelength divided by 2. This is the fundamental antenna that is the basis for virtually all antennas. The reason being, if I were to now draw this antenna, and I have to feed it somehow, which is why we split it. Let me ask this question. We haven't done current yet, but current is the movement of electrons through a point in a piece of wire. If we're all the way at the end, how much current can flow that way?
It only flows in one direction.
Well, no, actually, what happens when it gets to the end? How much current flows off the end of a wire? That would be 0. How much current flows off of this end?
0.
0. It's a piece of wire. So what that means is if we now take this and we draw it here like that, we have our current zeros at the end and our current maximum right in the middle. Well, we're going to get to that. But now let's instead draw a different wavelength because we are on a different frequency. And we end up with something like this. We're constrained by what thing? We still have the fact that our current has to be what at the end?
0.
0. But let's say that we have an antenna where the wavelength is really short and we have this. What do we have here in the center?
0.
0. Okay, so we're going to get to this. This is in the next section, but E, this is Ohm's law. E equals I times R, which is voltage and current and resistance. So as it turns out, if our current is 0, we do the little division here. R is equal to E divided by I. What is anything divided by 0?
Infinity.
Infinity, which means if you try to push energy into something with an infinity in resistance, good luck. So that's why when you say if you would operate on different frequencies, you need different antennas. That is true. That is to a large degree true. It's not impossible to do it. You can have an antenna that operates on multiple bands. You can have an antenna that operates on multiple frequencies, but it takes some design. There are some design challenges, which is why antennas are still, after 35 years, that thing which is the most fun for me to do.
We're probably going to get into this later, but when you say someone might say, oh, I'll meet you on the 2-meter band, how do you know what frequency within that band?
You have to pick.
Okay, so they would say, they would actually designate a frequency within that band.
Correct. You
Okay.
say, I'll meet you on, I'll meet you on 146.52, which is the simplex frequency, for
Okay.
instance. All right. Okay, you guys. Well, now that we've pretty much beat frequency and wavelength to death, let's see. What happens as your frequency goes up? What happens to your wavelength?
It's longer.
As your frequency gets higher, what happens to your wavelength? It's doing this more often.
Getting
It
shorter.
shortens.
Shorter and shorter.
It shortens.
All right. So what happens as your wavelength goes up? Your wavelength gets longer and longer. What happens to your frequency?
Gets smaller and smaller.
Right. They are inversely proportional to each other. So, okay. So now what we're going to do is I'm just going to mark off 3 things that are going to be on every exam. Guarantee that one of these will be on your exam. HF, VHF, and UHF. HF is 3 to 30 megahertz. VHF stands for very high frequency. That's 30 to 300. UHF, 300 to 3000. You have to commit these to memory. There is no way around it. You'll be using them if you're on the air all the time. Anyone have experience with an old school television
Yeah,
which had VHF and UHF channels?
yeah.
And you
Okay.
turn the knob to get them.
And you turn the knob to get them. So when you're turning the knob, what do you think you're actually doing?
Spinning a
Changing it.
transformer.
Changing the
Frequency.
Changing the frequency by switching in a different inductor or capacitor to change the frequency that it's receiving on.
You're
Because-
changing the length of your antenna.
Well, the antenna doesn't change,
Well,
unfortunately.
The
And
rabbit ears are still up on
The
top.
rabbit ears are still on top. That's right.
but
And
their
the
path,
foil.
The path could be
the
changing.
electrical path changes because of the inductor.
Well, what you're doing is you're really changing the internals. You're changing how the receiver itself is tuned. The antenna that's collecting the signals is still the same. Now, it is possible that your antenna is resonant on many, many frequencies, which is why TV antennas look like this. For those of you who remember old school TV antennas, and sometimes there was like X's in between, and essentially this is something called a log periodic. And this is a multi-band, multi-frequency antenna that has a very, very wide frequency response. This is always receiving lots of different frequencies and sending them down the cable. Your TV is essentially your eyes. It's looking for a particular frequency and a particular wavelength, and it's amplifying just that frequency. And we will be getting into that as well, because that involves filtering and how electronics can separate one frequency from another using capacitors and inductors and other frequency sensitive devices. Okay, So finally, the term RF. RF stands for radio frequency. That's basically anything that's a radio frequency. All right, everybody, 5-minute break. Think of all your questions. Everybody good? Okay, 5-minute break.
Yeah, good.
Yep. I guess not. Okay.
And while we're waiting for that 5 minutes to be over, if anybody has any questions, it's a good time to ask.
Hey, Scott, you were referring to page 24 in the book. What book were we looking at?
Did you get the zip file or not?
I just got the zip file from one.
Okay, if you open up the zip file, one of them is the one of the things is the textbook. And it is the no nonsense guide.
I had sort of a general dumb question for you.
Mhm.
Just for those of us who are totally new to this realm and don't have context.
Yep.
What does like a normal, say, conversation with a random stranger in another company, like what's the form? Do you essentially like meet on frequencies that are considered sort of like the general chat room, and then you say, now we're going to switch over to this other frequency and have an actual conversation?
Okay, so it totally depends. If you're operating on simplex, which is that both stations are using the same frequency. For instance, let's just let me put the spectrum up here. Okay, here's the band plan. All right, so let's say you're on the high frequency bands. There's no real such thing as a calling frequency. What you're talking about is basically like, let's say right here, 146.52 in the 2-meter band. So what we're going to do is zoom in on the 2-meter band. So right up here in this little pink zone between 146.4 and 146.6. Notice this says over here 146.52. That is the national calling frequency. Essentially, that is a make contact and transfer to another frequency because it's a channelized frequency. On FM, you basically do have channels that are kind of agreed upon by gentleman's agreement. For instance, up here on the 470 centimeter band, 446.0, typically, in order to free up that frequency for other people to use, because it is defined as the national calling frequency, you'll say, okay, I'll go up to 446 and call CQ, CQ. Somebody answers me. And you say, okay, let's go up to 446.2. So the Q term is QSY, which means change frequency to 446.2, which then frees up that calling frequency for somebody else. On the high frequency bands, by and large, there is no such thing as a calling frequency because it is not channelized. For instance, let's look at, let's say, the 20-meter band, and notice that general voice right here goes the blue between 14,225 and 14,350. Right? Those are your edges for the general operator. So the question then becomes, how many different frequencies are there in there for somebody to use? I want to hear the answer.
Well, there's going to be an infinite number, but
That
they
is.
don't all be useful.
Right. Well, but they are all infinite because you can actually tune your dial. It is not channelized. You can tune your dial to an infinity of different numbers. Now, at some point, you will have a situation where if the band is getting busy, what will happen is you'll have a signal here. Let's say we're on upper sideband. So it'll look like this. And then another one that's right here and another one that's right here, and they are not overlapping. However, if another one comes on and it's right here, notice it'll now be overlapping with two other signals. So because of that, you do have a limited number of channels, but there's no defined frequency at which they can be. The only definition is that, like, here's 14.350. The only rule that is a hard and fast rule is that all of your signal, this is in and this is out of the band, all of your signal must be in, which also means that you have to know what your signal physically looks like. You have to know that your signal is, let's say, 3 kilohertz wide, and this is 14.350 megahertz, and that if you put your signal right here, it will fall outside of the band and you will be operating illegally. If you move it over here, it'll fall inside the band, and now it will be legal. So you need to know what the bandwidth of your signal is, and in this case, know that you don't want to tune your radio any higher than 14.347, which is why we have to take classes, which is why ham radio is different from virtually any other service out there, because most other services can't just tune their radio willy-nilly and pick a frequency and start operating there. They have to go to a particular channel. We have the flexibility of doing lots of other things. With great flexibility comes great responsibility, and with great responsibility, like driving a car, you have to prove that you at least won't get into too much trouble. That's why we have a driver's exam. That's why you have a ham radio test. The more privileges you get, the more tests you have to take, the more complex they are. Pat, you have anything to say about that, considering you've been through all three recently?
Yeah, I think the extra exam is, I don't know, intimidating. I took it 3 times. So,
But you
know, it
passed.
just, it's one of those things that you've got to have a real personal motivation to do and why you're doing it. A lot of mine is emergency communications as well. My brother was in ham radio when it was only CW.
Yeah.
And recently got him reinitiated into it up in Canada. He is going crazy because it was only CW at the time.
I know. Yeah.
And
what's his call? You know, what's his call sign?
VE3RKY, and he's now activating parks with his ICOM 705, which I'm jealous because I want one of those too to do some expeditioning.
Yep.
And you know, I mean, he's all over the place. He's doing all kinds of events.
Yep.
They need him in parades, in all kinds of situations, emergency situations as well. So
and still doing lots of CW.
right.
I'm assuming,
And I'm interested in your CW courses, by the way.
Yeah.
It's a real hang up as far as time is concerned. And I think sometimes if you have a class like this, you make the effort. And working too many hours lately, I think, but.
Well, you know, if you stay up really late, like I've actually taught it from the East Coast. I mean, it starts at 11 o'clock.
11 o'clock at night.
PM.
Oh, wow.
Well, you know, like if I'm traveling for work, nope, I still got to do it. Fire up the computer, teach it at 11 o'clock at night from midnight, and then just go to bed.
Wow. So you were saying that at one point ham radio was only CW. When was that?
Well,
When,
I mean,
when I was a teenager.
well, I mean, there was still sideband, but sideband radios, you know, there was a significant cost differential. It was cheap to get into Morse code because a Morse code transmitter is just on, off, on, off.
Uh-huh.
And my brother had an N-Fed antenna that just went up our TV antenna or tower.
Mhm.
And, you know, that's what he did. And he had a desk full of older equipment.
Yep.
And when I reintroduced things to him and he got out there, he's on DMR, G-Star, Fusion,
Uh-huh.
everything now.
Yeah.
And I sent him some basic.
He's gone
digital
crazy.
equipment.
He's gone crazy. Yeah.
He loves it. So
Well,
it can be addictive.
yes. Oh, very much so. All right, everybody ready to go? We're going to page number 4. We're going all the way back to page 4. Electrical principles: voltage, current, resistance, alternating current, direct current, conductors, insulators. So now we're doing electrical theory now that we've covered what waves are. All right, here it is. E equals I times R. E is our electromagnetic force. This is also known as our voltage. I is our impulse, which is current. R is our resistance, which is something's ability to disallow the flow of electrons. So voltage is the amount of push, literally somebody like pushing against a wall. Current is the flow of electrons through something. Resistance is the ability of a material to block that flow. So if you think about it, let's say that you have a pipe and you have a tank of water above. We'll make it a nice blue tank. And then you have a valve down here. So the current would literally be the amount of water flowing down through here. The tank would be the push, the amount of force. The higher the water level is, the higher the push. And the current, again, would be the material flow, the water flowing down through the pipe. And this would be the resistance, essentially closing off or allowing lots of flow. Obviously, if you reduce the resistance to flow, what's going to happen to the amount of water flowing? Right.
Gregory, can I retire? No matter what your assets are. Oh, you can.
Well, I can hold on. I'm getting some feedback from somebody.
And retire at any time. Yeah. That's not the right question.
Hey, Albert, I'm getting your radio. I'm getting your radio, I think. All right. So as your water pushes down, which is your electromotive force in this case, it causes current, and it's proportional to the resistance. So the lower the resistance, the greater the water flow. If I were to take this valve out completely, I would get a flood of water through. So low resistance, high current. The amount of push would increase the current flow as well. So we're going to write our equation again with the circle. E equals I times R. In this case, there are 3 variables. One of them we're going to not know. If you don't know 2 of them, you can't really solve this so easily. But E again is in volts. I is in amps or amperes. R is in ohms. Okay, so this is the letter V. This is the letter A for amps. And ohms is the Greek letter omega for ohms. So what we're going to do is write this equation, E equals I times R. And now we're going to draw it as a circuit. A circuit comes from the word circle. And essentially, I have this device known as a battery, which is a generator of electromotive force. I have this thing, which is a resistor, which is something that blocks the flow of current. and I connect them all with wire. All right. So this is actually important to talk about. Again, what is another word for the flow of current? Used with the Greek letter I, or with the letter I. What is current?
Electrons moving.
Electrons moving, yes. And actually current is, the unit of an ampere is a coulomb per second. A coulomb is a lot of electrons. It's something like 10 to the 19th electrons, because electrons are really tiny. So an ampere of current is actually a huge flood of electrons. Of course, they have very little charge, but they do exist. And so a coulomb is a ton of electrons. So in order to simplify this,
Time.
what?
Yeah, it's just making per time. It's a number of electrons per second at
Yes,
past a
yes.
given point.
Over a given point. Okay, so an ampere is a lot of electrons going past a particular point in space, in a second. So if I were to look at this circuit, what would happen if I made my resistance go up? By this equation, if resistance got higher, what would happen to my current?
Slow down.
That's right. It would become less. So the easy way to think about this is, let's say that I did this and I took this out completely. This right here is known as a what?
A dead short.
Actually, it's the complete opposite.
Open
Oh, wait, no,
circuit.
that one's okay.
This is an open circuit. And what is the resistance of an open? In theory, infinity ohms, which basically means you'll have no current. This is basically how a switch works. I've now opened my switch and no current is flowing. Well, now I go all the way to the other side and I say, okay, well, we're going to draw this circuit and now I'm going to replace my resistor with a piece of wire. And we're going to say that this is a perfect wire with no resistance at all. So what would the resistance in my circuit be?
0.
0. What is that known as?
It's a short.
That is a short circuit. And how much current would we get?
All of it.
All of it, as much as that battery can make. So if we do E equals I times R, and my resistance is 0, well, the only way to get something times 0 and get something that's real is to make this basically go up to infinity. So essentially, we're now looking at if there's a little bit of resistance inside the battery and a little bit of resistance inside the wire, that's the only thing that's going to be limiting us. Well, that's a bad thing, right? Because let's say that the battery produces, oh, I don't know, 250 amps of current. That's a lot of current, which we'll get to in a second, why that's so important. Okay, so now we're going to do our circuit again. Very simple circuit. And we're also going to cover the mistake. Okay, so plus and minus. Here's our resistor, here's our battery, and there's our current flow around the circuit in that direction. Okay, what is the definition of current? One more time, what is current, everybody?
E equals I times R.
Yeah, but fundamentally, what is current? The flow of what?
Electrons.
Electrons. In particular, the flow of electrons past a given point, right?
In a
What
given
is-
time.
In a given time. What is the charge on an electron? Plus or minus?
Minus.
It's minus. Okay, so
Don't ask why.
don't ask why. Okay, so the question is, if I assume that we're going to tie this point to ground, which is going to be by definition 0. This is ground. It's also known as Earth. The assumption is that our Earth is at 0 volts. Okay, so this is our reference point, which is what a ground is. So given that an electron is a negative charge, and I look at this battery over here on the left side, which terminal, the plus or the minus, do you think electrons would come out of? Knowing what we know. It's the only one that makes sense. If electrons are a minus charge, do they come out of the plus or the minus?
Minus.
They come out of the minus. That's right. So we can go back to about 1850. And so here come the electrons and they go this way. Well, wait a minute. Which way does the current go?
The opposite way.
The opposite way. And this is our current, which basically means that they had a 50-50 chance and
It doesn't work.
they got
They-
it wrong. It means that they got it wrong about 170 years ago. They got it wrong because they didn't really know what an electron was at that time. All they knew was that it was the flow of this thing called an electron, but no one really knew that it was negative at that time. So they got it wrong. So what we're going to do from now on is forget that electrons are a negative charge, because every engineering student is taught this. Current flows out of the positive and into the negative, because that is the definition of current. So current always flows out of the positive terminal and into the negative terminal. Whereas in reality, electrons are now going this way. And this is something that, again, every engineering student learns, and then you're told to forget it. It's like, well, you know, okay, but I know that it happened. So now you know that it happened too. Okay, so from now on, current comes out of the positive and back into the minus. So here's our current out of the positive terminal of the battery, goes through a resistor. Now we complete our circuit. Okay, so what we're going to do is the first thing we're going to ask, what is the unit for electromotive force? Electromotive force is this E. What is the unit?
Volts.
Volts. So a car battery, for instance, is how many volts?
Well,
12
12.
volts.
Oh,
And
not
it's
in my
12 volts.
EV.
And it's 12 volts DC. This is a car battery. This is a very common voltage for a lot of ham gear because a lot of it is designed to run in cars. And that's why we have 12 volt power supplies. So for this case, we're going to assume that that's a 12 volt battery and that it's DC, which we will get to in a minute. Okay, so we're going to set a resistance of, let's say, 1 ohm. Okay, so that's our resistor. No, so the question now is, what is our current? So we're going to make our circle, E equals I times R, like this, which is the one that we don't know, everybody?
I.
I. So we're going to put an X through the letter I, and what are we left with? E
12
divided by
I,
R. So we have I equals E over R is 12 volts over 1 ohm, and a volt per ohm is known as an amp. And we have 12 amps.
Amps.
So that is our current flow coming out of the battery through that resistor. So now we're going to change this up to 2 ohms. We're going to erase our calculation. All right, what is our new calculation?
12 divided by 2.
That's right. It is now I equals 12 volts divided by 2 ohms is 6 amps. So by doubling our resistance, what did we do to our current?
Reduced it by half.
Reduced it by 50%. All right. So now we're going to change this to put it back to 1 ohm. And we're going to increase our battery to 24 volts. We're going to make it industrial because I do 24 volts at work most of the time. What's our new current?
I equals 24 divided by 1, which is 24 amps.
24 amps. Okay, excellent. Okay, so now here comes the next question. Now that we've done that, which direction does current flow through this circuit?
Positive.
Clockwise.
Yep, and flows clockwise in the direction of the letter I. Okay, this is known as direct current because it follows a specific direction. So now let us ask this question. If I were to instead change the battery, and I was really creative, and I figured out a way that I could then take this battery, and every second I could, let's erase all that. Every second I would go in there and I would do this and swap the battery from that to that. And the plus would now be down here. Which direction would the current flow out of this battery?
It would swap back and forth.
It would swap. It would be that way. Okay, then another second later, I come back in here and I switch the battery again. What would happen to my current?
Go back.
It would go back. And it would be this way now. This is known as
Alternating
current because it changes direction. The way to achieve this is that your battery switches back and forth. The number of times that it switches back and forth would be known as its frequency, the number of times per second. Typically, we replace that source with a picture that looks like that. And what is that wave known as? What kind of wave?
Sine wave.
That is a sine wave. That's right. Again, what a sine wave does is it shows the distance from the x-axis of a point on a circle as the circle spins around. So it starts at 0, it goes up to plus, then it comes back through 0, comes back to minus, and back to 0 again. If we were to plot that over time, it would look like that. So the big advantage of this is that this, in reality, is based on what shape? What is that crudely drawn shape right there?
A circle.
A circle. Can you think of anything that goes around in a circle?
The Earth.
The Earth. Any other things that go around in a circle?
The moon.
Yeah. Anything else?
Current.
Okay.
A
A
clock.
clock. Yeah. A clock. And how about a motor? How about an electric motor? How about a generator? So let's say that I take a water wheel and I run water over this water wheel. And I hook this water wheel up to a shaft, and I take this shaft and I put an electric generator on it, which will do what now? It will turn. And inside this electric generator, I now have something that looks like this with one magnet and another magnet. This is very crudely drawn, but now I have a bunch of coils of wire that are now connected to this, and these are now spinning. Well, as they do that, they're now in a changing magnetic field as they spin around, and magnetic fields, as it turns out, make current. And they also make voltages as it goes back and forth. And the end result of this thing looks like that. And what is that thing called? What is that wave called? A sine wave. And guess what? We've now taken energy from turbines or from water wheels and converted it to electrical energy that looks like a sine wave. And what's cool about a sine wave is that that now becomes the basis for our alternating current, which is why when you look, if you were to look into your wall socket using a meter, you would see that your meter says 120 volts AC. Right? Does everybody know that? You have 120 volts in your wall socket, If you were to actually look at it on an oscilloscope, you would see that it did this. And that its peak was 170 and its negative peak would be negative 170. And it would bounce up and down, back and forth between those points. The reason that
Not
it's
120.
no, the reason that it's called 120 volts is that when it's in this upper part, its voltage is higher, right? When it's down here below negative 120, it's actually further out. There's actually greater voltage outside of 120, right? But how about when it's in here? How much voltage is there? This is, it's less than 120, right? Okay, so we're now going to do our next Ohm's law thing. P equals I times E, or pi. P, I, E. Okay, so what is I again?
Current.
Current. What is E?
Voltage.
Voltage. What is P?
Power.
Power. And its units are?
Watts.
Watts. Okay, this is actually really important because watts are a unit of energy transfer. And since energy is conserved, what does that mean? It's neither created nor destroyed. It just changes form. So what this means is, because we have our I times E, and what else do we know about the relationship between I times E, or I and E? E is equal to I times R. If our resistance doesn't change and our voltage goes down, our current also goes down. If they both go down, what happens to our power?
Decreases.
It decreases actually by the square. It actually goes down a lot. So what happens to this amount of power that's being made inside right here as that voltage is really low? How much power is being made when that voltage is really low?
Maximum.
No, think about it. If our voltage is zero, what's our current?
Oh, multiplied, right? Yeah.
So basically, this sine wave makes peak power up here and down here and up here and down here. And inside, it's actually diminished. And because it's actually proportional to the square, this is actually known as RMS, which is root mean square. That 120 volts is actually an equivalent DC voltage that would generate the same amount of power as the sine wave that you're seeing. So it turns out that in order to do that, a sine wave, the peak voltage is actually 1.4 times the RMS voltage of a sine wave. So that's why if you were to look at your wall voltage, you use 120 volts, you would actually see those peaks. And they call it 120 volts. Now, here's another question. Let's say that you had something called a square wave. That has a frequency, doesn't it?
Yep.
Okay. How much power is being made up here when it's at its peak?
All of it.
Full power. How about when it's way down here?
Oh,
All of it. How about up here again? Full power. So basically what that means is that in this particular case for a square wave, your RMS power is actually equal to your peak. Your RMS voltage is equal to your peak voltage, which is why when you go by a voltmeter, sometimes you will see a voltmeter that is true RMS. Because a cheap meter is not smart enough to figure this out. So when you go buy a meter, if you care about this and you look for a true RMS meter, it will actually figure out what the waveform looks like and give you an actual value.
So what is the issue with a device that creates a square wave?
Square waves are noisy. I mean, a square wave by definition is noise.
Huh.
So, well, okay. So this is advanced but important. Ready, everybody? Here we
Sure.
go. Okay, what is this thing known as? One more time.
Sine wave.
A sine wave. Well, how do I get from there to here?
Chop off the tops.
Well, I could do
Lows
that,
and highs.
but then it still goes up. I mean, basically, I have to superimpose this. How do I do that? I can certainly go from this to this.
You have to
But-
put a lot more power in at the beginning and hold it.
Yeah, right. I can do that. So, but how do I actually make this square wave down here? Well, it turns out this is advanced math, but it's important nonetheless. Oops. Here we go. Okay, so there's a sine wave. And here's another sine wave. And here's another sine wave. And here's another sine wave.
It's the integration of sine waves.
It's the summation of different sine waves of harmonic frequencies of the fundamental frequency. So you actually have a square wave with different amplitudes of those corresponding higher frequency sine waves that ends up being very close to a square wave. So what that really means is that a square wave contains an infinite number of sine waves of different frequencies. So let's say that your frequency that you're looking for is 60 hertz. You want to make a 60 hertz square wave. That means it would actually have potentially 180 hertz in it and 300 hertz in it. Let's say you have a really dirty inverter that's making power for your computer off the battery, 420 and 540 and so on, all the way up to like 3 kilohertz. Well, that's pretty dirty. But this frequency probably isn't going to bother your radio operations. However, let's say that, for instance, you have a pulse width modulator that's operating at 3,000 hertz, and it's making square waves. So there's 9,000 and 15,000 and 27,000. And what ends up happening is that this actually can generate radio frequency interference. And that's the difference between square waves and sine waves. But I digress. And I could digress a lot more than that too. But, all right, so alternating current, we covered that. Okay, so what is a conductor? A conductor is a material that allows electrons to flow freely. So if I have, we're going to get down into the atomic version of a piece of wire. Sorry, we're drawing individual atoms. Okay, so here are individual atoms. Inside each atom, we have a really small nucleus, and spinning around outside of the atom, we have different shells full of electrons. Okay, what are electrons again? What charge do they have?
Negative.
Negative charge, right? So let us say that we have these electrons are all held really tightly by that nucleus. An electron, because the nucleus, all those nuclei are positively charged and the electrons are floating around and they have negative charges. Let's say an electron gets pushed in. Well, it's not going to get absorbed by anything because they're all tightly held. There's no additional space. That would be known as an insulator. because there's no more room. But let's say that in this other, free living sort of loosey-goosey world of metal, let's say copper, these electrons on the outside are kind of like, no, I sort of belong to this atom, but if there's another one, maybe I'll go over there. And that one, well, maybe I'll go down here. So another one comes in and takes its place. This electron right here is cool with that. It'll just move over here. And well, but now there's an excess over there. So it's like, okay, I'll just move over here. And well, then maybe it'll move, it'll push another one, and it'll come down here. Eventually, what's going to happen is, to balance things out, the electron's going to come over here. So this electron over here, what happened to it? It came in and it displaced another one out the other end. That is known as current. That is current. Basically, the amount of electrons per second passing through a given point. This is a really, really magnified version of copper. In reality, there's millions of atoms thick, billions of atoms thick of copper. This happens continuously on a very, very microscopic scale. If I pushed a lot of electrons out, it would be really easy to push a lot of electrons. If I pushed a lot of electrons in, it would be really easy to push them out the other side. Copper is a really good conductor. It conducts electricity. So what are some other good conductors?
Aluminum.
Aluminum's actually really good, except that it oxidizes.
Gold.
Silver. How about some poor conductors, which would be insulators?
Glass.
Yeah, glass is a great insulator. Other
Ceramic.
ones?
Ceramic.
Certain ceramics, yeah.
Wood.
Got a lot of air in it.
Plastics.
How about one really, really good one?
Rubber.
How about a really good one that's everywhere?
Air.
On Earth. Air is a fantastic insulator. Air actually has a breakdown voltage of about 10,000 volts per inch. So you would need 10,000 volts over here in 1 inch to arc across. Unfortunately, it's also dependent upon moisture. The more water vapor there is in the air, the worse that becomes. But dry air is actually really, really good. Well, what happens if it gets a little moist? And then you get a voltage of many thousands of volts on one side.
Static arc.
You get an arc. You can also get lightning. Okay. Let's see. Okay, so we did Ohm's law. Okay, somebody tell me what Ohm's law is. There are two versions of Ohm's law. The two formulas.
V equals IR.
Right? We use the letter E just because that's electromotive force. E equals IR. What is E again?
Voltage.
Electromotive force. What is I?
Amps.
Amps or current. And R?
Resistance.
Ohms. And what is resistance again?
Ohms.
Yeah, but what is it?
The resistance to current flow.
Resistance to current flow. And in particular, it is the resistance in current flow to any current, AC or DC. It does not matter. Okay, so then what is the other form of Ohm's law? That's the power equation. Somebody give it to me. P equals I times E.
Yep.
Okay, so power is equal to current times voltage. Okay, so now what we're going to do is draw that same circuit, and we're going to have our E and our R and our I. And okay, what's something that's really important about power and energy?
You can't create it.
That's right. It can only change form. So conservation of energy, very important. Okay, so let's say our voltage E is equal to 10 volts. Our resistance is equal to 10 ohms. Somebody tell me how to set this up and find the current. Draw our circle again. Always go back to the circle if you can't remember what to do.
E divided by R.
That's right, because we have E divided by R. I equals E over R, which gives me how much current? 1 amp. Okay, so now we have our current and we have our voltage. Let's figure out the power. P equals I times E equals.
10.
Okay, so we
Watts.
have 1 amp times 10 volts equals 10 watts. Okay. Where's the power? Where does the power go? This is actually in joules per second. A joule is a unit of energy. It's the SI unit of energy. Where does that go?
Through the resistor, heat.
Comes out as heat because energy has to be conserved. Energy that is burned up in a resistor has to come out as heat. So 10 joules per second will do what to the resistor?
Heat it up, make it warm.
Make it warm. That's right. So if you have your resistor like this, and let's say that this resistor is rated for 1 watt of heat dissipation, what will happen to your resistor?
It'll melt.
Actually, it'll probably catch fire and release all the smoke, and then it won't work anymore. Everyone know what smoke is? The magic stuff inside all electronics that makes it work. Everyone heard that? If you let the smoke out, it doesn't work anymore. The smoke is the stuff inside electronics that makes it work right. So once you let the smoke out, it doesn't work anymore. So, okay, so
E equals I times R is Ohm's law. Is
Yes.
P equals I times E is
also Ohm's law. It's the other version, the other form of Ohm's law.
okay.
Okay, so now let us say that we have a resistor in there and we've redesigned our resistor. Here's the resistor, and here's a bunch of metal vanes that increase its power dissipation to 15 watts. What will happen to that resistor?
It should maintain.
It'll maintain its temperature. It'll heat up to a certain temperature and then stay at that temperature and not burn up. Well, we can actually use this device intentionally. What is this known as?
A heater.
That's a heater. That's called a resistance heater. That's right. We're converting electrical energy into heat. So let us instead change this circuit to, I love having an eraser like that. Okay, let us instead change the circuit so that our E is now 120 volts. That would be AC. But the reason we can still do the equations is because that's our RMS voltage. It has the same power generating equivalent of 120 volts DC. So our E is going to be 120 volts. Our resistance is going to be 12 ohms. Okay, somebody tell me what the I is.
N.
E equals IR. I believe you're correct. Is 120 divided by 12 is 10 ohms. Or sorry, oops. Would be 10 amps. All right. Okay, excellent. So now what is our power dissipation? P equals I times E would be 10 times 120 is, everyone get 1200 watts?
Yeah.
Yeah.
Okay, what is this known as if this is the intent of the device? You might have one in your cold garage.
A heater.
That would be called a space heater or a resistance heater. Okay, so we have now decided that we're going to use a 12 ohm resistor and hook it up across our 120 volts and maybe run a fan across it and make 1200 watts of heat on purpose to heat up our cold space. That's known as a space heater. So now We've done some power calculations. So now we're going to do something else with this heater. We're going to say that, oops, we had a little bit of a problem. And here's the little bit of a problem. We had a little bit of a short circuit in our space heater, and the resistance dropped to 6 ohms. Okay, what's our new current?
20 amps.
20 amps. Okay, so what's our new power? 20 times 120 is
2,400 watts.
2,400 watts. Okay, couple of problems here. Let us say that I was building something that nominally would draw on the nameplate. It would say 120 volts AC, 10 amps. What if I were trying to build something economically? What ampacity, what current handling capability would I use for my wire?
A little more than that, just for
A little more
safety.
than that, just for safety. So let's say my wire was good for carrying 12 amps of current without melting, without getting so hot that it melted the insulation and started a fire. All right. Well, here's the other thing. Let us also say that I was picking a resistor that was able to dissipate for nominally 1,200 watts. Let's say I picked a 1,500 watt resistor. Normally it would be fine. What have I just done? What has happened?
Double the amount of power.
Yeah, I just doubled the amount of power, and I have now exceeded the design of my system. It is now carrying 20 amps instead of 10. And it is now carrying 2,400, now dissipating 2,400 watts instead of 1,200. Okay, what's the problem here?
You forgot to put your 15 amp breaker in there.
I forgot to put any kind of overcurrent protection in here. So the reason I need overcurrent protection is because I cannot predict the things that might happen. So I need a little black box that I'm going to drop into my circuit. And that circuit is going to be my safety valve. My get out of jail free card if something goes wrong. So if my resistance, for instance, drops off and I get 6 ohms because my resistor actually looks like this, typically like a coil of wire, and something happened and I got a short circuit right here. This basically is no longer resistive and I get something like this. My resistance is now considerably lower than it should be. Has anyone ever had this happen in a toaster oven or something? You get a spot where it's like super, super hot and bright for a really short time, and then it doesn't work anymore. I have had that happen. Normally it glows kind of like a nice orangish red, except right there in this one spot, it becomes bright yellow, right? And that is the act of the thing committing suicide. Well, in order to make sure that it doesn't burn your house down in the process, because why would your house be built with wiring that could handle 20 amps when really you're only ever going to use 15? Well, all of a sudden you're pulling 20 amps all the way back in the wiring inside your walls. If you don't have any kind of protection, what will happen to that wire?
Burn up.
It'll get
It'll
hot.
melt and burn.
It'll get hot. It'll get really hot. And because it's inside your wall and there's wood in there, what might happen?
Fire.
Flames.
You'll burn your house down. That's right. So in order to protect that, we have something that says, okay, we're going to say that if we start getting more than 10 amps through this thing, we're going to put a device here that's going to sense that and blow up on purpose, and thus protect your house, protect the device, essentially prevent a fire. This is known as a fuse or circuit breaker. So why should you never increase the size of the fuse or breaker without knowing what you're doing?
You could burn your house down.
Because you could burn your house down. That's right. So what happens is if this is specified to carry 10 amps and all of a sudden you have a failure that causes 20 amps to go through, your wire will get hot, but your fuse, because it's been engineered that way, will get hotter faster. And internally, there's a little piece of wire which will melt. As your wire melts, it'll vaporize, and that will become an open circuit. And what does that do to your whole circuit? What is this new circuit called that I've just drawn?
Open circuit, it stops
That-
the flow.
And it stops the flow and it turns off your device and keeps your house from burning down. All right, that is known as a fuse. Okay, so series and parallel. We're going to do series and parallel next. Okay. Okay, so we now have one resistor and another resistor. So current that flows through one resistor and then another resistor has to encounter both of them, correct?
Right.
Okay, the current through this point is the same as the current through this point. The current at any point in a series circuit, if it's just a simple series circuit, has to be the same. Now, what do we also know about Ohm's law? E equals I times R. By definition, the total voltage across this circuit, if we go around the circle, has to be zero. If we start at 0 volts, we go to E up here, and then we have E minus VR1. And then here we have E minus VR1 minus VR2, because we lose voltage as we go through each resistor, and that better be equal to 0. Which basically means that every time we encounter a resistor, we experience a loss of push, our ability to push current. The bigger these are, the less overall current we'll have. And again, each of these experiences a different voltage. If we were to take our voltmeter and put it across this resistor, we would be able to measure a voltage. If we took a second voltmeter and we used it to measure the voltage across this resistor, we would measure a different voltage potentially. Those voltages are proportional to the resistances. We can actually use this circuit to our benefit. Let's say that we were to take the voltage right here and use this and run this off to another circuit on purpose. It would necessarily be lower than the total voltage. And this is known as a voltage divider. Right? This is a series circuit. We have our resistors in series, and it splits the voltages, and each resistor experiences a different voltage across it, but they experience the same current. So now, what is the problem with doing a circuit like this? Everybody, does anyone have a Christmas tree? Not this time of year, but have you ever had a Christmas tree?
Oh, if one of the resistors breaks, you stop flow completely.
That's right. If you lose a light in your Christmas tree lights, what happens to the other ones?
They all go dark.
They all go dark because they're all experiencing the same current. And if you have an infinity resistance here, you get no current through anything. So now let us draw this in a different and more useful way. Okay, the voltage here is E. And the voltage here is going to be E, and the voltage here is going to be E, which basically means that every device experiences the exact same voltage. The current through each one is going to be defined by the resistor that it is. So if I take this resistor and I make this an open circuit, how much current will be flowing through this R2?
0.
0. Okay, so what? So I just took this out of the circuit. What'll happen to my first one?
It keeps working.
Keeps working. This is how your house is wired. Your house is a parallel circuit. That's why when you pull out a light bulb, the other lights stay lit. Every one of those devices experiences the exact same voltage. The currents are different. The voltages are the same. Okay. Let us see, where are we now? DC power, we've already done. All right, we're gonna do units and then we're gonna take a break. Okay, so here we go with units. And we sort of covered this a little bit. If everybody, oops. There we go. Okay, so units. This is basically replacement of numbers with a letter or a symbol. So our unit of anything is one. That's the definition of a unit. We can make something 1,000. We can make it 1,000th with 0.001. We know this as a K, and we know this as a little letter M. All right, what does the K stand for?
Kilo.
Kilo, like a kilogram or a kilometer. We can also use a million. That's a big letter M. What does the big letter M stand for?
Mega.
Mega. We can also make it bigger than that, 1,000 times bigger. That would be a giga. We know that because we're familiar with gigabytes now and gigahertz. And we can also go smaller. 1,000th, little letter M is a milli. 1 millionth is a micro. 1 billionth is a nano. And if we go even smaller than that, it's a pico. And we can go bigger because people have big hard drives now.
And we can go to terabyte.
And that would be tera. Big letter T. So these are our basic units that show up everywhere. And the nice thing about these units is, let's say that I wanted to represent 3260000 hertz. Well, okay, that's still a lot of zeros. There's a decimal point here after it, and I can slide the decimal point over 1, 2, 3, 4, 5, 6, and put it here. Well, I've taken up 6 decimal points. That is actually 1,000,000 times. Or 10 times 10 times 10 times 10 times 10 times 10 is 10 to the 6th power. So that would be 3.26 times 10 to the 6th power, 6th hertz. And I can also replace this with mega, and that would now become 3.26 megahertz. I have now converted my number with a lot of zeros to something that's a lot easier to deal with. That is the whole point of doing units. Similarly, I could take something that's really small. For instance, I could do 0.00002. Let's do farads. Okay, so now let's slide it over this way. 1, 2, 3, 4, 5, 6. Okay, so we went 6 places that way. So that's 1/10 times 1/10 times 1/10 times 1/10 times 1/10 times 1/10. That's 1/10 to the 6th power. By convention, 1/10 is equal to 10 to the -1. That's how the numbers work. And then you raise that to the 6th power, and you can multiply those together, is 10 to the -6th. So now you have 2 times 10 to the -6th farads. And we now know also that 10 to the -6 is replaced by the little letter, Greek letter micro, and that would be 2 microfarads. And now that's our new unit. And in fact, you can then go out and buy yourself a 2 microfarad capacitor, which is the same as that. It's just called something that is actually usable. So with capacitors, we use micro. We also use pico. With inductors, we use milli and micro. With resistors, we do a lot of kilo and mega. Okay. Everybody ready for another 5-minute break?
Sure.
Okay. Come up with those questions. All right, let's hear who's got some questions. There must be some questions.
Well, going back a little bit on the sine wave versus pure sine wave versus modified sine wave,
Mhm.
what's the downside of running a device off of a modified sine wave inverter?
Noise.
Right, okay, so
Electrical
noise would affect transmission, but what about like powering
Like a computer?
microwave or a computer, but a computer usually has a power supply.
Right.
Yeah. So
That would
something
probably
that
be
doesn't have
okay.
a power supply.
Electronic devices like sine waves. They
Uh-huh.
like clean power.
And so a microwave would be an electronic device.
Yeah, the actual, like the magnetron wouldn't care. That generates the power, but the control circuitry probably would.
Uh-huh. And what does it do when you say it doesn't like it? What does it do? What is the effect of it not liking it?
Well, your power supply is designed to convert, let's say 60 hertz to DC.
Okay.
Well, let's say that your signal has 60 hertz in it and it's filtering for 60 hertz. But then there's also these other frequencies that are thrown in there that can get through.
Mhm.
Depending on how your power supply is built, those other frequencies could actually get through on the DC. And then you'd basically have DC with superimposed ripple noise coming through. Your electronic circuits, transistors don't like to see that, which might make them not work properly.
So they get hot.
No, well, they could get hot, but they
or
probably typically what would happen is, I mean, an electronic circuit likes to see either because it's digital, it likes to see either on or off. If you have something that's on, but it's bouncing, sometimes it could be viewed as off when it's really on, or vice versa. In which case it doesn't work anymore.
Okay.
So, I mean, most things that have an electronic power supply in it will be able to survive it. But that's why for, certain things, it's really important to have clean power. I mean, like a space heater will not care,
Right, right. But
but
maybe
because it's resistive. But things that are electronic, sensitive electronics, possibly will care.
Mhm. Okay.
All right, let us continue. Where are we on the pages? Okay, so we just did our units. Okay, we're on to decibels. Yay, I like decibels. Decibels, this is sort of like the language of exponents. All right, everybody ready to do a little more math? I hear lots of yeses, right?
Oh, yeah.
Oh yeah, okay, here we go. Lots of math. All right, it is important. We already sort of covered this with units. What we're going to do is say we're going to have 10 times 10. Okay, we're going to do the number 10,000. 10 times 10 times 10 times 10 times 10. Does everybody agree with that? Which is by convention 10 to the fourth power. That means 10 times itself 4 times. Okay, so now what I'm going to ask you is, what is the exponent on that number 10? What is the number of the exponent?
4.
That would be 4. Okay, this would be the power to which 10 is raised to get that number. Right? Because 10 to the fourth power is 10,000. So let's do another number. Let's do 100,000. Another way to write that would be 10 to the fifth. So the exponent there is
5.
5. Okay, so by definition, we could also say 0.001, which is 1/10 to the third power, is 10 to the minus 1 to the third power, is 10 to the minus 3. So in this case, the exponent would be -3. So this means that things that are bigger than 0 get a positive exponent. Things that are smaller than 0, or sorry, things that are bigger than 1, things that are bigger than 1 get a positive. Things that are smaller than 1 get a negative exponent. Okay, so if you start at 1 and you go up to 10,000, are you getting bigger or smaller? Not a trick question.
Bigger.
Bigger. If you start at 1 and you go down to a 1/1000th, are you getting bigger or smaller?
Smaller.
Smaller. Okay, let's ask this question. If I start at 1 and I go up to 10,000, and then I multiply that by 0.001, what will my new number be?
1.
Try that one again.
001. Wait.
10.
That'll be 10. All right. So I went up by 10,000 and down by 1/1000th. So this is a +4, and this is a -3. Well, what's 4 minus 3?
1.
1, which means that this answer should be 10 to the 1. And in fact, it is. So this is how our exponents work. Now, Alexander Graham Bell came up with something called a bell. And a bell is a reference to a certain known value that is exponential. Kind of like the way we sense earthquakes, where every number is, like, let's say 10 times higher than the previous one. It's a logarithmic scale. So what we now have is 10 to the something is something. Well, so what we then do in order to come up with this new term is we take the logarithm base 10 of both sides, and we end up with question mark equals logarithm base 10 of something. logarithm is the opposite or inverse function of exponents. It's kind of like a reverse exponent. So what we now have is, let's say that we have log base 10 of 10. That would mean what power would 10 have to be raised to get 10? So 10 to the what is 10?
10 to the 1.
So the log
10.
base 10 of 10 would be 1. What would the log of a base 10 of 100 be?
2.
That's right, because 10 to the 2 gives you 100. What would the log base 10 of 0.01 be? By definition,
-1.
10 to the
3.
-1 is 0.1. 10 to the -2 is 0.01. So notice that exponent. So the logarithm of 0.01 would be -2. Okay, so this is known as a bell. A bell is a representation of, it's the log base 10 of thing 2 over thing 1. And it doesn't matter what those things are. It's just a way of comparing logarithmically how much bigger something is than something else on a log base 10 scale. Where we use this is typically in power. You can also use it for voltage, but we typically use it for power in radio. And so now we have a bell is a log base 10 of P2 divided by P1, power 2 divided by power 1. So we could now say that power 1 we're going to set to 1 watt and power 2 is 10 watts. Okay, so what is the log base 10 of 10? 10 has to be raised to what power to get to 10?
1.
1. Okay, so how about if we did this? Log base 10 of 100 divided by 10.
10.
1.
That would also be 1, because what's 100 divided by 10 is 10. That would also be log base 10 of 10. It's the exact same thing. So it is a change. It is a measure of the amount of change from one thing to another. So if I were to do this and say I'm going from 100 up to 1,000, I would get the same answer. That is known as a bell. That is known as a unit, a measure of bells, which is a reference, a change from a reference point to a new point. Well, as it turns out, the bell is a really large unit. So we created something called a decibel, which is a dB. And deci means 1/10. So a decibel is 10 times the log base 10 of P2 over P1. That is the definition of, for power, a decibel. So, or the measurement of decibels. So for an example, let's do log 10 times the log base 10 of, let's say we go from 1 watt up to 100 watts. Okay. That's 10 log base 10 of 100. So what is log base 10 of 100 once again?
2.
10 to the 2. So that would be 2. So that's 10 times 2 is
20.
20 decibels. Okay. So now we can also do this. Let's say we started instead at 100 watts and we go to 1. So we're cutting it down. Okay. So what is the log of 1/100th?
Minus
Minus
two?
two?
Minus 2. So it's 10 times minus 2 is minus 20 dB. Okay, so dB plus would be known as gain. Any idea what dB minus would be?
Loss.
That would be
Negative
loss.
gain.
That would be loss. So what happens if you go up by 3 dB and then have 3 dB loss? What would the end result be?
Nil.
No gain.
0. No gain, no loss. And what's cool about this is that it doesn't matter where you started. If you, at any reference point, if you start at a particular point and you increase by 3 dB, and then you decrease by 3 dB, your result is 0. You're exactly where you started. And this is a very handy notation because you don't have to carry all those zeros around. You don't have to say, I started at 822 milliwatts and I went up to something and then I lost it and then back down. You can just say, I started whatever power I was at. I had a gain of 3 and then a loss of 3. And here I am back at where I started. You can also say that, let's say I started at 6 watts and I went up through my antenna with minus 10 dB of loss in the feed line. And then I have a 15 dB gain antenna. Okay. So what is my net change? I started at some reference point. I went down by 10 and then up by 15.
You increased by 5.
That's plus 5 decibels. Okay. Now we can go back and say dB is 10 log base 10 of P2 over P1. In this case, we already know what our starting point was. We can say 10 log base 10 of something divided by 6. And our decibels, we already know what it is because we figured it out. It's plus 5 dB. Could we solve for that?
Yeah.
That's the only thing we don't know. And it's a little bit of math to do. You'd have to take, you'd have to go and divide both sides by 10. You have to go 0.5 equals log base 10 of something over 6. And then you'd have to take the exponential of both sides. 10 to the 0.5 is equal to question over 6. So question mark is equal to 6 times 10. Oops. 10 to the 0.5 power, but you could do it. And that would tell you what your effective amount of power at the top would be after your gain and loss. So you can very easily, you can use math to do it. However, what it turns out we're going to do is we're going to simplify this process considerably. So 10 log base 10 of something. We're going to say, what gives us a value of 10? That would be 1. So the log base 10 of something is 1. What is that something? That's 10. So 10 times is equal to 10 decibels. That is one of our things. That is one of the only things that you need to know. Here's the other one. 3 is equal to 10 log base 10 of something. And it turns out that this is approximately equal to 2. So 2 times is approximately equal to 3 dB. If you have these two things, you can get very close to knowing what your result is all the time, no matter what you're doing. These are, I don't actually memorize any others. These are the only two that you need to know. So what's cool about it is that if you go up by a factor of 2, what is your change in decibels?
3.
3 decibels. If you go down by a factor of 2, what is your change in decibels?
Minus 3.
Minus 3. So 2 times equals 3 dB with a plus. 1/2 time is negative 3 dB. 10 times is 10 decibels, exactly. And 1/10 is equal to negative 10 dB. So we have now just greatly simplified the whole process of figuring out what a change will do for you. Now, the other question, of course, is why is this so important? Because when you go and you look at an antenna, you will see a gain of an antenna specified in decibels, meaning that if you put power in this particular direction, the amount of effective energy that you will get in that direction is increased by the number of decibels. So because it's based on a reference point, it doesn't matter where you start. If I have an antenna that gives you 10 decibels of gain, and I put one watt into my antenna, what will be the effective amount of wattage that I get coming this way?
10.
It'll be 10 watts. It'll be robbed from all the other directions because I've decided to build my antenna that way. It will be much lower in the other directions, but in the forward direction, which is where I care about, it will be like I'm running 10 watts. If I were to change that and say that I have 5 watts, what would be my effective amount of energy coming out?
50.
It would
50
be
watts.
50 watts because it's a gain of 10 times.
Oh,
So here's the next one. Let's say that this antenna now was increased to 13 dB. Okay, so how can I write 13? It's 10 plus 3, right? What does the 10 give me?
10.
10
50.
times. What does the 3 give me?
2x.
2 times.
2 times. And what's 10 times 2?
20.
20 times. So then all of a sudden, I now have the effective transmitting power of 100 watts. The other thing is that if anybody has ever seen on a radio something called an S meter, which is a signal strength meter, this is actually measured in S units. By convention, 1 S unit equals 6 dB. So guess what? If I now have a gain, if I've induced a gain of 13 decibels, how much stronger is my signal on the receiving end? About 2 S units louder, which means that if I was an S3, my signal strength is now an S5, which means the other person will be able to hear me better. That is how an antenna with gain can translate directly into being heard better or being heard worse. Because I can also do this. Let's say that I'm lucky enough to have a 100-foot tall building that I live in, but I'm unlucky enough to have my station in the basement. And I have an antenna up here, which has 10 decibels of gain. But I also have a cable, and my cable is, again, it's 100 feet long. And at this particular frequency, I have 6 dB of loss per 100 feet. What will my loss be in that length of cable? It's 100 feet long, and I have
6
100 foot of
dB.
cable. That's right. It will be
Minus
negative
6.
6 dB. So what will my net be?
4
4.
dB.
It'll be minus 6 plus 4, well, plus 10. It's equal to plus 4 decibels. So let us say that I wanted to improve things, and I replace the cable with something that had a loss of negative 1.5 dB per 100 feet. What would my new calculation be?
8.5.
It'd be negative 1.5 plus 10 is 8.5 decibels. Okay, so by changing my cable, what have I done? I've increased from 4 dB up to 8.5. Doesn't seem like a lot, right? It's 4.5 decibels. And what do we know about 3 decibels?
It's twice the power.
3 decibels is twice. So that leaves 1.5 decibels left. So maybe it's gone up by a factor of 3, which means that just by changing my cable, I have the effect of having 3 times more signal coming out of my antenna. Just by improving my cable. Which is why cable TV, it's so important for the cable company to use decent cable. Because if that signal drops off, then you don't get a picture. All right, so now we've done some basic RF design. Congratulations, everybody. We've done some basic RF design. Okay. We are now on to page 15 in the book. All right, electronic components and circuit diagrams. Okay, this thing, what is this thing called?
Resistor.
A resistor, and it has what is its unit of measurement?
Ohm.
Ohms. It's a resistor. It has resistance. Its measurement is ohms. If I were to take this and make this variable, which means I can adjust its value, this is now called a pot or a potentiometer. Like a 50K ohm, for instance, potentiometer. This would be variable from 0 to 50K ohms. And why would I want to use something like that?
Tune a filter.
Well, no, you could tune the gain of a filter because this would cause loss. I could also use that to adjust my volume. Right? I could use it to adjust signal levels. Okay, our next thing that we're going to do is something called a capacitor. A capacitor is basically 2 metal plates with a space in between that can either be filled with nothing, air, or filled with something like glass or mica, which is a kind of a rock, or plastic. Its basic goal is to keep electrons from jumping across the gap. If you increase the voltage beyond what a capacitor can hold, what will happen?
Spark.
You'll get a jump from one side to the other and your capacitor will be kaput. So you don't want to do that. You don't want to over voltage your capacitor. Okay, now we're going to get back to a little bit of physics here. We're going to have 2 charges, a plus charge and a minus charge. What do we know about pluses and minuses, everybody? Opposites do what?
Attract.
Opposites attract. These are trying to pull themselves together. So if we have a lot of them here, what is it trying to do to this material in between the capacitor plates?
Reduce the distance.
It's trying to reduce the distance, and the material is fighting back, right? The act of these charges putting a pull or a push on those 2 plates actually causes a force, and this is called an electric field. It puts energy inside the 2 plates. It tries to pull them together using something called an electric field. And that's proportional to the amount of charge on both sides and the voltage on both sides. Okay, so this is known as a capacitor. I could do this with a capacitor. That would make it variable. That means I could change the size of the plates that are parallel to each other. That would make it a variable capacitor. The unit of measurement of a capacitor
Farads.
is a farad, F-A-R-A-D, named after Michael Faraday. Okay, so now we're going to draw this one. This is a coil of wire spooled up. Okay, so this a capacitor contains energy in an electric field. Well, The analog to an electric field in electromagnetics is what?
Magnetic.
Magnetic. Okay, this would be known as an inductor. And an inductor is measured in the unit of henries. And if everybody holds up your hand, sticks out your right thumb, got to be the right hand, stick out your thumb and take your fingers and curl them over, forward. This is known as the right hand rule. Again, basically, if you have a current flowing in the direction of your thumb, it will generate a magnetic field that rolls over in the direction of your fingers. So if you hold your hand up and point it toward you and move your thumb toward you, the magnetic field will curl that way. If it's going away from you, the magnetic field will curl the other way. So a current carrying wire generates a magnetic field. Well, what do you think a magnetic field with a wire in it will do to the wire?
Induce current flow.
It'll make a current flow, which means that if you have two wires in parallel and one of them is carrying a current and it makes a magnetic field going around it, what will happen to the second wire?
Create a current flow.
It'll create a current flow in the other wire. That's right. This is called inductance, mutual inductance. And this is why we do what with our microphone cables?
Shield them.
You shield them because that keeps them from being affected by the other one. Otherwise, you'll have crosstalk and noise getting back between two different wires. Sometimes we want this, actually. When do we want this to happen?
Transformer.
Yeah, a transformer. What else? Radio antenna. We make a magnetic field that goes around. It gets picked up by the other one, and it puts your signal into the receiver. We actually want mutual coupling to occur there. I mean, that's the whole purpose of sending out a radio signal. Okay, so an inductor is a coil, and what ends up happening is that because this is all coiled up, the magnetic field actually ends up looking like this. So it makes a coil. A coil makes a magnetic field that kind of goes around from one end to the other. And that actually makes a north and a south pole, which you may recognize as parts of a magnet, like an electromagnet. An inductor is a fundamental component inside an electromagnet. Okay, so
Does the north go direction of the thumb or the other side of your
you
hand?
know, I don't remember. I have to say, I do not remember that. All right, now batteries. As we're on the bottom of page 16. As ham operators, we often use batteries to power our equipment. What is the nominal voltage of a car battery, everyone?
12.
AC or DC?
DC.
DC. What is the nominal voltage of wall current in your house?
120 volts AC.
AC, and that's actually AC RMS. You don't have to remember that, but someday it'll be important to you.
Doubt it.
You never know. If you ever go to buy a meter, you'll have to make the decision to buy a true reading, a true RMS meter.
I have meters. They don't. I just bought it at Sears.
Okay. I have my $3 Harbor Freight meter. I also have my $300 my $300 Fluke. One is a true reading meter. Take a guess which one.
I'm gonna guess it's Fluke.
Yeah. Okay. A carbon zinc battery is your standard heavy duty battery. That's not rechargeable. Once it uses up its electric, once it uses up the chemistry inside that generates energy, it goes in the trash. That's known as a carbon zinc. What kinds of batteries are rechargeable? Everybody?
Rechargeable batteries.
Name some.
Nickel metal
Rock,
hydride,
carbon, zinc.
lithium.
Yep.
Right,
all of them.
Yep. Nickel metal hydride, lithium ion, lead acid gel cells, nickel cadmium, good old NiCad. There's also a lithium iron phosphate. There's a whole bunch of rechargeable ones. Now, it's important to note that a true lithium battery, like if you've ever seen like the 10-year batteries that run stuff forever and eventually die, like a little coin cell, those are lithium batteries, but those are lithium metal and are not rechargeable. So not all lithium batteries are rechargeable. Okay, the electrical component used to connect or disconnect circuits is known as a switch, essentially creating an open circuit. Electrical component used to protect other circuit components from overloads.
The fuse.
That would be a fuse. Okay. All right, now we are on to semiconductors. Do we have any questions before we move on to semiconductors?
What's the difference between how does a breaker work in terms of its ability to pass power
Okay.
bidirectional?
Here we go. Okay, so this is a fuse. Okay, the point of a fuse is to sense a current, and at above a certain current, it will generate a lot of heat, at which point it will melt the conductor inside. A thermal magnetic breaker is exactly that. And the way that it typically works is that you have a heating element. And right next to the heating element is a bimetallic spring. And what happens, anyone ever seen a bimetallic spring? Basically, this generates heat based on the amount of current that's flowing. When this element gets up to a certain temperature, it goes boing and flips back the other way. That's a thermal magnetic switch. And once it goes boing, you now have an open circuit here. And that's how a breaker works.
Can current flow either direction through a breaker?
Yeah.
And so
Yeah,
it doesn't.
It's just using heat. That's why they work for AC.
What about DC?
They work for DC too.
Same DC.
Yeah, this will work
Wouldn't
for
make any
DC
difference
also. Nope.
which way current flows.
Heat is heat.
Okay.
But that's also why if you use a thermal magnetic breaker, you need to specify the amount of current that it's rated for, because
Why does
that'll
some-
determine how hot it gets.
Why do some breakers have input and load? Or input or output or source or load?
Well, you can also have a breaker that breaks a secondary circuit. So they can actually be designed, as a switch that can actually break a second circuit. That would be more of a relay.
GFI on them.
Sorry, what?
Some of the breakers that have multiple inputs on them also have GFI.
True. And you guys want to know what a GFI looks like? Okay, so here's a GFI. Everyone ever heard of a GFI?
Sure.
Okay, ground fault circuit breaker, GFCI. Very important. So you have your hot and your neutral. Okay, ideally, what's going to happen? You're going to have a device hooked up on the other end, right here, that's connected to your line or your L, which is your hot and your neutral. All the current that goes into one side is going to do what?
Go out the other.
Go out the other side. What a GFCI does, very simply, is it measures the differential in current flowing this way and current flowing this way. Because if it sees a difference, where does that mean the current is going?
Somewhere else.
Somewhere else, right? Which means that it could be flowing from this thing down to ground. Well, if that's happening, what is represented by this dotted line?
Short circuit.
Some sort of short circuit. It could even be a high current. It could even be a high impedance circuit. But what is frequently represented by this line is, I'm going to draw this.
Leakage.
It's leakage. And we're going to draw a person in a bathtub, right? we're going to put a dead person in a bathtub because this person was unlucky enough to drop a hot air dryer into the bathtub without a GFCI. Okay, so what happened in this case is that without a GFCI, your line voltage went into the bathtub. The drain of the bathtub is connected to metal pipes. And what are metal pipes connected to?
The earth.
Ground.
The earth, ground. That's right. So in the process of doing so, you ended up with a voltage path that went down through the tub, thereby electrifying it and then going to ground. A GFCI would basically sense if there was 5 milliamps of current or more flowing through that circuit. As soon as it did that, it would open the circuit and cause the breaker to trip, thereby keeping the current flow below the point at which this person would die. See, now he's smiling because he's not dead. And that's the whole point of a GFCI. It's to protect personnel from getting electrocuted. Okay. Device that allows current flow in only one direction is called a diode. All right, so there's an anode and a cathode. The anode is your positive terminal. Your cathode is your negative terminal. If you were to draw this the way that it's physically built, it's usually a little cylindrical device, although it could actually be really, really tiny little chip diode that goes on a surface mount in a surface mount package. You'd have a plus and a minus. The cathode or negative terminal is represented by a band on this, like a physical band that's drawn on the device. And what is important about a diode is that internally it has P material and N material. The P material has extra pluses, the N material has extra minuses. And because of that, what you have to do is you have to get above a certain threshold for this P to be overcome and for the N to be overcome, which basically means that if you try to push current through it in the opposite direction, it does not go. If you try to push current through it this way, the current does flow, which means it's now a one-directional device. A very special kind of diode, in addition to allowing current to flow in one direction, emits energy in the form of visible light, which looks like that. Anyone?
LED.
LED, light emitting diode.
So can I, just one question?
Yep.
I remember anode being anode as a negative and cathode being cathode as in positive.
Yeah.
That's why am I confused here?
I think because you have anions and cations, and we come down to the fact that it's backwards again.
Okay.
Because it deals with electrons, it's semiconductor material.
Okay.
So yeah, I know.
So when you play, wait, but what I'm getting at is, so then in order to have it flow, the current is flowing from left to right. Is that right?
Correct. It flows from the plus
Okay.
to the minus.
Right. Okay.
Okay, let's see.
Is that in reality or in the circuit diagram?
In the circuit diagram, it flows plus to minus because
Yeah.
current is defined as plus to minus. Okay, now we can also take this device and we can build it in a different way. We can have a triple layer instead of 2 layers. We can have N, P, and N material. And what this does is it forms something called a transistor. And the way that a transistor works is that we're going to draw something called a bipolar junction transistor. This is the collector, this is the emitter, and this is the base. And its electronic symbol looks like this. And I know this is an NPN. This is a very useful trick. Which way is the arrow pointing? It's pointing out. This is not pointing in. NPN. So this is an NPN transistor. And the way that a transistor works is that you have something called a base and an emitter. And this effectively is a diode. And if your base to emitter junction has a positive voltage on it and you develop a current through here, you will get an amplified version that is allowed to flow from the collector to the emitter. So basically what it allows you to do is throttle the amount of current that flows from the collector to the emitter by putting in a small amount, but a changing amount of current from the base to the emitter. What this allows you to do is make an amplified version of the signal that's coming in at the base. So it might be that you have a tiny little letter B here, and you end up with a giant letter B over here. That is your amplified version of it. To amplify means to make a big copy of. It's not actually making it bigger, it's making a large copy. So that being said, if something is making a large copy, what's one of the things that can go wrong when you're making a copy of something?
Distortion?
Distortion, exactly. So if you've ever heard of distortion of an amplifier and why some people who are purists like amplifiers that are designed with certain components and in certain ways, that's exactly why. Because an amplifier that is a clean amplifier will be very close to distortion free, whereas an amplifier that is designed in a not particularly linear way will create distortion. The difference in between the input and the output of the transistor amplifier is known as its gain. And what do you think? One of the things, what do you think we'd use to measure gain?
Decibels.
Decibels. Yeah, there it is again. Okay, so there's our gain in decibels. The primary gain producing component in an RF power amplifier is a transistor. The primary gain producing component in an audio amplifier would be, unless you happen to be one of those tube guys, that would also be a transistor. A component that contains 3 layers of semiconductor material is known as a transistor. Now, this can also be drawn a different way. Again, this is known as a BJT or bipolar junction transistor as drawn. I'm going to change the way this is drawn a little bit. And here we go. All right, so I just redrew it. Instead of being this, notice on the one on the right, you have your base, collector, and emitter. Notice that they're actually all connected. What do you notice about the one on the left?
It's an open.
Yeah, well, but you have these 2 parallel things. What does that look like?
Capacitor.
That's a capacitor. So the bipolar junction transistor looks for a current to flow. There's not a lot of current that's going to flow here on the left-hand side because it's a capacitor. But what can you change?
The voltage. Yeah.
You can change your voltage. And that will change the amount of current that flows by opening and closing this channel. And this is known as a field effect transistor. The reason that it's a field effect is that what's inside that thing? An electric field, because that's what a capacitor does. So that's known as a field effect transistor or a FET. They are actually much more usable now, much more useful now than the bipolar junction transistors because they use a lot less energy. They're much more efficient. Okay, next we are going to, I'm going to share this. Before we move on, are there any questions? Okay, so now we're getting into practical applications. So can everybody see this screen that I'm presenting right now?
Yeah.
Okay, good. All right. So we are now moving on to a practical use of devices. Okay, so if we look right here, you will see that component number 5 on this drawing right in the middle of the page. We're doing something called schematics. A schematic is basically the electrical connections within a circuit, how something is physically built, all the wires that are connected together. It doesn't show how they're laid out on a circuit board or anything like that, but it does show how they're interconnected. Component number 5 on figure T-1, that is our ground. And notice the ground shows up in 3 different places. Why is that okay?
It shows a common connection.
Because it's a common connection, and all 3 grounds, even though they're not shown, are what?
Connected to each other.
They're all connected to each other. That's our 0 voltage reference for the whole circuit. All of those are actually exactly the same. So if we really wanted to, we could actually connect them all and then show 1 ground. Okay. Item number 2. What is item number 2?
Transistor.
A transistor. And is it a PNP or an NPN? Just looking at it.
NPN.
Because it's not pointing in. It's pointing out. It's because the arrow is pointing out, not in. All right. So if we were to draw this, if we were to look at this circuit, and let me see if I can annotate. Oh, I can. Look at that. If it lets me. Okay, here we go. So we have our first half of the circuit. Okay, so notice that we have a voltage coming in right here. We have a voltage and a current flowing in, and we have a path that goes from this voltage down to ground. When this is on, when we have a voltage that exists, we have a current that exists, this transistor is activated. It's turned on. Once that happens, this channel on this other half of the circuit becomes active as well. So what we do at this point, we have our battery, which is number 4. We have current, which flows up through number 3, which is a light bulb, and then down through the transistor to ground. And when that happens, basically when we have the input turned on, what happens to the light bulb?
Turns on.
It turns on. This is a very simple transistor switching circuit for turning on a light bulb. Okay, so now we'll go to the next one. Let me close that. Oops, how do I get rid of my annotation? There we go, clear. Okay, so now we're into a little bit more complicated circuit. And we are on now page 20. So over on the left-hand side, component number 1 represents a wall plug. Is that going to be AC or DC coming in?
AC.
AC, 120 volts. Item number 2 is a fuse. Why do you put a fuse in there?
Protection.
Protection, so you don't burn your house down. Item number 3 is an on-off switch. All right, how about item number 4?
Transformer.
A transformer. Yeah, okay. So it is going to be really important for us to just go over what a transformer is. All right, so a transformer, what is this device right here? What is that known as? Does everybody remember?
Coil.
That's an inductor, also a coil. Okay, but that's an inductor. What does an inductor make when you put current through it?
Magnetic field.
Magnetic field. All right. So, and if it's time varying, because we're switching it back and forth, it's going to make a magnetic field that does what?
Oscillates back.
Oscillates back and forth. Okay. So sometimes it's going to be going this way, and sometimes it's going to be going this way. So that's great. Anything that makes a magnetic field can be coupled to another, for instance, another inductor. And what will happen to this coil if it senses a varying magnetic field? That will induce a current in the other coil. So the power coming in on the left-hand side will generate power on the right-hand side. But the tricky thing here is that they're kind of far away from each other. So what we do is we take a core made of iron, usually laminated plates, and we do this with it. So this is our core. And we wrap our coils around that core. And what that does, what does everyone know about iron?
It rusts.
It rusts. Yeah. What else about it though?
Magnet.
You can magnetize it. Yeah. It actually is very good at containing magnetic fields. So what this core does is it makes a very favorable path for that magnetic field. And it concentrates the magnetic field inside this core. And since it's concentrated inside the core, most of it is going to go right through the center of this other coil, which basically means that the power going into this side that's generating magnetic field is going to produce power coming out the other side. The other really important thing about a transformer is that it hasn't really transformed anything yet. We have N1 and N2. N1 is the number of turns. The magnetic field is proportional and the voltages are proportional to the number of turns in the coil. What ends up happening then is that the number of turns in each coil is going to be proportional to the voltage. So if I have 120 volts over here and I have, let's say, 240 turns and I have 24 turns on this side, my ratio is then 10:1. I will end up with 120 volts on the input side. I'll end up with 12 volts AC on the output side. And because energy is conserved, P equals IE equals IE. If my voltage goes down by a factor of 10, what's going to happen to my current?
It's going to go up by a factor.
Go up by a factor of 10. So if I have 120 volts at 1 amp over here, I will get potentially 12 volts at 10 amps over here, minus the losses in the coil, minus the losses in the core. If you go outside and look at your power pole, what you will find is that you have a transformer that is typically 12,000 volts on one side down to 240 volts on your house side. So you can figure out if it's 12,000 volts on one side and 240 volts on the other side. You can figure out how much current is flowing, and you can also figure out what the turns ratio inside is. So
what restricts the amount of current that is on the input?
Largely it's a function of, well, what actually restricts it, the size of the wire. I mean, you can overload a transformer and it'll catch fire.
Uh-huh.
There's typically no, I mean, you can also put current protection on it to prevent that from happening. But sometimes you'll see a transformer on a power pole catch fire. So that means somebody overloaded it.
I was just thinking like an old-fashioned doorbell transformer.
Yeah.
That, is connected to 120 volts and it just rings a bell. And
Yes,
what
okay.
stops that something in that transformer from getting burned up because there's so much
Right here.
potential current.
Right here. The fact that your doorbell transformer essentially has some resistance over here. And what you're going to end up with is current and a voltage that are, whoops. On the secondary side, you're going to have current and voltage and a resistance caused by the doorbell transformer. And because of conservation of energy, that's going to determine how much current can flow into the other side. Unless, of course, you get a short circuit, in which case, you know, basically what'll happen is at some point your transformer will saturate and you can't, you know, you can't generate a bigger field inside the core than you can generate. At some point, it won't hold any more magnetic field. And that is actually one of the things that limits the that limits a transformer from overloading too much. Okay, let's see, back to, and we're going to take lunch pretty soon. So if everyone's getting hungry, that's a good thing. Okay, share, yes. Okay, so now we now have our transformer, which is item number 4. We've now generated a smaller AC voltage from a bigger AC voltage. So we now know, what does an AC current look like? It goes up, it goes down. It goes up, it goes down. It goes positive, it goes negative. And what do we see when we do that? We get something that looks like this. Right? Goes plus and minus. What happens when it goes minus with respect to this diode right here? What happens to the diode if the voltage goes negative? The diode gets cut off. It says, nope, no current flow. Okay, well now the only thing that comes out the other side are these positive peaks and there are no negative peaks. Well, if the current's only flowing one direction, what's that called?
DC.
That's called DC. What have we now done with our diode? We have taken AC and we've turned it into very ugly DC. Right? So now we have this capacitor right here. What do we know about a capacitor? When it tends to see a high voltage, it charges up to that voltage, but then it essentially serves as a charge holder. The supply voltage goes down, the capacitor will start to discharge and release some of its electrons or positive charges into the circuit, which will tend to smooth out the picture. The bigger the capacitor, the smoother the picture. All right, so that's item number 6. Item number 7 is a biasing resistor, which limits the current. And how about number 8, which is an LED? What does that do?
Give us light.
It tells you that the power supply is on. Okay, how about 9 and 10? Number 9, that's a variable resistor that basically says that if that's like a voltage and current limit, more of a current limit, to say that it's going to, even if you put it across a short circuit, it's going to say, well, okay, there's at least a little bit of resistance in there. And it will, let's say this is a short circuit, it will keep the power supply from basically dumping an infinite amount of current across the wire. And how about item number 10? Right there. That looks like a diode, doesn't it? For every rule, there's an exception, right? What do we know about diodes?
They only let current go one direction.
Unless they're a special kind of diode, which is known as a Zener diode. And notice it has that funny looking bar. You can think of it as it's turned on its side letter Z. What happens is that a Zener diode will function as a normal diode, but it's been designed specially so that if it's operated backwards, it will basically say, okay, well, I'm going to allow just a certain amount of voltage to exist on it, and then I won't go any higher. So when you buy a diode, that's a Zener diode, you basically say, I'm going to run the thing backwards, and it'll allow a certain amount of current, a certain amount of voltage to exist, and then nothing else. So if I have, let's say 17 volts right here, and I have a 9-volt Zener diode, what will happen is that on my power supply output, I will end up with 9 volts. And any of the excess voltage will get burned off in the power supply. And that will basically take my final waveform and make it nice and flat, essentially chopping off all the peaks. So this is a half wave rectified. Rectified means, you know, fixed. This is a half wave rectified power supply that converts AC to DC. It's basically what you find in here in your computer. It's what runs your computer. That's typically going to be something that's a little bit more exotic, but essentially this is a very basic it's known as a linear power supply. And they work really well. Okay, finally, before we go get lunch. By the way, did anyone bring lunch?
Not for everybody.
Oh, damn.
Yeah, hate it when that happens.
Oh, I know. I was really hoping somebody brought pizza. Okay, finally, what we have here is known as, notice we've got some different looking components there. What's number 2?
A variable capacitor.
Variable capacitor, yeah. And what is number 3?
A variable inductor.
Yeah. Okay, so why would we want to do that? Because some things aren't black and white. Okay, so what I'm going to do, I'm sorry to do this, everybody, but it's like really important because everybody at some point is going to find themselves exposed to these things. So this is a capacitor. We're going to make it variable. This is an inductor. We're going to make it variable. Okay, so what is this thing called again?
Resistor.
A resistor. Okay, this is a capacitor. This is an inductor, L. For AC and DC, what is a resistor? Does it matter? Does it care?
No.
Whether it's AC or DC? No.
No, it resists both.
That's right. Okay, how about a capacitor? What happens if you charge this up to pluses and minuses? At some point, what will happen to it?
It'll stop flow.
You'll stop flow. You won't be able to put anything else into it, right? So for DC, this becomes an open circuit. Okay, but now let's make this capacitor, say it's all charged up, and now we hook it up. It was all charged up to pluses and minuses, but now we throw a battery across it that's minus, minus, and plus, plus. What's going to happen? The pluses are going to flow to the minuses are going to flow to the pluses, and then eventually what's going to happen? We're going to replace the pluses and the minuses and the pluses, and then it's going to charge up the other way. Right? Well, now we switch this back the other way. When the capacitor is all charged up, we switch it back the other way. The capacitor charges up this way, and then those turn minuses again. So what does it look like is happening as far as the battery is concerned?
If there's a battery, it's just becomes an open circuit.
Well, no, it doesn't, because is current flowing out of the battery?
No.
Well, it is. It keeps switching back and forth.
Alternate.
On a capacitor?
Yeah.
That's just straight connected to DC?
No, that's connected to AC.
Oh, I thought you said direct. Okay, yeah. You know, it starts rectifying.
Yeah, here. Well, actually, it's even more than that. So let's hook this up to a battery like this. We'll go plus and minus. Actually, let me just replace that with a circle so I don't have to keep redrawing it. Okay, so here, if I hook this up to plus and minus, what happens to this plate over here? Turns plus, and this one turns minus. And now I switch back on the power supply. and I make this the plus and this the minus. Well, now the pluses get called back home, the minuses get called back home. Eventually, this plate charges with minuses and this plate charges up with pluses. Well, then I switch it up again like that. And then everything gets called back home. And eventually this one charges up to plus and this one charges up to minus. So what's happening to the battery as far as the battery is concerned?
Charging and discharging.
Right. As far as it's concerned, there's a short circuit there. Okay, so now let's draw an inductor. What is an inductor? What is it physically built out of?
Coil of wire.
Coil of wire. What is a coil of wire? It's copper, right? It's just a piece of copper. Well, so for DC, what does a coil of wire do? Who cares, right? It's just a piece of wire. So that is a short circuit,
right?
For the most part. But now what I'm going to do is I'm going to make this AC. When it's flowing this way, I get a magnetic field that goes like this, let's say. But now I switch it up. And I just want to, it has to switch the direction of the magnetic field. Well, what do we know about energy?
Doesn't go anywhere.
Yeah, well, it can neither be created nor destroyed, right?
Right.
Well, I've got this field that's now built up in this coil, which has energy. And now the battery is saying, no, I want to go the other way. Nope, can't do it. Nope. Don't want to do that. So what ends up happening is that the only way to do that would be if this was an open circuit for AC. Because otherwise the energy would have nowhere to go. You'd create energy and not be able to move it anywhere. So what ends up happening is that notice these now operate completely opposite each other. Let's look at DC. A capacitor is an open circuit. And for DC, an inductor is a short circuit. And let's look at AC. The capacitor is a short circuit, and a DC, or an inductor, it's an open circuit. So they are opposite of each other. So we can actually use this to our advantage. As it actually turns out, this is in the extreme. And the reason that it's in the extreme is because the function of acting as an open or closed circuit is not complete. It's actually dependent on each component and its value. And we now have something called reactance or impedance. We're going to use reactance and impedance sort of interchangeably. So what ends up happening in this case is that impedance, notice to impede is similar to resist, right? Similar word?
Yep.
Okay, it's also measured in ohms. Impedance is something's ability to object to the flow of AC current specifically. For a resistor, resistors don't care. So impedance of a resistor would essentially be the same as its resistance. But we now know, looking at these things down below, capacitors and inductors actually do care. And this is actually, resistors are really quite boring. Inductors and capacitors are where the world becomes interesting, because XL is actually equal to 2 pi FL. And X is reactance. And XC is equal to 1 over 2 pi FC. So what do you notice is in each of those values? in the inductance value, what do we have? We have the L, which is actually the size of the inductor. And in the C, we have in the denominator a letter C, which means that this term is dependent on the value of the thing that we're doing. But what else is in there that's really important? Everybody see that letter F? What is that letter F?
Frequency.
Frequency. So it's actually frequency dependent. So not only is it dependent upon the thing that you're connecting and the size of it, it's also dependent on the frequency at which you're using it. So what that means is if I were to take this circuit and go with this and then this, and I had a C and an L, I had those two values, what would happen to XL plus XC when I changed the frequency? If I change the F value, what happens to those two values?
In one case, it goes up, or, well, they both change.
They both change. One goes up and the other goes down.
Right.
And in fact, adding those doesn't make any difference, really. There's no point to it. But I can do the Z, which is the impedance. And if I replace the X with a letter Z, here's where it really gets fun. This is a plus value, and this is a minus value. So if you pick a spot when they're equal and opposite, what will happen?
There'll be no impedance at all.
No impedance at all. That is known as resonance. So if I were to look at that and I change the frequency by a little bit, guess what happens to my overall impedance? Some points it's 0 and some points it's not 0, which means that it's going to present more of an impedance to the energy trying to get through it, depending on the frequency. So this is the basis for something called tuning. This is how we make a tuned circuit. This is what allows us to build a radio transmitter or receiver. This is what allows us to tune one device for another one. And if we go back to this very simple looking thing, okay, here we go. What do you see in here? What are the components that you now see?
Capacitors and the inductor.
And what do you notice about them?
They're
You
all
said
adjustable,
They're all adjustable. And why would you want to be able to do that?
because you just said that tuning is when is used by by capacitance and inductance.
Right.
By
So
adjusting
basically, by adjusting those values, you can change how the circuit behaves for different frequencies. And in fact, what you have is something that looks like this. So everybody see that picture? It's a beautiful photo. What we've got, that white thing all the way on the right-hand side, that's actually a transformer. And then the big silver plated thing in the middle, that's like a silver plated coil of wire. That is a variable inductor. And the two things with all the parallel plates, top and bottom, those are variable capacitors. And by rotating the knobs, that reduces or increases the amount of meshing between the two plates, which makes them more parallel. It changes the amount of area between them that are parallel to each other. And that's the definition of a capacitor. That's what a variable capacitor does. It changes the amount of meshed area that's parallel. And that is how we adjust something called our impedance of our system. And why is this important? Because we have in radio, most antennas have an impedance that is designed to be 50 ohms, resistive. Well, as it turns out, impedance is actually a lot more complex than that. And in fact, complex is the proper term for it, because something called complex impedance, ideally we want to dump our energy into a resistor. An antenna represents a resistor, but it can also have impedance. And this device is known as an antenna tuner, and it is designed to counteract the impedance in the antenna and make it purely resistive. So if your antenna is, let's say, 50 ohms resistive and plus 10 ohms well, I'd have to draw it on a graph to show you. But basically, if 50 plus J10, the J doesn't help you at all. This would allow you to generate -10 so that they add up to 0, so that you have a purely resistive system. Essentially tuning your circuit. Which of the following is a resonant or tuned circuit? That would be an inductor and capacitor connected in series or parallel to form a filter. When they're connected in series, it has a very low impedance. When they're connected in parallel, it has a very high impedance. The whole point of doing this is to generate a filter or a device that allows certain frequencies to pass while others to not pass. All right, so just about lunchtime. Finally, a relay. A relay is essentially an inductor or coil that pulls a contact in, allowing you to switch an isolated device on and off by just activating the coil. So that's known as a relay. A device that displays an electrical quantity as a numeric value, that would be a meter. A device that combines several semiconductors and other components into a package. They could be a billion transistors or one big transistor and a resistor. That's known as an integrated circuit. It's made as one circuit. Type of circuit that controls the amount of voltage from a power supply is known as a regulator, typically in the form of a Zener diode. And when connecting electronic assemblies together, we often use cables which are shielded, and that basically prevents signals from one wire passing to another. And notice we are now onto radio wave characteristics. This is a good time to take lunch, I think.
Great.
Anybody with any questions? I'm sure there were some, right?
Yeah. Yeah, I always have the same question.
Go ahead.
So just speaking for myself, I wanted to get into ham radio to be able to talk to people.
Yep.
And I guess all this is really critical to be able to talk to people.
On the exam.
Right.
What's
Well,
that?
the reason.
Wait.
Yep.
But what my point is this.
Yeah.
In the world that we live in, let's
Yep.
just call it the Amazon world we live in. We want to go online and buy an antenna and buy a radio.
Yep.
Plug it in a wall and go, come in Vietnam.
Yep.
But we can't do that, right?
Well, you can, but here's the reason. Ooh, excuse me. Here's the reason why it is more than that, because you're essentially, yes, you can go out and buy equipment to do that. And that's all well and good. But there are lots of other services that allow you to do that. What we are, one of the goals of ham radio is to have a group of people who are who are literate in how radio actually works, as opposed to just, screwing one thing into another and it works. Because there's lots of other ways, lots of other things you can do that with. We are basically given free reign. I mean, we're allowed to build our own stuff. That's in the rules. we're allowed and encouraged to actually build our own stuff. And in the act of building our own stuff, we also have to know how to not interfere with anybody else. So it's essentially being given the keys to a very, very expensive car, which can do 0 to 60 in 2.5 seconds. Just because you're not going to use it for that doesn't mean you can't, I guess is the point.
Okay.
And that's largely why, because, you know, even if you're only going to touch the surface, you know, you're potentially going to have the possibility of being able to do so.
Okay.
And actually, if everyone holds on just a second, I'm sending Kent. Hey, here we go. Okay, give me 1 second. The guy who's running our session tomorrow is about to sign in. Let's see if Kent's here. Hello, Kent. Come in, Kent. So yeah, I mean, I get asked that question a lot, and the answer is, you know, that there are, like, for instance, if you want to talk with somebody, you can go and spend $70 and build your and you know, build a repeater on GMRS and buy GMRS equipment, and it works just fine, you know, for operating in a local area. You pay the FCC your $70 for 5 years or whatever it is, and you're good to go. So the difference is that, you know, we can do we can do a lot of stuff. I mean, we can build an amplifier ourselves legally and transmit with 1500 watts of RF output to an antenna that provides 10 decibels of gain, which would give you 15,000 watts of power in one direction. Right? You can cause a lot of interference with that. You can actually hurt people with that. So
Okay.
okay, so Kent should be here any second. Sorry, I know it's lunchtime. He's in Alaska, so.
Hey, Scott.
Okay, you got your updated link.
Okay, I'll check it out. I'm doing a pre for another session right
Oh,
now.
okay. So how about after lunch?
Okay, see ya.
We're gonna do a half-hour lunch now. Okay.
Thanks.
All right. Well, there you go. So he's gonna drop in after lunch. He's setting up another session right now. So half hour for lunch.
See you in a half hour.
All right. Cool. Anyone with any questions? Hey, Pat,
Yes,
is this what you wanted?
absolutely.
Oh, good.
This goes beyond anything that I've had access to. And you know, I read a lot of books, but when you put it in place, like just the tuner, I've got one of those on my desk.
Mhm.
I've lifted it open to make sure it was clean because it was secondhand or third hand or whatever.
And getting getting a bug inside it literally will cause you a short circuit sometimes.
Right. And so you got to make sure things stay dust free, clean, you know, all that kind of stuff, but it makes you understand how it works. And, you know, just starting out, I only had a handheld.
Yep.
And to get into the local repeater, I built myself my very first antenna. And this is one of the reasons why you study some of this stuff. And I built myself a 2-meter quarter wave ground plane antenna. And it was very simple. And we stuck it, you know, the feed line down through some PVC pipe, stuck it on the front porch just to see if we could get out of the valley we're in. And boom, I was right in, and I could participate in the net meetings very quickly. And so I may understand some simple basics, but this takes it to the next level.
Well, you know, I'll tell you, here's, you know, what's funny. So I've had my license for what, 36 years. And about 7 years ago, the antenna that I built an antenna for my house,
Mhm.
and it's 19 inches of wire and an SO239 and
Yep.
four 19-inch pieces of wire hanging down from it. And I used a piece of PVC pipe and I ran the cable up through it and connected to it. And then I used electrical tape and waterproofing. And I put it up and supported it on my on one of the vent pipes on the house using electrical tape. I just went
Yep.
around and around with electrical tape and ran the cable down into my room, into the room. And so it's now
can-
been up for, like I said, it's been up for 7 years.
Yeah.
And it was supposed to be temporary, but funny how that
I've
happened.
got a really nice diamond now.
Yeah.
That actually it's a tri-band, but the thing about it is it and the cable's buried, so there's no issue with mowing the grass or whatever. But I'll tell you what, antennas are my addiction.
Yeah,
I want to
antennas are
build
great.
antennas like crazy.
So
Look at that.
yeah, we're at 950 feet,
Uh-huh.
and so we're at about 450 feet above the valley floor here.
Yep.
So that little quarter wave on the roof actually works remarkably well.
Elevation is everything. so-
Elevation is everything. Yeah.
So, I mean, this is just taking it to the next level, which I really appreciate. There's some of it I'm still lost in, but I'm going back to my basic electronics book and make sure that I understand it. My husband walked in and he was like, walked right back out. He's not a ham.
Not yet.
Well, the guys have been pushing him and I think he's dug his heels in. So
No, what for?
well, it's what I talked about in the email. Okay.
Yeah.
Let's just put it that way. And that there is a marginalization of women in this hobby, and in some places, not everywhere. But I don't find it in Canada as much as I do in this location. So
There aren't nearly as many hams in Canada either, but
actually, really,
yeah,
I
no,
thought
I
there-
don't think so. But
Really?
I know that like in our club, it's about 1/3 women.
That's awesome.
I know.
That's awesome. I'm the only woman in mine.
What? You got to work on that.
I have been trying to do so. So any of the women want to move to Michigan, let me know.
Yeah.
But this is great. And I think sometimes in understanding some of this stuff, I probably could let that magical smoke out of things.
Well, but see, that's the other thing. We're amateurs. It's designed to be a learning and training ground.
I think we learn a lot of this stuff too, to safely experiment.
Yeah.
And
that's a big part of it.
A lot of amateur radio is experimentation because they don't know the whole capacity of it because it continues to change and add on to. So,
well, have you guys done any mesh up there?
Any what?
Arden mesh?
Don't know what that is.
Ah.
Send me some info.
Here, I'll just here. Well, let me just put this up on the screen.
Okay.
So if you've ever heard of something called a ubiquity router.
Never heard of it.
Okay. Ubiquity is a commercially available router that, the 2.4 gigahertz and the 5.6 gigahertz band, we share with unlicensed services.
Mm-hmm.
The difference being that we are allowed to use our transmitters in ways that unlicensed services like Wi-Fi are not. So see these routers like here?
Mm-hmm. Mm-hmm.
Those are it's essentially a ubiquity router, UBIQUITI. And notice these high gain antennas and dishes and stuff like that. We basically can take a ubiquity router with a high gain antenna, put new firmware in it, and have it be part of an ad hoc network that, because we're able to put up as much gain as we want, you can have a 30 mile long microwave link.
Wow.
And Arden, basically the firmware is a self-healing network for data transmission. So you basically temporarily put one up from mountaintop to mountaintop, and you can set up a radio-based Wi-Fi network
Wow.
that can cover, like around here, because of all the mountaintops, we've got Portland linked to Salem, linked to Eugene, linked through the internet to the coast.
Do they have anything like this up in the Adirondack Mountains?
I don't know. Let's see.
That's interesting because I used to live up in the Adirondack Mountains. You couldn't get cell service. You couldn't get anything.
Yeah, I don't know. Let's see. Yep.
Wow. Oh my goodness.
Yeah. So that's when you say, the technology is continually changing. The technology is continually changing.
Yep.
And if there's something that exists that we can modify, which there's a lot of commercially available stuff like that.
Wow.
That's one of the things that makes it fun. And I still like Morse code best.
Well, that's, I also want to know the 4 different groups that you're connected with to do certification or testing. I know it's ARRL, but
Right.
what are the other ones?
Anchorage.
Anchorage?
That's actually who's going to do this. We're actually going to do the session here.
Okay.
And then W5YI.
W5. Y. Okay.
And Laurel or Lark, LARC. And I've been with W5YI since 1984.
Okay.
Or no, 86. 86. 87? 87.
Well, some of this stuff I've never heard of. And so
happens all the time.
And,
Happens to me all the time.
Well, some of the people think that they know everything, and it's good to just get out there and get involved. And yes, I'm an extra class license. Yes, I trained and I passed.
That just means that it's time for you. That just means it's time for you to learn.
It's time for me to really dig in because antennas are my thing.
Yeah.
So,
have you done any modeling?
Not really.
So we actually in our club we do some classes on using 4NEC2. Ever heard of it?
What? 4Net 2?
4NEC2.
Net. Nope, I've never heard of it. Huh.
It's free.
Oh, I love anything free.
I know.
4NEC2. The thing about it is I'm trying to develop high frequency antenna. And yeah, I know I'm 2 years into this. Okay. I get it. But there's something in me just poking me that I want to do my own type of high frequency antenna.
Okay. Let's see. Okay. I'm going to email you. Okay. Let's see.
And the thing about it is, when do I need a ball and when do I need this? When do I need that? And so that's why I'm starting at the basics.
Okay, you see this guy right here, Gary Hale.
Gary Hale.
He got his license in 2018, and he builds bicycles or has built bicycles for a living. But his thing is antennas.
Really?
So
Antennas, dude.
so am I on audio here?
Yes.
Yes.
So when I got to Eugene in 83, I built bicycles with Gary Hale I built 10 and foot powered short wheelbase recumbents and all sorts of weird crazy bikes for years.
Okay, hold on. Hey, Tom, you're a little muffled. Just so you know. There we go.
Yeah, that was one of the first. With Gary was one of the first jobs I had when I got to Eugene building bikes.
Yeah.
A long time in the 80s.
Yeah, Gary's awesome. He does some of everything.
Yeah.
And he says he doesn't do he does everything, but he doesn't really do anything well, I think he said. But we've got a couple of guys. They're both Gary actually, who are really, really prolific antenna builders here. And we've actually taught Zoom-based classes here on how to use Fornac 2 and how to do
Oh.
some basic modeling.
Wow. I would love to be a part of that.
Yeah. So, but yeah, feel free to send him a note. Tell him that I sent you. If you
Okay,
have
will
have
do.
any specific questions, his big thing is doing like collinear J poles for every band, and he has a 130-foot cedar tree in his yard,
Oh, really?
and so he'll just like, oh, I'm gonna put up another antenna, shoots a tennis ball up there, and drops another antenna. I keep telling him that he's got to be careful because, you know, his tree is going to start dropping antenna seeds and they're just going to sprout up from the ground. Because he's got this one tree and he's got like 12 antennas hanging out of it.
I just got myself a really nice tower, and it's not a TV tower. It's an antenna tower.
Like Roan 20,
And-
is it Roan 25 or something?
Yeah, it's a Ron
Roan.
ROHN.
Yeah.
And it's one of those ones that tips over.
Oh, you
It's
got
on
a tilt. You got a tilt over.
Yeah, and so that way, if there's any repairs, you know, I'm just not too keen on climbing and stuff like that. And
Yeah.
and I can, but I just prefer not to. And so I'm trying to decide on a really, really good high frequency antenna because my G5RV keeps coming down in the storms.
Mhm.
We got hit pretty hard this summer. I mean,
Yeah.
really hard. And I've not relaunched it. I'm waiting for the leaves to come down. It would be easier if the leaves were off to relaunch my, and I just use that dog, you know, chuck it thing
Yeah.
over the trees. But some of the trees I used came down in those storms. So I
Oh.
have to refigure. And, but I'm just, I'm trying to figure out something to put on that tower and understand its complete height, because it can't be in any distance if it comes down of any of the power lines around us. So,
Yeah.
you know what I'm saying? There's a lot
yeah.
of consideration. There's a lot of consideration.
How tall is the tower?
32 feet, I think.
Okay. And it's 25G with a tilt over.
Yep.
So you could, I mean, how much do you want to spend?
I don't care.
Do you have a rotator up there already?
No,
Okay.
this is like from scratch.
Okay, so you need a decent rotator and you need, so, I mean, you could look at like, you could look at like what is it, like an Omnibeam DP36 or
A what? What was
Um,
that?
there's like an Omnibeam, there's, it depends, like, a lot of people really like the, what is it, OptiBeam?
Opti?
I think that's, yeah, let's see. OptiBeam, that's, yeah, the only problem with the OptiBeam stuff, it's, okay, yeah, no, those are good. You have to be, like, there are some that are tunable. And those are a little harder to maintain. OptiBeams are good. Then there's always like your old standard TA33.
Okay.
That's going to be fairly, so that's a Mosley 3-element, I think, if you don't want anything too big.
I just want to make some really good contacts and. you
Okay,
know,
well,
the G-
can I tell you something? I live in Eugene, Oregon, which is in the Pacific Northwest, which is an RF hole, where people don't realize how far away from everything we are up here. And well, here's the other thing. Have you ever done any of this? Let me share this.
It's kind of like Plentyville, Montana, in the middle of nowhere.
Yeah, but you're not in the middle of nowhere. Have you ever used VoaCap?
No,
Oh my God.
what in the
Okay.
world?
Yeah. VoaCap.
Oh, a cap.
Yeah. So the Voice of America used to try to, figure out how to get their signals everywhere, obviously.
Uh-huh.
And so we'll go to like, we'll go to Columbus, Ohio. That's a good start. So let's say, okay, how do I get into Europe? Okay, let's
Wow.
see. here we go. We're gonna run CW. We're gonna run at 25 watts. Antennas. Here's the different antennas.
Oh my
And
goodness.
show me the prop wheel.
That's even more confusing.
Oh, no, it's not. This is
Oh,
awesome.
no.
This
Well,
is,
it's a good thing you live close by. I'll have to come and hound you.
yeah, but like,
This
so
is
you-
awesome.
I know. So you can see the best times of day, best bands to operate.
Yeah.
So
So
here's
in,
South
in
America.
the, at 2 o'clock in the morning when I wake up, because I can't sleep, you know, I could find out where I could actually reach at that time of night.
Yeah. So that'd be like,
Turn on my
so
radio.
that'd be 0900.
Mhm.
So at that hour,
Wow.
well, so this is an incredibly useful propagation tool. So let's see, 0900,
Especially with going into cycle 25.
yeah, 40 meters to Japan would be solid.
Hmm.
Australia probably. Yeah, 40 meters to Australia.
Wow.
South America, probably 40 meters also, but oh yeah, look at that hotspot during the day.
Hmm.
But yeah, this is an incredibly useful propagation tool. And then there's all this stuff at the bottom too.
I see that.
there's,
I'm anxious to get into it.
So can I tell you, I have never owned a tower or beam or I've never owned a tower, a beam or amp.
And you're in like basically the hole.
I moved here 20 years ago, 22 years ago. And so I spent, I was in Maryland before that. And so a good number of my DXCC stuff, well, I won't say a good number, but some of my DXCC stuff was from back east. But have you set up a logbook of the world account?
Yes, but I changed my call sign.
Mhm.
And
You
since
just have to
then,
have them merge it. You just have to have them merge it.
I've talked to some people there and they just, we've already sent you the key, you figure it out. You
Oh yeah,
know?
that's true.
And I'm like, really,
It's not too bad. It's not,
I can't get into it.
LOTW is a great thing. So
That's some of my hiccup is just being able to get onto Logbook of the World, and log these things.
mhm.
Plus I use a different program that can link into Logbook of the World that actually brings up a whole lot of information. If I can find it here, amateur contact log. Should be right here on my desktop. I'm looking for it.
So notice
Yeah,
here,
N3FUP,
FJP,
FKP.
no, FJP, Fox Juliet Papa. Yeah.
Yep, you're right. And some of my contacts are in there, but I haven't synced it with Logbook of the World because I can't get into Logbook of the World.
Mhm.
So,
Well, somebody will fix you up. Yeah,
yeah,
I think, but like here's, you'll notice the gaping holes in my DXCC,
oh, you'll get there.
but
You-
I'm actually at 260.
Are
So,
ya?
yeah.
Well, that's good.
Yeah, and I mean, look, so 221 on CW, it's actually probably 225 after all said and done.
Yep.
So,
It takes a while sometimes for
it well,
people
but
to
see,
confirm.
yeah, but you know what? That's okay. There's,
Yep.
you know, I mean, some people just want it now. I've been at this for 36 years.
Well, you know, that's where, you know, this Google, Amazon world,
Instant
know,
gratification.
yeah, we have to step back from that because every once in a while I go to my mailbox out front and I find a card from one of the contacts.
Yeah.
And it could be 6 months, a year ago, you know, and you know,
LOTW helps that a lot.
yeah, and I can get back online and, you know, say hey to them and
Well,
try to seek them out again.
here's the one that's been the thorn in my side for 3 years now. Notice I've got 50, 50, 50, 50, 50, 50, 50,
Yep.
46 on 12 meters. That's other than 160. That's the only one that I'm missing.
Wow.
I've been working really hard at it. 12 meters just with crappy sunspot numbers has not come up anytime recently.
Well, maybe you'll catch a gray line.
No,
Get it done.
the sunspot number will come back.
Well,
12
it
meters.
is, I know with our repeater, local repeater, some nights when I'm running the net, it just sounds like a wind tunnel. Cause it's just wide open.
Yeah, but that's not an HF thing.
No, it isn't, but
HF is going to be completely beholden to the sunspots. So,
Ah.
but you've either got a little E-skip or tropo. Probably.
well, that's, I'm not the trustee of the repeaters, so.
Well, I mean, you can't do
know.
anything about it,
No, there isn't. And we just kind of have to wade through it. Even still, it's very distracting as NCS though, to try to keep on track when you just hear a wind tunnel.
Yeah.
But
All right, I'm gonna go refill my coffee.
I need to go get some iced tea. I was gonna go down the road and get a pumpkin, but I don't have time. So
Oh, okay. All right.
hopefully my husband will.
I'm curious, who's ocean meat, Balaenoptera? I can't see. Musculus. Hi, Kent.
Hey, Scott.
How goes
How
it
are
up
you?
there?
It's going okay. Going okay. Just getting ready for some exam sessions here this afternoon, and yeah, you got a herd here. I see a
Well,
nice big grid of folks.
You know what's interesting? This always happens. That it's impossible for me to plan anything schedule wise with regard to a class, because I can show you how big this roster was.
Well, we could talk. I got some ideas for you.
Well, yeah, I know. I mean, I don't even mind, because actually this is the perfect size.
Yeah.
It's just so. But I was up to 51 people, and the actual attendance is like 20 something, but that's fine.
Yeah.
It's just like, well, I mean, people have things that come up and people have to
Yeah.
work, and
Yeah.
I don't mind.
Okay, well, you've got a good group of folks here, and I'm looking at the exam roster, and I've got looks like we've got 10 people registered to test,
Okay.
so we can handle that no problem. I
Let's,
do.
let's make sure everybody's back. Is everybody back?
Let's see.
By the way, Kent.
I'm back.
Oh,
Yeah.
Good. Hey, Kent. Hey, hey, Pat. Unmute yourself for a minute.
Yes.
So this is Kent. He's
Hi,
KL
Ken.
KL5T.
Pat.
What was the call sign again?
I'll fix it. It's Kilo Lima 5 Tango.
Perfect.
And he is because you said you were accredited with ARRL, right?
Yes.
And so Kent, are we now like 100% remote exams?
Right now, yeah, we're not doing any in-person exams right now. For COVID and liability, we're worried about that
Yeah.
stuff. Yeah.
So
Yeah, 100% remote. So we test every day, twice a day. Well, not every day, Monday through Saturday. We usually take Sundays off, except for Scott's special sessions
Sorry.
here.
Yeah. So
That's awesome.
Pat, if you're interested in getting accredited, this
I
is
am.
this is the guy to talk to. By the way, Pat is well, I'll let you give the story, Pat.
I'm extra class license, call sign AA8J. You can look me up on QRZ.
Yeah.
I've been an amateur radio operator for 2 years. Really got started back when I was a teenager. My brother had the whole old fashioned setup of CW and N-Fed antenna and such. And that's all he did was CW. And so after going through a cert class and stuff at law, emergency radio is really important to service the community as well as a hobby. So I did everything in a year, and from technician to VEC, I did it within a year. And so, my intention is to continue. I have a passion for antennas.
Good for you. Well, it's all about black magic. Good stuff. Actually, it's about good science, but we do some, that's great news. And we do some serious antenna modeling here at the Radio Science and Operations Center. And we use some pretty sophisticated software to do that. And we've got one guy who's a bloody expert at it. So you might be interested to meet TJ, KL7TS. But Pat, I sent you a chat with the link as to how
Perfect.
to become a VE with us. You can just read that page and scroll on down to the bottom and apply.
Okay.
And then I will send you a link to take our little examination.
Okay.
And it's there's about 100 questions in the question bank. There's 30 questions that will be rendered, and It's open book, obviously, but you might find it easy. Some people don't find it so easy, but you'll do fine. So we're happy to have you aboard. Okay.
Thank you so much.
No, thank you. Scott.
Yes.
So you wanted me to come talk about exams tomorrow. So we have 10 people registered. Is Mr. Boyles here today? Mr. Boyles, William, I don't see him.
I don't think
And
so.
maybe Sonja. Is Sonja on?
Sonia?
Sonia?
She's
Yeah, I'm
on.
here.
Okay, Sonia. Hey, you should have received an email today from me. It says, hey, go do something else. So please do that. You got to do your, there's one more step you need to do, okay? So check that email. It tells you what, how to handle it, okay?
Okay.
Wonderful. So tomorrow, I guess you're gonna finish at about
12:30.
yeah, your time, and then so we'll start testing at about 1 o'clock. If you want to test, you'll need to go register. Scott, I'm sure you've shared that information with the folks. I won't bore them with resending it there. I'll let you handle that when it's convenient for you. And so if you do register for testing, there's actually 3 things you have to do. You register on the examination platform, you have to pay for your session, and then you have to complete what we have. It's an examination agreement form, just to say, I understand I'm going to do this stuff and it's going to be remote and blah, blah, blah. So it's pretty straightforward. Okay. So when you're taking your exam, nobody can come into the room with you. So you want to let everybody know who might be in the house, hey, don't come in here, bar the doors, keep the kiddies out, all of that kind of stuff, because somebody comes in, we'll have to stop the exam and get all reset and then start a new exam, which would suck if you had 34 questions answered, right? So yeah, I've only ever had to do that one time, but the guy passed. It was wonderful, and he was all happy. When you're taking your exam, no smartwatches, no earbuds, no headsets, none of that stuff. You can use a calculator, but it needs to be a simple handheld calculator. You can't use a calculator on your computer, okay? You could use a sheet of scratch paper. We prefer just one sheet, and just hold it up to the camera for us, and don't worry. Make sure you've got your government issued photo ID. We'll need to see that. We do record the sessions, so you know that as well. And let's see. And we do use 2 cameras. So usually we use your primary device would be the one you're taking your examination on, just like you're doing right now. And then we'll have you bring your second device in. Most people use their cell phone. They might use a laptop computer, but bottom line is we have you do a sweep around the room so we could see the entire room with, and then ultimately we'll get you to position that camera. So we sort of get a side view that gives us a good look at the computer you're taking the examination on. We want to see that whole screen. Your keyboard, mouse, desktop, and just a little bit of you, okay? And then we'll do the exam, and it's pretty easy.
So you're gonna call people to get them in order?
Yeah, we'll call you. So yeah, we've got the phone numbers that you provided us. So be ready for a phone call, and we'll just start bringing you in, getting you prepped up and stacked up and ready to test. I don't know how many VEs we'll have tomorrow. We need 3 VEs to give an exam. Let me see how we're looking so far. Yeah, we're going to have a pretty good pile of VEs, so we'll get through. We'll get through everybody pretty quickly.
I'm still trying to get Hannah to do it. She's got some homework, but I think she could probably, unless they go somewhere. So for all of you who don't know, I'm referring to my daughter, who's an extra also. She's 19.
What kind of internet speeds do you need to be able to accommodate both computers during this?
If you're doing this Zoom and it's working okay, you're going to be just fine.
Okay.
Yeah, we really have rarely had problems with that. We've always been able to figure out a solution.
Okay.
I mean, we've literally done thousands of these, so it works pretty good. We're pretty good at doing it, so don't worry. If there's any issues, we'll walk you right through it. But we'll bring you in, and we're going to put you off into a room to get you all set up technically to make sure you're good to go. And then you just sort of stand by there, and then the VE is going to come over, and we'll grab you and pull you off into another breakout room and give you your exam, okay?
So are they apt to be done in parallel, or is it going to be more like one one or, one group goes and then another group goes?
Well, we'll be running several breakout rooms. So if I've got 18 VEs, I can run 6 breakout rooms, so I can,
But you won't
everybody runs in
necessarily start
parallel.
everybody at 1 o'clock.
No,
No, we don't have
About
enough
how
people to
long,
do that.
about how long does the test take?
that's a function of you. Some people take this test in 8 minutes.
I've
Some
seen
people-
6, I've seen 7.
Some people take 45 minutes. Some people take over an hour. Usually, on average, most people take 15, 20 minutes.
Okay.
How many questions on the test?
35. That's a test question.
How similar are they to the one that's with the icon group?
Okay, so let me answer the question this way. Scott should be sharing this with you. The question
haven't yet.
pool, yeah, the question pool is in the public domain. Every examination, the questions on the examination are pulled from that question bank. So every examination that we generate is unique. There are no 2 exams that are the same. But there are 35 subject areas on the exam, and each area has about 9 to 14 questions in that sort of part of the pool. So one of those questions for each area will be pulled to build the examination of 35 questions.
So if everybody can see this, hamstudy.org, this is the same site, but this is the non-official portion of it that we use to give exams. So if you've taken practice exams on hamstudy.org, it will look very, 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 very familiar to you.
Good.
Kent, would you agree with that?
Yeah, you should be very comfortable with it. It's very straightforward. When the exam is rendered to you, it's basically presented as 35 questions in one long web page. Okay, and you can answer the questions by selecting the right answer with your mouse or glide pad. And if you do that, you'll probably have to scroll to the next question. Alternatively, you can answer the questions by pressing the A, B, C, or D keys, and that will typically jump you then to the next question. When you're taking the exam, you can skip questions, you can review, you can go back and change answers.
But you can't get up and go to the bathroom.
No, you can't. So make sure you're squared up. If you do skip a question, it'll show up in the upper left corner of your screen in a little yellow or orange circle with the question number in it. And you can actually click on that. It'll jump you right to the question you missed. Once you've answered all the questions, at the very end below question number 35, there's a button to click that says grade me now or grade exam. And once you click that, that's the end of the show. And then we're going to get you your results real quickly. Okay. And
The other
when you
cool,
pass,
sorry, go ahead, Ken.
and so when you pass, it's Sunday, we will be submitting to the FCC, and they don't issue call signs on the weekends, but they will issue your call signs. If everything's running like it's supposed to be, you'll have your call signs tomorrow morning around 8 o'clock Eastern time.
Yeah.
Yeah, Monday morning.
Wow.
Yeah.
Wow.
Will we know which questions we got right and which ones we got wrong?
We'll share that with you if you want to know.
Yeah.
That's one of the advantages of doing these things remotely. The fact that or doing them electronically with this VEC, the fact that, we don't have to mail anything in. It gets submitted immediately.
We're a pretty small organization. From bottom to top, it's like one layer, one level. So we're pretty small and we're very, very agile. And we don't mess around. We submit really quickly to the FCC. It doesn't take a week.
I have a question. My daughter's only 11. She doesn't have a ID issued to her yet. How does she go about taking the test?
Yeah, well, she probably has a birth certificate or something like that. We have instructions for minors. Typically, the parent has to be involved, and if there's not, usually what we require is 2 forms of non-photo ID from the individual or an affidavit from the parents saying this is who this child is. But we do demand parental involvement because we're talking about minors here, even though we're remote, yeah. So we're sensitive to that. But we're happy to test. We're happy to test kids. Absolutely. We just need to, we have to do our due diligence so to make sure who we're testing is who it actually is. So
My husband ran to do errands and he's not here right now. He's the one with his ham radio license. So we're trying to catch up to him.
Good for you.
That's Tony.
Okay.
So
Any other-
on that note of testing kids, like if they're, so my son's 12, can I be here with him while he's getting himself set up and then step out of the room?
That's exactly what we do. Yeah. We ask that you step out of the room while the exam is going on. And then as soon as they're done, you're welcome to come on back into the room.
Okay, so then like I can help make sure he's got his camera set up and all that stuff is good, and then, okay,
Yeah, and actually, we're gonna ask that you present your ID to us as well
okay,
as the parent. You see what I'm saying? So yeah,
Yeah.
you have to be there. All right?
okay.
Wonderful.
I have a question. Are programs on a computer to read to you allowed to be used? Because I have dyslexia and I find that in tests it like acts up
No.
so bad. So I was just wondering if that's something that's available. Otherwise, I'll take forever.
No. Okay, so if you have a condition, so we're obligated. So what the Part 97 says that we have to accommodate folks with physical disabilities or some sort of physical thing. But we can require a medical professional's certification of that. So now, typically, what we deal with there is folks with visual impairments.
Okay.
So when that happens, then what we do is we read the questions. One of the volunteer examiners reads the questions to the examinee. We have someone read that does it properly, if you know what I mean. But we won't allow any sort of application that reads the question because we found that oftentimes it's not going to do a very good job at reading it in a way that makes sense. So if you have something like that.
I'm sorry, I'm also Lauren's mom, and she is a college student at community college, and she does have accommodations. She's getting accessibility there. Is that a thing that will be like, can she ask for that? That would definitely be a benefit for her.
I think you just did.
Okay, all right.
What do you think?
So we just give me some sort of documentation that we can put in the file. Okay.
Okay.
Yep, and that's not a problem.
Cool.
And on our website, when you register, we do ask a question about. We ask if you need to be accommodated or if there needs to be some sort of accommodation. And if you answer yes, it tells you, hey, you need to send an email and it gives you the email address with some, supporting documentation. And we're happy to do it. Okay.
Okay.
Okay. Any other questions?
Yeah,
So if-
I am getting through on my hotspot on my phone, and so I don't think I'm gonna have two sources of video.
Have to have two sources of video. Do you have a laptop computer?
On my laptop now.
Okay, well, you can also come in on your phone.
Yeah, the phone will still work.
Yeah, it'll be
Will it?
fine.
Okay.
Don't worry, we'll work it out one way or the other, but we do have to have two video speeds. But I'm sure, trust me, like I said, we've done thousands of these and every possible combination, so I think you'll be fine. Yeah. Any other questions?
By the way, Kent, you might be interested to know that you remember Joel? Probably not. Well, anyway, he was the examinee when I first met you guys. I was I was his moderator on site.
Oh, you were the proctor.
I was the
You were the
proctor.
Oh,
Yeah,
okay.
he's got his extra.
Oh, excellent.
He's kicking butt.
Very good. Very good. All right. Any other questions? Does anybody else need to register who wants to test tomorrow? And you don't have to test tomorrow. You can test anytime. You can go under our website and pick another day and time. Give you a chance to take practice exams and make sure you're in a position where you're actually passing before you go wasting your time on the real deal. Okay. Because on hamstudy.org, you can take practice exams to your heart's content.
And I strongly recommend doing practice exams.
Yeah. And we even ask, when you register, we ask you, hey, have you been taking practice exams and like consistently passing it about with at least like 85%? Because you need a 74% to pass, okay?
Which is 26 out of 35.
Yeah, if you're scoring 85s all the time, life's gonna be good. You know, some people get a little nervous when they take the real exam, so, you know, so that's why we say about 85, you're gonna be good. All right? And, you know, if you haven't taken any practice exams,
You got
take some
tonight.
today. Yeah,
Yeah.
take some today, take some tonight, see how you're doing. And look, if you're scoring, if you've already registered and like you're not, and you registered the test tomorrow and you take some practice exams and you say, man, I'm only scoring like 60, 65 on every exam I take. Well, just let us know. We'll reschedule you. It's not a problem. We'll delay it. You're good to go. You don't have to pay again or anything like that. We'll just reschedule you. Okay.
Cool.
Thank you for clarifying on that. That's a good thing to keep in mind.
Sure. Yeah, listen, just keep this in mind, everybody. We are all on your team today. We want you all to pass, very much so. We just have to, we do have to dot our I's and cross our T's and do it all right, but we want you to pass. So we're rooting for you, okay? We really are. I mean, there's a lot of cheering that goes on when people pass their exams. We're happy for you because you're joining a great fraternity. This is a lifelong endeavor and you'll meet some amazing people in this field. Amazing people. Okay. Anything else? Okay. I'll probably stop in and visit you tomorrow before your class is done. Okay.
Okay, cool. Good luck on the afternoon exam, Kent.
Yeah. Thank you, everybody.
All right.
Take care. Bye-bye.
See you, Kent.
Bye. Whoops, somebody chatted me here. Let's see.
Oh,
no problem. I got the, we're good to go. I'll see you guys later. Bye-bye.
okay. Thanks, Kent. All right. So we are on page 27. And that is properties of radio waves and propagation modes. And before we shift to that, is there anybody with any other questions? Okay, I don't hear anything. Let's start. Here we go. All right. So does everybody remember what the frequency range is for HF in megahertz?
3 to 30.
3 to 30. Okay, how about VHF?
30 to 300.
30 to 300. UHF?
300 to 3,000.
300 to 3,000. Okay. Good to remember. Very important. Okay. So we're starting talking about VHF and UHF being line of sight. What is line of sight? That means that literally your eye can see the eyeball of another person. That would be line of sight. Now, it is also true that line of sight communications are typically direct line of sight in that if you can't see each other, you can't work each other. UHF signals, VHF signals are rarely heard from outside your local coverage area, especially on UHF, because in order to go beyond, they would have to be reflected by the ionosphere. We are going to get to that in a minute, but essentially what we have around the Earth is, so here's our planet, and here's levels of the atmosphere above the surface of the planet. And now I'm going to draw this big yellow ball in the sky. Anyone have any idea what that big yellow ball in the sky is?
Sunflower.
That would be sunflower
Antenna.
or a sun. Or if you watch Teletubbies, there's a weird looking baby in it. So anybody know what I'm talking about? Having suffered through Teletubbies?
No.
No? Okay. It's a strange British children's show. Anyway, so what happens is that the sun is perpetually putting out streams of light and particles and UV and X-rays and all other kinds of stuff. There you go. Thank you, Hannah. So what happens is that all these light rays and charged particles and UV rays and infrared and basically the whole electromagnetic spectrum. The sun also puts out a good amount of radio, which thankfully doesn't really affect too much of what we do, but it does generate a little background noise. Anyway, we are very lucky that we are surrounded by this thing called our atmosphere, because our atmosphere contains mostly diatomic molecules of nitrogen and oxygen and other. All right, so all this stuff is floating around in our atmosphere. Our atmosphere is 78% nitrogen and 21% oxygen. So that constitutes 99% of the atmosphere. Fortunately, as these molecules are floating around, they also, once in a while, tend to get struck by a photon, which is a packet of energy that comes out of the sun in the form of light or ultraviolet or X-rays or infrared. Typically, it's the X-rays and the ultraviolet that are the most energetic. You'll also note that on that frequency spectrum thing that we did, those are the ones furthest to the right with the highest frequency. High frequency is, it turns out, is actually proportional to energy. So high frequency is very high energy, which is why X-rays can go through your skin and go through your bones, whereas radio waves, they can pass through you, but they don't cause any damage or anything like that. So what ends up happening is that as our atmosphere is made of these particles or these molecules of nitrogen and oxygen, largely photons and energetic particles that are coming out of the sun, we'll just call them electrons, will occasionally strike one of these molecules and cause it to become ionized. And the way that happens is they rip an electron off of it. So you basically end up with a nitrogen ion or an oxygen ion and an electron floating around. So as these are floating around, what you end up with is once in a while, these things will recombine and turn back into a happy atom or a happy molecule. But during the day, you have more energy coming off the sun, which causes this to happen. And this basically ends up in a state of equilibrium where you essentially have a continual process of forming ions and electrons and then things recombining. So what do you think happens at night? Directly overhead. What happens at night?
With regards to what?
What happens to that equilibrium?
There's less.
There's considerably less. So what we end up with is a very distinct pattern during the day of high ionization, and at night, very diminishing ionization. Eventually, you'll still end up with some of those electrons and ions floating around, but there won't be as many. So what happens is during the day, you get high ionization, and at night, you get low ionization. And if we were to draw this, so here's the Earth, and we're going to put the atmosphere around it, you would end up with high ionization over here and low ionization on this side. And so the peak of your ionization is going to be anytime during the day, but it's going to really peak right around lunchtime, right around direct high noon. And so what will continually happen as the Earth rotates is that you will, because the atmosphere is rotating with it, you'll end up with conditions that change from high ionization to low ionization. Well, as it turns out, the greater the level of ionization up there in the atmosphere, the greater the chance that frequencies up or on the HF bands will be able to come up here and refract or reflect back down. What will happen at night is that that same frequency will come up and it won't find enough ionization to hit anything, and it will just pass right on through. Similarly, a different frequency during the day will come up to here and just become absorbed by the lower levels of lower levels of the atmosphere. At night, that particular frequency might hit and bounce back down. So you get very distinctly different patterns between the day and night. During the day, you will get 10, 15, and 20 meters that tend to be really quite good. And at night, what you'll end up with is 30, 40, 80, and 160 meters, which are much longer wavelengths. The main reason this occurs is that your ionosphere, which is, it starts at about 50 miles up, consists of the D layer, the E layer, F1, and F2 as you go up in altitude. The D layer forms during the day, during sunny times, and what it does is it forms a heavily ionized layer at low altitude, 50 miles up, which tends to absorb everything up to about 7 megahertz. Has anyone ever listened to AM radio in the car? Have
Only
you ever
when you can't
noticed?
get something else.
Yeah, right. But have you ever noticed that at night you tend to pick up stations from far away,
Right,
and during the day you can't?
right.
That is the D layer. That is specifically because the D layer, because AM radio is at 1.5 megahertz, which has a wavelength of about 200 meters. Those frequencies are absorbed by that lowest level of the atmosphere during the daytime. At night, that layer quickly dissipates, and all of a sudden, it's wide open for those frequencies. The E layer tends to form during the day. It can stick around a little bit toward the night. And to be totally honest, it doesn't really do a whole lot for us, except that the E layer, once in a while, can build up so heavily that it tends to refract VHF frequencies, believe it or not, and give us propagation that can cover 1,000 miles on 6 meter band and the 2 meter band, both of which you have access to as technician operators. The F1 and F2 layers are essentially the layers that build up the most during the day and then start to fade out at night. And those layers way up here, which are between 200, let's say 250 to 500 miles up, where the air is really thin, those are mostly responsible for our long distance communications, our single hop from the US, for instance, from me to Colorado, Oregon to Colorado, double hop from Oregon to the East Coast, triple hop from the West Coast to Europe, sometimes even more than that, if they line up properly. The furthest I've ever done from here is from Oregon to the Indian Ocean, which was, as I figured, either 6 or 7 bounces. So it's like 6 bounces off the ionosphere and 7 bounces off the ionosphere. No, it would be 6 and 7 bounces off the ionosphere and 6 bounces off the ocean. So only ever experienced it once. But anyway, that is why we have signals that behave in this way. They change from day to night, and they also change from season to season because the Earth is tipped. And the northern hemisphere in our summertime gets more ionization, so the entire North Pole stays lit up all night and it stays ionized. So we typically have a decent higher frequency path to Europe, for instance.
I have a question.
Yeah.
Dealing with the atmospheres and all that, have we noticed any effect with the Starlink satellites being the low Earth orbit atmospheres that we?
No.
Okay, I didn't know if it would affect us or what.
No, there's so many satellites up there that it's all minimal. Now, I will say, in addition to that, there are also multiple other satellites that are amateur satellites, which are typically low Earth orbit, about 200 miles in altitude. And for for instance, like the International Space Station. That is a low Earth orbit satellite. And actually there's a crossband repeater on the ISS, which with a very modest antenna, like a quarter wave on the roof of my car, running 10 watts, you can actually work through that because it's line of sight. It's kind of amazing. You can hit it with, a couple of watts. And I was able to driving up to Seattle, 10 watts on the uplink and listening to the downlink on a handheld radio inside my car. Okay, so why are UHF signals rarely heard from stations outside your area? Notice that UHF did not come into this equation at all. And that is because UHF signals are not usually reflected by the ionosphere. Now, as far as on the surface of the Earth, this thing called line of sight, there's something called the radio horizon. It's the longer the wavelength is, the longer the horizon is. So visible horizon might be a certain, let's say 20 miles. The radio horizon would be about 10 to 15% further than that. So basically, because radio waves are bigger than light waves, the Earth seems a little less curved proportionally. So the radio horizon is a little bit further.
So when you say line of sight,
yep,
it's not a literal thing, is it?
Actually, it really is.
So then when you're talking about the radio horizon being further, that it can travel further than the horizon, your whatever it is, 20 some odd miles or however many miles it is,
Yeah,
or whatever. But you can communicate significantly farther than that, right? But not if you're like on a mountain or in a valley or.
Oh yeah. If you're on a mountain, I mean, line of sight from, that's why repeaters are put on top of buildings and on top of mountaintops. We've like our club's repeater is at 3,500 feet altitude, and it's on one of the highest peaks in the mountain range on the coast. And it has line of sight coverage to, 50 miles into the ocean, and 60 miles to the north and 60 miles to the south and 70 miles to the east. And if you're up in the Cascades on a hilltop, you can have a conversation through our repeater with somebody who's, is able to talk through the repeater, and you might be 125 miles away running 1 watt because it's line of sight. I mean, it is quite literally line of sight.
So does that mean that you're in a valley or SOL?
No, it depends where the repeater is. That's why people put repeaters on mountaintops.
But you can still be in the shadow of the tower of your repeater with the terrain.
Oh yeah.
And
I mean, yes, you can be. It is possible if there's another hill to be shielded by that hill.
And it's also possible that just because you can't see the repeater due to foliage or something like that, a radio signal is transparent to that, so you can get through it even if you couldn't see it. It's
right. And it's also, I mean, because it's line of sight, radio waves tend to bounce off of things too. So we had a guy who does a lot of backcountry hiking, and he was running just like a J pole hung up in the tree, running about 5 watts with his handheld radio. And he was up around Mount Hood. And there was another mountain to the south of him, which should have been blocking his access to our repeater, which was 100 miles away. Except for some reason it wasn't. And if he moved a little bit, his signal went away. So it can only be assumed that his path was his signal was bouncing off of Mount Hood to the north and being redirected to the south. Because why not? Does that answer the question, kind of?
Yeah, that's fine.
Okay. One problem often encountered, let's see, we're on page, at the bottom of page 26. One problem often encountered when using VHF and UHF, which are line of sight, is multipath distortion. So multipath is quite literally that. It is multiple paths, and it looks like this. So let's say that there's a building here. Your signal goes two different ways. Sometimes it might even go more than two different ways. And if we were to draw our wavelength, let's say we're on the 2 meter band. What would the wavelength be approximately on the 2 meter band? Not a trick question.
150?
150, yeah.
No, what's the wavelength on the 2 meter band?
Oh, 2 meters.
2 meters, exactly. So let's say that this right here is a certain number of wavelengths. It doesn't even matter what the wavelength is. But let's say that this other path is, we'll call this X, and this is X plus 1 meter.
That's fine.
So what would happen is your signal would go like this. This is your first signal. Your second signal, because it's 1 meter extra path length, would actually have to do this. It would be delayed by a half a wave.
That's a half.
Right. It would be delayed by
No,
a half of a wavelength. What is the sum of those two things?
zero.
That would be 0. That would be called destructive interference.
But that's not going to be X plus 1. That's going to be X plus a half.
Well, no, it's X
Or
plus, it's
1
X
and a
plus,
half.
it's X plus 1 meter.
Why wouldn't 1 meter just give you a sync up to the same wavelength, but just a little bit of just,
Because this whole thing is 2 meters.
oh, 2 meters. Okay, right.
So I
Sorry.
shifted it. I
Right,
shifted it by
right,
1
okay.
meter.
Gotcha. Sorry, I'm being stupid.
Okay, so that would be destructive interference. So being that if these were light waves, we'd be talking about, instead of 2 meters, we'd be talking about, let's say let's say 400 nanometers, right? This would not be an issue, right? This is something that becomes, a part of scientific experimentation, but we're dealing with real world stuff here. We're dealing with 2 meters. So how do you fix this? Well,
Telescope mirrors are real world too.
yeah, exactly. So what we're doing here is we're now taking this path length and we have a couple of options. Well, if you walk over this way, let's say a meter, your new path has been shortened potentially by about a meter. This one's about the same. So now it's no longer X plus 1. It's just, let's say, X plus something. And now instead of being in a destructive interference area, they now sync up, and now this is constructive, which means they're additive, which means now your signal goes from bad down here to good. And all you did was move how far? About 3 feet. And that is totally true. You can hear that by listening to the radio. If you know what band you're on, you move across the room. And as you move across the room, you might go from an area of good interference, or a good signal to bad signals, good signal to bad signal, back and forth as you walk across the room. So how do you fix that? You just stand in a good spot and hope that the thing that's reflecting your signal right here is not a truck that's parked that is then moved, in which case your good signal then becomes a bad signal area potentially. If you're, let's see, how do you, if you're using digital communications, if you're using voice, you'll basically get all scratchy and distorted. If you're using digital communications, computer to computer, you'll notice that your error rate increases for the very same reason. Okay, so you can actually use this to your advantage. Let us say that this path doesn't work at all because there's something in the way. You know that there's a building down here and you intentionally reflect your signal off of it. That can work also. If you have a directional antenna which points this way, you can direct your signal to something and intentionally reflect it off of it. That's very useful in urban environments. There's also something that is a physics thing that we have called the single slit diffraction effect, which is that a wave coming through here as it passes through a slit tends to be affected by those edges and form areas of constructive and destructive interference. Notice that if this is a mountaintop, some of this signal that's coming in like this will actually go down. And this is called, in the real world, this is called knife edge diffraction. So that a hilltop can actually diffract signals back down over the opposite side, even though you don't have line of sight. As you're driving in a car, you may notice as you're driving that you pass through areas of good and bad signal strength. And it will sound like this as you're driving. It'll get weak and strong and weak and strong and weak and strong. And that's known as picket fencing because it sounds as though you're actually trying to talk to somebody as you're moving along through a picket fence. Another condition that can impede the transmission of VHF and UHF is vegetation. Vegetation, leaves have a lot of water. They're also flat surfaces. Flat surfaces can reflect energy, even leaves. For the most part, it does pass through, but you're typically going to find that your signal strengths are better in the winter than they are in the summer for that very reason. On certain frequencies, that is a really big problem. On the 2.4 gigahertz band, vegetation is an absolute killer. In addition, not only is vegetation a killer, but fog and rain are a killer. And I'm guessing that somebody knows why. Okay, well, okay. So now we're going to get into something called the microwave oven to explain why. So a microwave oven is a radio transmitter in a box that releases energy at 2.4 gigahertz into a box where your food is. Okay, why does your food heat up?
You hit the resonant frequency.
That's right. This is your resonant frequency of water. So all that energy vibrates the heck out of your water molecules in your food. And what happens is that if you happen to be using the 2.4 gigahertz amateur band, which is a ham band along with Wi-Fi, what happens is that if you have a lot of trees have water in the leaves and it tends to absorb those frequencies. So that's why microwaves typically are very, very subject. The microwave frequencies are typically very susceptible to attenuation by vegetation. Okay, next, we were talking about this before. So we're going to draw a wire. It's a nice blue insulated wire. Okay, so current moves back and forth in this wire. The electric field is parallel to the direction of the wire. So this wire would be horizontally polarized because the E field or electric field is horizontal and parallel to the ground. How about this right here? If this were my wire, my E field would be up and down or vertically polarized. So in actuality, it goes like this, back and forth and back and forth. In this case, it goes up and down and up and down. So let's see what happens if I take an antenna that is transmitting a horizontally polarized signal and I try to receive it using a vertically polarized antenna.
They intersect at a point.
Yeah, it's a point. They don't, there's virtually no energy that is induced in the second antenna. So typically, if you think about it, if you have two parallel wires, one will induce energy in the other. If you have an angle between them, it will be reduced by the sine of the angle. That'll be the overall. Or is it the cosine? Sorry, cosine. So if it's 0, you have 100%, you have 100% signal retention. If it's 90 degrees, cosine of 90 is 0. They basically don't see each other at all, which is why it's very important to make sure that you have the right polarization. So let's take a look at the antenna on a car. Would this antenna be vertically or horizontally polarized? Remembering that it goes in the same direction as the wire itself. It'll be vertically polarized. Okay, so why is that so great? Because viewed from above, I'm looking down on the car. Is there any direction, for the most part, that is really favored over any other direction?
No.
No. This is what's known as an essentially omnidirectional antenna, because it doesn't have any preference as to transmitting in any one direction or another. So the other thing is, looking at it from the vertical, looking at it from a horizontal plane, its signal goes this way and its signal goes this way. Well, if I'm driving along the ground, do I really want any signal to go up into the air?
No.
No, because most of the people I'm talking to are not going to be up in the air, which is why a vertically polarized antenna on the roof of a car is a very popular antenna. Similarly, if I were to put up a repeater on top of a building, what would that antenna be?
Vertically polarized.
Vertically polarized with the same kind of pattern. And I would be picking up people who have vertically polarized antennas from all directions, which is exactly what I want.
So
And-
does everybody have a vertically polarized antenna?
If you're mobile, yes.
But if you're not,
If you're not, well,
if you're at your house, do you want to have a vertically polar? Does it I mean, how do you pick which one you'd have?
if you want to be talking to people who are driving, if you want to be talking through repeaters, you would basically put up a vertically polarized antenna to match.
If you want to talk to someone far, far away bouncing, so these aren't very good for bounces.
They're not. So what you would do is, if you wanted to maximize your distance that you were talking to somebody on, for instance, this is known as weak signal work, you would typically use an antenna that's horizontally polarized, because you have an E field that's going this way, and when it hits objects, it tends to bounce up more. You get more bounce off of objects. So for very long distances, you would typically use horizontally polarized, but that's a very specialized case. If you were doing, as it's again known as weak signal work on VHF and UHF, that's what you would do. In fact, that was the next question. Sporadic E, we covered the E field right here. So sporadic E is typically found on that's typically found on 10 and 6 and 2 meters. You have access to all of those bands. It's really cool because when 6 meters opens up, which it doesn't usually do, but sometimes it does, all of a sudden you'll start getting signals in from 1,000 miles when there's typically nothing. So 6 meters is kind of in the sweet spot for that. And the problem, of course, with sporadic E is that word sporadic, which means you can't rely on it for anything. It happens when it happens. If you live in the, okay, who was it from Florida though? Who was here from Florida?
Nick,
Okay, you're gonna, if you get on 6 meters, you get 6 meter E skip a lot down in the Southeast. Florida's a real hotspot. It's supposedly because of the number of thunderstorms. So that's why we hardly get any sporadic E up here. Whereas the deep south, the deep South, Texas, the mid-Atlantic, Florida, they get a lot of good sporadic E. Which mode is responsible for allowing over the horizon VHF and UHF? And that would be known as tropo. And what we'll do is we're going to draw a low level atmospheric model. So here's the Earth. And now we're in the troposphere. This is where we live. And so you can have tropospheric scatter. Your signal comes up, it hits something in the atmosphere, and it bounces in a whole bunch of different directions. That would be known as troposcatter. And that can be good for up to 300 miles or so. Then there's another thing, which is even more fun when it happens, called tropoducting. So if you've ever driven a car and you've noticed on a hot day that you look in front of you and you see a reflection of the sky in the road, and it kind of looks like a puddle of water, what's actually happening is that you get a temperature inversion where right over the road, you're really hot, and then you get really cool. And what ends up happening is that you get light waves because you now have differing indices of refraction. Your signal comes down and gets bounced around a few times, and then it gets picked up by you. So even though the road is not containing the highway, what you're getting is a bounced around reflection of the sky. And this is known as a duct, but it would be for light waves. It's essentially a little temperature inversion. The same thing exists on the radio, but because everything is of a much larger scale, because instead of dealing with things that are in the nanometer range, we're dealing with things that are in the meters range. What can happen is you get the troposphere and you get a layer, which is an inversion. Normally, as you go up, it would get cooler and cooler and cooler. So this would be hotter, and this would then be cooler. Essentially, you get a layer which would be, it would get cooler, but then it would get hot again and then cool. As soon as you get that interface layer, you have a differing index of refraction, and your radio waves, which would be sent up, can go into here and hit this interface and bounce around a bunch of times, being bent just like your spoon is bent in your glass of water. And eventually they'll come out somewhere, and that might be 500 miles away, and that's known as a duct or a tropoduct. The most popular one of these to work is if you happen to live in either Southern California or Hawaii, or even Northern California for that matter. Every summer, there is a duct that forms between, let's say, Mauna Kea in the Hawaiian Islands and Southern California. And you can actually operate at up to like the 10 gigahertz range by shooting signals through the duct. It helps to be on top of the mountaintop to get your signal into the duct, though. But pretty cool stuff. At microwave frequencies, precipitation, because of energy absorption by the water, can greatly affect your signals. At lower frequencies, rain has little or no effect on what you're able to do. Okay, so now we're on to page number 31, which is HF propagation, which we kind of covered a little bit. Sorry, this got really ugly, but I think we pretty much have covered it. We have the D, E, and F layers. They contain something, they are parts of what we know as the ionosphere, which is an ionized layer of the atmosphere starting at about 50 miles up. HF and VHF give us the ability to do long distance ionospheric propagation. It's very, very useful on HF. It's what allows us to talk to Europe, allows us to talk to South America. Okay, so now what we're going to talk about is something called the sunspot cycle. So the reason this is so important is because the sun goes through these 11-year periods of high activity and low activity. And in addition to the difference between day and night and your ionization levels, the sun, when there are a lot of sunspots, typically puts out a very high amount of ionizing radiation all those microwave, all those ultraviolet and X-rays. When there are not a lot of sunspots, it turns out that the sun does not make a lot of ionizing energy. Ionizing energy is what makes the ionosphere into the ionosphere. So what happens is every 11 years, we go through periods of very high and very low solar activity, which generate very high and very low levels of ionization. When we're at the peak in the middle of the day, the 6 and 10 meter bands can be used for worldwide communications because there's so much ionization up in the upper atmosphere. And when that is not at the peak of the sunspot cycle, that just completely disappears. We haven't had a good peak for probably the last 15, 20 years or so. Hopefully this next cycle is a good one. It's starting now. We don't know what's going to happen, but this is a good time to get in. From when is the 10 meter band best? Through the F layer. 10 meter band, if we look at our frequency chart, you will see once again that the 10 meter band is 28 to 20, essentially 28 to 30 megahertz. It's the highest frequency of all the HF bands. It's the one that's most improved by a lot of ionization. So when there's a lot of ionization, when does that occur? In the middle of the day, from dawn to right after dark. And preferably during the summertime locally, but.
Question?
Yeah.
So going around the world means that if you're going east-west, that the other side of the world is dark.
That is true.
There isn't ionosphere ducting or bouncing because.
Well, there's still some.
There's still some.
Yeah.
So, but the question was, is it mostly north and south for the daytime?
Typically, you're going to find that 10 meters is opened up transequatorially, yes.
Okay. Transequatorial is fancy for radio talk for north and south?
Yep, exactly. Now, interestingly, I can show you guys a very cool map, which I think is very cool. Hopefully you think it's cool as well. But okay, so now what we have is there's a mode called FT8, which is a digital mode by which signals are able to, where computers are used to encode and decode signals at very low power levels and through very, very poor conditions that allow you to have communications on a very, very slow data rate, but also you're able to decode every signal that's on the band, which means that you can see everybody who's been able to hear everybody all around the world over a period of time. So if I were to, for instance, listen to received by grid square, which we'll get to, CN84, which is our grid square, over the last 15 minutes, we would find that, hopefully there's somebody. There we go. Okay. Ooh, look at that. All that red. That's 12 meters is open. Interesting. We're hopefully going up on the sunspot cycle. All right. So this is actually segmented out by frequency band. And notice there's some paths to Europe. This is at roughly 14 megahertz. We have these open paths to the East Coast, these red dots. If we zoom in, that would be the 12 meter band. And notice, what do we have in between here and where those red dots land? And I can open this up a little bit here, make it so that only. Okay, so there's a very distinctive pattern here. Do you agree, everybody? What do you notice?
Nothing in the middle.
Nothing in the middle. You've got this ring that goes through Colorado and Wyoming into Arizona. And notice from this central point, what do you have? You essentially have a first ring. What do you have outside of that?
Is that the next ring?
Yeah, but but there are people who live and are on the band in between these rings. There's a lot of people. Where are the signals?
Above them?
I mean, where'd they go? Yeah. I mean, basically, in order to get that, your angle off the atmosphere, the ionosphere would have to change, right? Because essentially think of it as a mirror. So this is known as the skip distance for this particular band at this particular time. Anybody who's inside that zone from the starting point is too close, and your launch angle is such that the signal, instead of being refracted back down, is going through. If the angle is too low, what would happen is that it's getting internally reflected or absorbed. So that is why what we see here is signals that are getting to this first ring are coming down and actually being heard. The second ring would be signals that are coming to this first ring and getting re-reflected off the ground back up to the sky at an angle so that they can hit the atmosphere and bounce back down again. And notice that it's a little bit fatter because this is probably a narrow ring. So you have the shortest and plus the shortest, or the longest plus the longest. So the second ring is going to be a little bit bigger than the first one. So this is basically a real world application of atmospheric physics. Very cool.
So are they must all know exactly what the angles are and the skip distances for the various frequencies and widths. Right?
Well, you can sort of predict it, but the problem is that the ionosphere is not flat. The tricky thing is that the ionosphere is not flat. The ionosphere the ionization changes altitude, and it's also bumpy.
Mm-hmm.
So as you're listening, you will not hear typically something that is solid and reliable. You'll hear something with fading and signals that sort of come in and out over time, because the ionosphere, as it's moving, is rippling. Your signal will typically bounce along with it, and over a period of 5 minutes, you might hear it come in and be really solid for 3 minutes of the time and fade out for 2 minutes of the time. It might change every 15 seconds. That's part of the fun. If we look at another band, for instance, let's look at the 40-meter band. My guess is we will probably see almost nothing. Eventually. Come on. Notice here down at the bottom, 23 billion reception records received. There we go. So virtually nothing. And the reason that there's almost nothing is because, number one, it's the middle of the day and there's probably very few people on. And number two, because it's the middle of the day. And for the most part, those signals are being absorbed. But now let's say I go over to a different area. I'll go to PM 95. PM 95, I believe, is Tokyo. And hopefully it doesn't make me wait so long. Because it's sort of at the day-night terminator over there in Japan. And what we will hopefully see is a very good bifurcation. Oh, there we go. So not a lot going to the east, but look at it going to the west. Because those frequencies travel really well through the dark. And now if we were to look at all bands, let's see if it's smart enough to do this. There we go. You notice a very distinct bifurcation of signals where you have these blue and green dots. Those are 30 and 40 meters with a little bit of 80 thrown in. Those are signals that travel very well through the darkness. And then all the yellow and bright yellow, those are the ones that typically travel really well through the daytime. And this happens on a daily basis. It's seasonal. It's from day to night. Okay. Which of the following is a likely cause of irregular fading of signals received by ionospheric reflection? That would be random combining of signals arriving by different paths. Because again, the ionosphere is not flat. You'll have periods of fading and then really strong signals, and then they'll fade again. That's known as fade. Signals bouncing off the ionosphere. typically the polarization of antennas that you're pointing at the sky doesn't matter a whole lot unless you're trying to work satellites. The reason it doesn't work a whole lot is because the ionosphere has a way of taking horizontally polarized signals and sort of spinning them and randomizing the signal polarization coming down. For vertically polarized signals, it'll do the same thing. So essentially what comes down is randomly polarized. And since it's random anyway, it doesn't matter what kind of antenna you use to pick it up. Pretty much anything will work. All right, everybody ready for another break? 5 minutes?
Sure.
Is that they all work equally badly or they all
Yes.
work equally well?
Both. I mean, the real significance is if you can put up something with gain, then you'll start to see a real impact. But essentially, yeah, if you put up a vertical dipole versus a horizontal dipole, you will see similar performance when picking up signals from floating around in space, bouncing off the sky.
What about just going straight through the sky for satellite?
That's a different story. And typically what will happen is that satellites, they'll have antennas that are, they're circularly polarized, but not always. Sometimes they'll have a dipole, for instance, and the dipole is on the satellite, but the satellite is rotating. And that's actually called spin fade because it'll go from, you know, horizontal to vertical based on its orientation to you as the satellite is rotating. Because satellites don't just sit still, they actually have to spin. The other thing is that the antennas, let's say that you're down here and the satellite's up here, the antenna might be rotating and it goes behind the satellite for 15 seconds, in which case you'll probably hear nothing for a little while.
Quick question for you, Scott.
Yeah.
Are we going to talk about equipment at all and your recommendations for starter and like intermediate radios?
We can a little bit.
I know I've been reading about that in particular online and everyone says, oh, just get the little like $30 or $50 Baofeng
You know,
handheld thing. But
yeah, here's the thing. They have their, like a Baofeng has its place. I've owned, I've had 6 of them.
Yeah.
And here's how here's my take on it. And then I'm going to have to go use the bathroom, but here's my take on it. For $25 or $30, if I drop it and break it, I don't care. You know, for $25 or $30, if I drive over it with my car, I don't care. You know, for $25 or $30, if I drop it in a lake, I don't care. Right? If I were to take this radio, which is $150 and drop it in a lake, it would probably hurt me a lot, you know? So if I were to take, but you know, let's say I've got I know somebody who got their license and doesn't have anything to transmit with. You want to borrow one of my Baofengs? Sure. I'll just give it to you. You know, give it back. Don't give it back. I don't really care. If I never see it again, it's okay. But now the only problem is that if you take a look at what you get for $25, it's a great deal for $25. But if you start looking at its performance, you take it and you put the stock antenna on it. The stock antenna actually is very well matched to the receiver that's inside it. If you hook it up to a bigger antenna and you're in any populated place to speak of, what will happen is that the receiver itself is very, very poor at rejecting other signals outside of the band. And even though you aren't receiving it, the receiver energy that is essentially used up in hearing those things, and it will essentially desensitize your receiver to what you want to listen to.
Gotcha.
And if you hook it, I've tried it. If you hook it up to an outdoor antenna, you know, it's totally swamped. It becomes completely useless. So the difference between the $75 radio and the $25 radio is that the internals might be the same as far as the receiver goes, but the RF performance, you know, the RF section, the filtering that keeps it from having a glass jaw are a lot better.
Yeah. I know whenever I start a new hobby, I've found that I do the best if I go for sort of an intermediate level, something that's not like too advanced to start out with, but that I also don't feel like handicapped by as soon as I, start to progress a little bit.
Yeah.
So I'm definitely willing to spend like $100 to $200 out of
Yeah,
the gate.
and you'll be happy with almost anything you get in that range. Literally almost anything. And then it becomes a question of, okay, do you want it to have APRS built into it? Do you want it to have a GPS so you can run APRS? And then you don't have to carry around a TNC or anything like that. If you're talking about HF, the question then becomes, do you want to do digital? How much integration do you want with your computer? What does it have as far as, RF power output? How portable is it? And things like that. So
cool. Any brands you recommend or recommend staying away from?
Not really. I mean, if it's, for the most part, I typically try to stay away from the Chinese made stuff. That's Chinese branded. The reason being that I've found that in some cases their QC is desperately lacking. The other thing that I found is that, for instance, if it's a significant company, Yaesu, ICOM, Alenco, Kenwood, a couple others, reputable, they're typically going to make everything that they make. Every copy of everything they make is going to fall within FCC specifications.
Nice.
Right? They tested it out. It was approved. If you get one of the Chinese made ones and their QC is spotty, then you might find that the copy that you get doesn't meet FCC spectral requirements.
Gotcha.
And you won't know until you're interfering with someone or you put it on a spectrum analyzer.
Yep.
So
cool. Thank you.
Yep. All right. I got to go use the restroom. I'll be back in a minute. Okay, everybody ready? Ready and raring to go? Okay, everybody ready? All right, here we go. We are on to antennas and feed lines. We're getting into the stuff that I consider the most fun. So we are on page 33 and here we go. All right, which of the following describes a simple dipole antenna? Okay, so I'm going to draw a simple dipole antenna. There's my feed line. There's my wire. My wire typically is a half wave long, cut for whatever frequency and wavelength you want to be doing. So there's my half wave antenna. The polarization of an antenna is in parallel with the wire itself. So this would be a horizontally polarized antenna, parallel to the ground. Okay, why is this such a great antenna? And here is why. I'm going to draw a wave. Okay, as we sort of discussed before, current is what makes an antenna radiate energy. If you can't get any current into the antenna, you can't transmit a signal. So if this is our wavelength, a half wave would be right there. And as we discussed before, what is the current at the end of a piece of wire? That'd be 0, which means that the current has to be 0 at both ends. So if I were to take this and translate this down to here, what I would find is that I actually get a perfect maximum current right here at the middle, which means that this antenna is the smallest antenna that is perfectly optimized for me to transmit maximum signal using maximum current. And as it turns out, right here, I want to feed my energy into it. So I have I, we're going to go back to Ohm's law, and E. So what we're going to do right now is say, using my E equals I and R, I don't know my R, right? Well, but I do know that I have maximum current and I have some voltage.
Didn't you say most antennas are 50 ohms?
It depends on the antenna. All right, so here we go with this. Okay, so typically a dipole is actually going to be about 72 ohms, but for the most part, we say, yeah, 50 ohms, we're going to go with that. A dipole is actually 72 ohms. But if we're feeding voltage, we're feeding current into an antenna, and here's our voltage, R is equal to E divided by I. So what does this mean? This means that if we have our current is big and our voltage, because our voltage is going to be typically out of phase with the current, we're going to have small. What is small divided by big? That's going to be small. So that means that because our resistance is small, we can actually put energy into the antenna. So instead, we're going to redraw this antenna. I'm going to get rid of that. And we're going to make it so that we're going to put our feed point at the end of the antenna. We're going to draw our current again. We're going to draw our voltage again. But now, what's our resistance going to look like? By Ohm's law, R equals E divided by I. At the end, it's going to be big divided by small. What's big divided by small? That would be big. So now we're going to have a very high resistance at the end of the antenna, which is why we typically don't feed an antenna like that unless we have a special transformer, which will give us the ability to feed power into a very high impedance. So that is why we typically build a half wave dipole like this, and we feed it right in the center. Okay, so now we're going to make our antenna and figure out how long it needs to be. So 6-meter antenna. So everybody, somebody take a look at the frequency and wavelength chart. Somebody give me a frequency for the 6-meter band. All right, who's got it?
50 megahertz?
All right, let's go with 50.0. Okay, let us do our calculations. Ready? What do we have? 300, F, and lambda. All right. So we want to know an exact wavelength to design for. So we're going to get rid of that. So that would be 300 divided by 50, which is
60.
6.0 meters. Okay, so now we want to make a half wave antenna. So cut that in half. It's 3 meters long. And now we want to take 95% of it. So that's 2.85 meters long. And again, that is to the 95% is to account for the real world, real world effects, capacitance, inductance, and so on. So now we have to convert this because we live in the United States and we haven't adopted the metric system. You have to take 2.85 and multiply that by 39.3 inches. We get 112 inches.
So that's the distance from where to where.
That is the total length of the antenna of
Okay.
a half wave dipole. That is how long you'd make it. So how long would you make each leg? About 56 inches. Now, it would not necessarily have to be fed in the center if you didn't want to. You could feed it a little off center. You would have a pattern that would still be something like you wanted it to be. And then just so long as your total length is 112 inches. And sometimes it's actually desirable to feed it off center. Okay, next we're going to do, okay, so let's say that you built this antenna and you found that for some reason you had an antenna tuner and the antenna itself was actually resonating at 49.7 megahertz. Okay, so what does that mean if your antenna has too low of a resonant frequency? What does it mean if it's too long? That's right. It's too big. So what would you do at that point?
Snip.
Snip, snip, snip. All right. And you want to cut off just a little bit at a time. Because if you cut off too much, let's say after your first pass, your antenna is resonant at 50.1 megahertz and your target is 51.0. So then that's your target. And you cut off a little bit more. And oops, I cut off too much. So now it's at 51.6 megahertz. What do you do now?
You add an inductor onto it to make it look longer.
Yeah, or more than likely what you do is you just grab your soldering iron and you put a little piece on. But that involves, you know, grabbing your soldering iron and putting a little piece on. So the basic rule of thumb is that you cut off just a little bit at a time because it's a lot easier to make something shorter than it is longer. It's much easier to make an antenna that's too long and shorten it.
So my question remains that with what you referred to there as the feed, is there a break between those two halves?
Yes.
So there is, okay.
Yeah, there's actually a split right
Or
there.
else it would be a short and you
Or
wouldn't
else it would
get
be a
any
short.
difference on the two sides of the.
Correct. So each antenna is then
Okay.
separated from the other.
Okay.
Sorry, that was poorly drawn. So each leg is going to be of that length. Okay, so that being said, if we were to take this antenna and again feed it off the end, the overall length would still be a half wave. A half wave is the smallest basic antenna that works really well, with one exception, because there's always an exception. Here we go. This would be a perfectly reflective ground plane. Okay, so this is all metallic. Let's say it's a metallic ground plane. And you took an antenna and you put it here above the ground plane. So let me ask a question as I turn off the light here. Okay, so I'm going to take my light reflector right here, which is my plate. And okay, so I'm going to hold this up and tip this down. There we go. All right. So with it right there, how many lights do you see?
We don't see anything.
Oh, shoot. Sorry, I have to unshare that. It was just that it was really small. Do, do, do. There we go. Okay. There we go. How many lights do you see in the image?
2.
2. Okay. How many are there for real?
1.
There's 1. Okay. So this is known as a reflective ground plane. And that my glossy plate works as a really good reflector for light, but not so much for RF. However, a metal plate would work really well for RF. So let's think of things that make a really good metal plate, that are a really good metal plate. The best one that I can think of that most people have is the roof of a car, which is usually, let's say, 5 by 6 feet of steel. So if I can connect this antenna so that here's my roof to the outside world, it does not look like there's only one antenna because it's perfectly reflected. There's one up here and one down here. If you didn't know that there was a reflective surface, it would look like 2. It would look like there were 2 things. So again, this is actually a ground plane, which is reflective. So how long would you suspect that that antenna would appear to be from the outside world? What would the total length of the antenna be in wavelength?
Twice its length?
No, well, yeah, twice its length. What would the ideal antenna length be? We just drew one, but it was horizontal.
A quarter wave.
That's right. It would be a quarter wave up here and a quarter wave down here for a total of a half wave. So this is known as a quarter wave ground plane. And in reality, this bottom part of the antenna doesn't even exist. So how in the world does this work? Well, we just showed that it has to because of the reflection that exists. Now, one thing that happens is that if I were to draw the half wave dipole antenna that looks like this, this has an impedance of 72 ohms. If I were to feed this antenna right here, so that here was one leg and here was the other leg, this antenna has a feed impedance of 36 ohms. It's actually half, but it works just fine. Both of these can be pretty well fed with cable that is 50 ohms characteristic impedance. And that's our standard cable that you'll typically find in the world that you can go and buy thousands of feet of. Now, the other tricky thing is you might say, well, okay, clearly this is actually connected to the ground plane, right? There's an electrical connection. But now I'm going to redraw this. This is typically how you would buy a mag mount antenna. If you've ever seen a magnet mount antenna, it just sticks to the roof of the car. Well, how in the world can that possibly work? It's not connected to the roof. I want to hear somebody have a good guess. I like guesses.
You can induce a connection.
Well, so here's internally, there's a plate that's now held off of the roof. What does that thing mimic? What does that look like? Two parallel plates. What is that?
Capacitor.
And are we operating at DC or AC?
AC.
AC. As far as that goes, that looks like a short circuit, which means that electrically speaking, this top plate, which is our other half of our antenna, is capacitively connected.
Okay, so
To
it's
the
not
ground.
it's not inducing a connection, it's capacitating a
Yeah,
connection.
it's basically inducing a current to flow in the roof of the car
Through the paint and everything.
through the paint. Yep. Okay, so now we're going to take a look at how long this antenna has to be and why they're so great. Because we're going to pick the 2 meter band. And okay, so somebody pick a frequency in the 2 meter band.
$140.
Wait, 140 is not in it though.
145.
145. Okay.
Oh,
So,
I'm not, my slop isn't tuned in yet.
all right. So 300 divided by 145. Somebody give me a number for that.
2 point something. How's that?
Well, it's close.
Divided by 145.
Yeah.
2.0689.
All right. 2.07 meters. Okay. Divide that by 4.
0.5172.
Okay. We'll go 0.517. Okay. Multiply that by 0.95.
0.4913.
Okay. Multiply that by 39.37, which is inches per meter.
19.3456.
There you go. There's our 19-inch long 2 meter vertical antenna.
So
And that's, yep. Go ahead.
no, I get it. The 0.95 is one of these things that I'm just gonna forget.
Well, no, it's a fudge factor. It has to be there because if we were building this antenna in an unreal world, it wouldn't work. It would be too long if we didn't do the 0.95. And that's again for real world effects. So go ahead.
Do quarter wave antennas only work with a ground plane?
Yes, it won't work worth a crap without it. So,
and the size of the ground plane has to be the same as the height in one direction?
It does not. It just has to exist. Ideally, if you think about it, it has to be at least some size. But let me ask a question. So this radio, this is actually a quarter wave antenna that's wrapped up in a coil. Let me unshare that so you can see it. Okay, can everybody see this antenna?
Yeah.
This is a 7-inch long antenna that works on the 2 meter band. This is clearly not 19 inches long. It's only 7 inches long. And that's because it's loaded, it's coiled up inside this base. So my question to you is, this is a quarter wave vertical antenna. How does it work? Where's the ground plane?
Your hand.
It's my hand, it's my whole body. I am the ground plane. It is actually inducing an RF current in me. And I am becoming the second half of the antenna. So if I just put it on the tabletop and tried to use it, it would not work very well.
Really?
Nope.
Oh.
Now, if I were to put it on the roof of my car, it would work considerably better.
So does it, so what part of the handheld is transferring or is inducing the,
that would
what
be
part of that handheld is responsible for inducing the ground plane
that
effect?
would be, let me get it open. Notice what the body of the radio is made of. This is an alloy case. So basically, if I'm holding it, it's actually grounded. It's actually, this is the other half of the antenna. The case is a metal alloy. And if I'm holding it, it's capacitively coupled to me. So that is one of the reasons I don't particularly like running
The
high
plastic
power.
ones.
But I will say, here's the other interesting thing. I have a bow thing, and it's got these two screws right in the back that hold, if I, for instance, if I took off the belt clip, there are these two exposed screws. What I noticed was that when it was hot out and my hand had sweat on it, as I was transmitting with 5 watts, if my hand made and broke contact with one of the screws, I would get an RF burn. And that's
Wow.
because I was part of the ground. And as soon as I broke the connection, it was now only capacitively coupled. I was actually breaking the current path between the body of the radio and my hand. And it would arc to my hand and give me a little burn.
Little Red Farm.
It hurt. It definitely hurt. Okay, what is loading? Loading is the act
Wait.
of making. Oh, go ahead.
So I'm looking through the documentation and stuff, and we talked about the half wave and then the quarter wave. And so I'm trying to figure out the reason that it's just a function of being able to make an antenna shorter, that's more manageable with regards to construction and where you want to run it. That's the whole purpose of these. I mean, of choosing. When do you choose one antenna over another?
Okay, so if let's say you have an infinite amount of room available to you. So if we were to draw, part of it is what you want to do with it. So if we were to draw this antenna, the radiation pattern would look like a donut shape around the antenna.
Right.
Okay, if I were to stretch this out so that it was vertical, my radiation pattern would look like this. It would look like a donut like that.
Right.
Right. If I were to take this and scrunch it down by doing a quarter wave over a ground plane, it would actually look like this. Right. I would still have energy going in these directions, but the lobes, because there's not a lot of gain, would not be terribly flat. So let's say now I wanted to build something with higher gain, which did more with my signal, and I had room to do it. Okay, so I would take this potentially, and I would put a matching stub, which would delay the signal getting up to the second part. And then I might actually do another one. And what this would do is it would essentially, I gotta stretch that out a little bit. I'll redraw it. So it looks like this. Okay, so Pat, you said you have what? Kind of like a GP9 or a Diamond X50 or something? Okay,
Yeah,
this is what's actually inside your antenna. If it's a ground plane. I don't remember if it's a ground plane or if it's like a halfway bottom section, but essentially this is what is inside an antenna that is extended to give you more gain. This top part of it is either there or not there. The bottom part, this is a quarter wave antenna. This would be a delay stub, which delays the signal getting up to the second part of the antenna. This would also be a delay stub, which increases the length of the antenna. And what it allows you to do is if you're drawing your current distribution, it would do this. And then this is actually a half wave long, and this is a half wave long. This would be like this. This would look like this. Normally, you'd have to go through a whole period where it went like this and came back up the other side. But because of the delay stub, what we've done is we've taken this part of the current and then this part of the current where it comes back up, and we've basically folded them over each other. And the same thing up here. So we folded them over each other so they cancel each other out. So that now we have this section and this section and this section separated by a particular distance, which is a half wave each, which are now radiating in phase with each other. And when you do that, you get a multiplication effect or additive effect.
Okay.
And that is actually, this actually creates something called an array factor, which increases your gain.
Okay.
And that is why antennas can, and this is typically, if you have an antenna like that Comet or like a Diamond or something like that, where it's inside like a plastic or fiberglass radome, that delay section is actually, the whole thing is contained inside that inside that fiberglass cover to
But
keep
now
it
this-
shielded from the weather.
But this is, the gain isn't directional in this case.
Oh yeah, the gain, it has a pattern that, because essentially you now have three antennas, or if you look at it, you have 1, 2, 3, and then the top ones are reflected down below also. Essentially, you have a 5-element array because you have 1 and 2 and 3, and then 4 and 5 are down there in the ground, essentially reflected by the ground plane.
Okay,
So
but
this
you-
actually becomes a very high gain antenna,
But in what direction?
perpendicular to the antenna, and it's
That's- okay,
omnidirectional,
but
looking from
when you're
above.
perpendicular to the antenna, you were calling that omnidirectional.
Looking from above, you are. This is looking at it from the side.
It's right, but it's still not the gain. The gain isn't in a particular direction. It's in all the directions at a single dipole. If you had just had the original quarter wave down there, it would have had the same radiation pattern, but just not as strong.
Right.
correct?
Well, here's your first, let's say that your original antenna pattern looks like this. Your
Yeah.
new antenna pattern will look like that. It will be much flatter and much bigger, a lot more energy, very low to the horizon.
But not, okay.
Looking
guess
at it
I-
from above, it will still be 360 degrees because there's still symmetry.
Yeah. And I
So-
was thinking, I was associating gain with the direction.
Well, the
More
direction
than-
is that it's squishing the whole thing down.
Okay.
So the other thing you can do is if you see like a tower with like an FM transmitter tower, you might actually see something that looks like this. You might see something that looks like that. This is very typical of an FM transmitting station. And these are individual dipoles, vertical dipoles that are spaced from each other and phased so that they get a multiplicative or additive effect, and they have an array factor, because you don't really want to take your 50,000 watt FM signal and aim it toward the sky, because no one's listening up there. You want it as low to the horizon as you can. Same kind of story.
So then the reason I'm asking with regards to these kind of different antennas is how do we pick based upon our geography or where we want what type of antenna we should be getting?
Well, one thing you can do is you can look at your local terrain, figure out there's all kinds of tools out there as well. Like here, let me share one.
Because I'm back into a valley, the tail end of a valley where I know that there's a repeater 4 miles from me, way at the other end, around a small curve.
Yeah, you should be fine.
How much of a valley?
Sorry,
How much of a valley?
what does that mean?
How deep?
How deep?
Oh, it's at what, 500, 600 feet?
Oh,
It's not much.
Yeah, it depends. Like a slot canyon, I would worry more about. Let me see.
I know about it the same, and I just put mine into the chat box, and I reach probably 20 miles on a bad day.
Let's see if I can get into this. Oh, here we go. All right, so there's another site, for instance, called Radio Mobile Online. Let me look at one of the, oops, nope, wrong thing. Oops, shoot, I picked the wrong thing. Okay, my coverages. So for instance, you can set up coverage areas, and I can look at my coverage. This is actually from my house. Everybody see that?
Yeah.
Okay, based on parameters that I plugged in, antenna height, power levels, and things like that, you can see out toward the east. You notice that signals travel up and down valleys, but where they get, and notice up here, South Sister, that's at 10,000 feet. That's 80 miles from my home, but it's line of sight. But everything else is, you can see the individual shadows and things like that. Green is good, yellow is not so good. And this is a free site, which is, you can plug in, you can land exactly where you are and plug in your information, and it'll generate a map based on topography. Very useful.
Okay.
So what
Especially-
antenna for like Florida, which is just flat and there's nothing but ocean around it, either side, sea level?
Yeah, that would be called not much of an issue. That'd be called put up the biggest thing you can as high as you can, because the higher you are and the more gain you have, the further you're going to go. All right. Any other questions on that? Okay, here we go. Antenna loading. All right, so the act of loading means to shorten an antenna, physically while not shortening it electrically. So let's say that this is 19 inches. I can take that same amount of wire and do this with it, and it becomes 7 inches long. Electrically, there's still 19 inches of wire thrown in there, but it's coiled up so that it's only 7 inches long. So what do I give up when I do this?
Gain?
I give up a lot of gain. In fact, I induce a fair amount of loss. My efficiency is way, way down. The reason being, if you think about it, if I were to draw the current distribution on this, my current at the top is going to be 0, and it's going to be peaked at the bottom, right? Because this is a quarter wave long. So I just drew a quarter wave on this antenna. But now I'm going to start here, and now all of this stuff is going to be all scrunched up. And eventually it's going to be really high at the bottom, but all this stuff in there, it's all kind of folded back on itself. So really the only part of this antenna that's even working remotely well is the part at the tip and the part at the very bottom. All this other stuff in there is kind of like useless. If I assume that this is, I'm going to call this starting point, and I'm going to call this ending point, and this is my reference, the starting point, I might find that this antenna has actually -4 dB of gain compared to the other one. So do I care? And this is where we start to get into trade-offs, excuse me, and antenna design and system design. All right, so let us say that I have this system right here, and I'm trying to get into this repeater. And the repeater, we're going to assume, has 0 dB of gain. It's just, it's just there. And it has a minimum discernible signal of, let's say, -120 dBm. Now, this is a special kind of decibel. It's with respect to 1 milliwatt of energy, 1 milliwatt of power. So we're going to call it -120 dBm, and that's a function of the receiver that's built into the repeater. It will respond to any signals that are that strong or louder. So -121, Nope. Minus 119. Yes. Okay. So now let us say that I am starting down here with a handheld, and my antenna or my signal starts out with 1 watt. All right. So far, so good. How much is 1 watt compared to 1 milliwatt? How many times bigger?
1,000 times.
1,000 times. So how many decibels do I get from 1,000 times? 10 log base 10 of 1,000. 30 decibels compared to 1 milliwatt. So I'm now at plus 30. Okay. And the signal path is, let's say it's line of sight, but there's a little bit of trees in there or something like that. And it's negative 145 dB. There's 145 dB of loss in between us. Okay, so what's plus 30 minus 145?
Minus 115.
Do I get heard or not? Compared to negative 120, I'm still above it, which means I'm good. But now let us say that I have only an antenna that induces a loss of minus 6 dB. Because it's a little, well, I call it a dummy load. It's essentially a dummy load antenna. It's a very lossy antenna. So now where am I? Plus 30 minus 145 minus 6. I'm now at minus 121. And guess what happens? Somebody want to take a guess what happens?
Nothing happens.
Nobody hears me because I've now added enough loss in my antenna system that nobody can hear me anymore. So now what I've done by reducing the gain of my antenna, essentially inducing a loss for convenience, is I've rendered myself unable to get into a repeater system, unable to be heard.
So is the thought of that the repeater is looking for something that has a high enough quality of signal with regard to, is that what it is with regards to the amount of loss?
Not on purpose. So, but now let's say that I move here. I move closer to the repeater because I live somewhere else. My path loss now is minus 135. Well, I take that same system and I replace this minus 145 with minus 135. And now my signal is at minus 111. Does it work?
Yeah.
It does. So, nope, not here, but yes, it works there. So really what this means is that your choice of an antenna is very much dependent on where you are and what you plan to be doing. Sometimes, if you're close enough, the signal path is good enough, there's enough excess gain in the whole system that even your lossy, crappy antenna will work just fine. And sometimes you put yourself in a spot where it won't work. And you have to decide, okay, I'm going hiking. Do I want to bring the antenna, the big antenna, and put it up in a tree, or do I just want to go with the handheld and hold on to it? And maybe I have to climb up on a hilltop to get heard. Okay. So now we're going to look at something called a beam antenna or a Yagi. A Yagi is a type of a beam. A beam is an antenna that concentrates a signal in a particular direction. Other forms of directional antennas include, for instance, a dish. It can also be a quad, which looks like this. It's successive loops of wire. typically what you'll have is something called a driven element. And here's the driven element here. Anyone take a guess what that kind of looks like? Anyone guess what that might be? What kind of antenna do you think that is?
Dipole.
That's a dipole. Okay, so you take your standard dipole, and then behind it, you take something longer, and that's a reflector. Okay, so I now have a 2-element antenna system. I have a dipole and a reflector behind it, which is a little bit long. What that does is it will tend to capture the energy going this way and radiate in phase, re-radiate the energy in a forward direction. These elements in front are directors, and these tend to catch the energy and sort of, if you want to think about it, they make an easier path for the signal to go forward. And the overall effectiveness of those extra elements compared to a dipole are known as the gain of the antenna. And what do you think? What's that measured in?
dB.
dB. Okay, so I might have a dish. The dish might have 30 dB of gain. Inside the antenna, that driven element is still a dipole. Although in a microwaves, it could be like a feed horn or something. This particular antenna, there's actually a single driven element called a loop antenna. And these are all loops. And this is actually a full wave loop. Each of those is a full wave loop, but you still have the same basic thing where this is long and these are short. So what is the advantage of a Yagi antenna versus pretty much anything else?
You can point it directly at something.
You can point it directly at something. And on top of that, it's pretty easy to build, at least on VHF. So for instance, I will show you a very easy to build antenna. This is one of the most popular VHF antennas that there is to make. Here we go, tape measure Yagi. And why is it so easy to make? What do you have in the center of it? You have that driven element, which is a dipole. And then reflector is slightly longer, directors are slightly shorter. And why is it so easy to make? Because all it is PVC and a matching stub on the dipole and measuring tape. Because everybody's got a broken tape measure, right? I've got at least one. It costs almost nothing to make and they work really well. The other cool thing is that they're very, very lightweight and they're easy to carry around. So they're very, very popular for direction finding. Okay, a Yagi, a quad, and a dish are directional. What is the gain of an antenna? Gain is increase in signal strength in a specified direction compared to a reference, again, measured in decibels. This kind of antenna is known as a rubber duck because it's made of rubber and it's flexible. The disadvantage, of course, is that you lose efficiency. It does not work nearly as effectively as a full-size antenna. If you're using a radio inside your car, why is that not as good as using it outside your car?
Your car is a shield.
Your car is a shield. That's right. It's a metal box. A 5/8 wave antenna will work better than a quarter wave antenna. The reason being that a 5/8 wave antenna will give you a little bit lower angle of radiation and a little more gain. Okay, so now we have moved on to feed lines and connectors. And I think it's time for another 5-minute break. What do you think?
Works for me.
Okay.
Oh.
All right, everybody ready to do feed lines and connectors?
Oh, yeah.
Okay, we are on page 38 on the book. 38, 36. All right, feed lines and connectors. What is the most common feed line selected for amateur radio antenna systems? That would be something like this, which is coaxial cable. Coaxial cable is basically an outer layer and an inner layer. The outer layer is basically a ring and the inner layer goes through the center. So you have a center conductor and then a shield. This is very similar to cable TV cable, which is also coaxial cable. It just differs in size and strength and power handling. What is impedance? Impedance is a measure of the opposition to AC current flow in a circuit. The unit of impedance is ohms. This is actually going to be very important. Most coaxial cables used in amateur radio are 50 ohms. That is the characteristic impedance, 50 ohms. Why do we use that? It turns out that it actually is best for power transfer as well as being able to match to other antennas. Some types of cable, you have RG8. This is RG8. This is RG58. This is RG174. You notice that they are totally different as far as sizes go. However, these are all 50 ohm cable. They have the same characteristic impedance. And that is because characteristic impedance is a characteristic of the cable itself. It's an intrinsic property based on the ratio between its diameter of the shield and where the center conductor is. So this is a very small copy of this. This is a very large copy of this. Where they differ is that whereas this cable, I could actually put 1,000 watts through. If I tried to do it with this cable, it would probably melt. I could easily run 100 watts through this cable versus this cable, which if I ran 100 watts through it, it would basically melt. And I can typically run about 10 watts through this cable. The other big difference is that as these cables go, their losses are significantly different. Typically, the bigger the cable is, the lower the loss will be. The other thing is that cable loss is rated in decibels per 100 feet, and it's a linear thing. So if you have 200 feet of cable, you'll have twice as much loss as you will at 100 feet. As your frequency goes up, your cable loss goes up as well. So could I get away with using this for my high frequency stuff, very low, HF, which is actually low frequency, quite well. I could also get away with using this. And for a short distance, I could get away with using this, which is teeny tiny. If I were on the 2 meter band, this is pretty good. This is kind of bad. And this, if I were to use 100 feet of this, I would essentially have virtually no signal on the other end because the loss would be so high. Okay, so as the frequency of a signal passing through cable increases, the loss increases as well. RG8 is the fat stuff that I showed you, the really big cable. RG8 versus RG58. RG8 is going to have much less loss. If you're curious online, there are actually many different cable vendors that they publish loss tables in dB per 100 feet based on frequency. Which of the following types of feed line has the lowest loss at VHF and UHF? The best insulator you can get internally is air. Air is very, very good as a spacer. It does not burn up much heat at all. Air insulated hardline is great. One of the only problems with air insulated hardline is that it's full of air. Because it's full of air, what does the air we breathe have a fair amount of in it? Everyone?
Water?
Water, yeah. What happens if you get water vapor, water in your cable and it condenses? What will it do to your cable?
Short it out?
It will oxidize. And if it oxidizes, then it starts to break down. If it starts to break down, then your cable isn't working anymore. So which of the following is the most common cause for failure of coaxial cable? That would be moisture contamination. For those of you who live in Florida, this is a big deal. So you're going to have to do some serious waterproofing. Why should the outer jacket of coaxial cable be resistant to ultraviolet? Ultraviolet light damages the cable jacket if it's not ultraviolet proof. And what gets into the cracks?
Water.
Water. There you go. So water, bad, bad, bad. It causes copper to oxidize and then it's not conductive anymore. So a disadvantage of air core cable is that it requires special techniques to prevent water absorption, such as dry nitrogen being pumped into the system and keeping it pressurized. So typically, if you run a TV station, that's fine. You do that, but it costs a lot of money and it's hard to do. Above 400 megahertz, this is called an N connector. N connectors are great above 400 megahertz. Now, oddly enough, the thing that we consider that it's typically called a UHF connector looks like this. This is a PL259. These are terrible for UHF frequencies. And therein lies some of the confusion because UHF does not stand for ultra high frequency in this case. It stands for universal high frequency. So a UHF connector is actually terrible for use at UHF. If you're on the UHF bands, you want to run an N connector. Why should coax cables exposed to the weather be sealed against water intrusion? And that's to prevent an increase in feed line loss. Again, water intrusion destroys cable. We're going to get to SWR. We're on page 38 right now. Standing wave ratio is a measure of how good or bad your antenna system is. Changes in SWR readings can be caused by water intrusion as well as a loose connection. So basically, if you don't have a solid connection, your standing wave ratio can vary wildly. So it's a good segue into page 38. Standing wave ratio is a measure of how well matched your antenna system is, or how well a load is matched to a transmission line. So ideally, you have a standing wave ratio of something called 1:1. You can have something called an SWR meter, which can look like this. Let's see. Let me share that. Here we go. The classic MFJ standing wave ratio meter. This is my personal favorite. Notice that this has forward power and reflected power, and it gives you these curves which show you wherever the lines intersect. All the way on the right-hand side where your reflected power is 0, notice that it drops off at 1:1. That means you have a perfect match. All of your power is going forward. Nothing is getting bounced back down the feed line. As you start to get up to here to 2:1, you actually have a fair amount of reflected power. When you're at 3:1, 4:1, 5:1, then you can get all the way to infinity where you basically have no power going out. It's a ratio. Again, ideally you have 1:1. If you see, let's say 4:1, this is a serious impedance mismatch, which means something that you did is really, really wrong and it's time to go fix it. Why is it important to have low SWR when using coaxial cable? The reason being that when you're using coaxial cable, I'm going to show you really quick on this screen that let's say I have my transmitter down here and I have feed line right here up to an antenna. Basically, what happens at this point is when my power gets up to here, depending on, let's say this is 50 ohms and the antenna is 70 ohms. This is not a particularly bad match, but what'll happen is some of the power goes out and some of it because they're not equal numbers, bounces back down. Well, when it gets down to here, it goes into your transmitter and it shows up being dissipated in your transmitter, which causes your transmitter to heat up. In addition, when it travels back down this line, it heats up the line. So if you have a really bad match, you cause a lot of heating in your transmission line and you can actually destroy your transmitter. So let's say you forget to hook up an antenna altogether. That's a really bad thing. That can actually destroy your equipment. So power loss in a feed line turns into heat because energy is always conserved. Why is it important to have low SWR when using coaxial cable feed line? And that's to reduce signal loss. You want your antenna to get as much of the power as it can. Another reason, something else that will happen if you have an SWR meter, which is a standing wave ratio meter. Here's your transmitter again, TX. You want your standing wave ratio meter right here going up to your antenna. So you can see what the world looks like looking out into your antenna system. Most modern equipment will actually sense what the standing wave ratio is by itself. If it sees something big, it will do something called a fold back. The reason that it folds back is so that it says, okay, well, my SWR that I see is 5:1. That means that most of my power is coming back. If I transmitted full power, it's going to fry the transmitter. So I'm intentionally going to limit automatically to 20 watts. That way, the worst that'll happen is I see 35 watts here and it won't kill the transmitter. So that's what the fold back circuitry is used for. It's a protection device. Yeah.
So if you have an SWR meter, some of them have them right on the radios, but if you wanted to have a separate one, would that come between your antenna and before you get to the tuner?
It would come between the tuner and the radio.
That's what I needed to know.
Yeah. Because otherwise it would just show you what was happening in the antenna. The antenna tuner you basically use to match your antenna system to the radio.
Okay.
So
it's the last thing before the feed line?
Basically, if you've got your transmitter here, if it doesn't have an SWR meter in it, you want your SWR meter right here. And then if you have a tuner, your tuner goes here, which is your matching network, and then goes out and up.
Okay. So
and that way, when you adjust your knobs, you can see what's happening. What most equipment is built with a characteristic impedance of 50 ohms. So what you want to see out of your tuner is that the rest of the world looks like 50 ohms. So out here, you want to actually tune your tuner so that this looks like 50 ohms. And it's rare that that's going to happen right off the bat, which is why we have these things called antenna tuners or a transmatch, basically an impedance matching network. Now, if it's a single band radio, 2 meters, yeah, that's easy. The problem comes when you start doing high frequency radios, high frequency antennas. Let's see, what is the proper location for an external meter in series with the feed line between the transmitter and the antenna? Okay, let's see. Why do most solid state amateur transmitters reduce output power as SWR increases? Again, that's called fold back, and it's to protect the output transistors from being fried. An SWR meter is not the only way to measure SWR, as you may have noticed here on this picture that I showed you. This actually was measuring forward power and reflected power. And these grid lines are a calculation of the SWR based on the position of the 2 needles. So where they meet, that tells you what the calculation of SWR would be. It's just a graphical calculator. You can also use a directional watt meter. That's essentially what this is. There's a forward meter, there's a reflected meter. If you know those, you can actually plug those into the formula to calculate your SWR. Or if this is a cross needle, you can just look at the chart. Another test instrument that you can use to measure SWR of an antenna system is called an antenna analyzer. This is one of the most useful things I have. Okay, so what this is a very low power, very sensitive receiver that puts out a signal that does not have to be licensed because it's so low power, and it measures what the frequency is. It shows you what the frequency is, and it shows you what the resistance and the impedance of the antenna system is. And it allows you to alter the frequency even in areas where there is no ham band because the transmitter power is so low. So it allows you to get a really good representation of what's happening in your antenna. Okay, the major function of an antenna tuner is to match the antenna system impedance to the transceiver's output impedance. Again, how many ohms are most transceivers today?
50.
50 ohms. Okay. What is the primary purpose of a dummy load? And that's to perform adjustments of your transmitter while testing everything out without actually putting out a signal. And a dummy load looks kind of like, typically it's a big ass resistor, pardon my French, a really big resistor that generates a lot of heat. And it's inside a metal box, so it doesn't hurt you. And there's airflow to cool it off. And it is designed to basically take all of your transmitter power and turn it directly into heat. And in the process, it consists of a heat sink and a non-inductive resistor. Essentially, the reason that it's not inductive is because, as we saw, an inductor actually has impedance. So typically this is like a piece of ceramic, a very large piece of ceramic resistor. Okay.
Hey, Scott,
Yeah.
quick question. Where's the antenna analyzer located in the circuit then? Is it the same spot as the SWR?
It's not. It takes the place of your transmitter.
Oh, okay.
Yeah, it basically puts out a very small signal, like a milliwatt, and it's sensitive enough to see how much power is coming back and display it on the meters. Very useful device. Okay, modulation modes and bandwidth. Okay, so what is the most commonly used type of modulation on VHF and UHF voice? That would be FM, or frequency modulation. For VHF packet radio transmissions, also FM. FM again stands for frequency modulation. Amplitude modulation is another type of modulation. In order to modulate amplitude, here's the easiest way to demonstrate FM. So here's our frequency spectrum from 0 to infinity. And here's our center frequency, which we'll call FC. As we modulate, we basically have an amplitude that's fixed, and we take our signal and shift it back and forth depending on how you're speaking into the microphone. AM, we have our center frequency. We have our frequency going from 0 to infinity. We have a carrier, which is on the center frequency. And when we speak, we actually change the sidebands. And these basically, depending on what the frequency is of our voice and how loud we're talking, that generates these sidebands, which contains information. So this on FM, the frequency and how loud we talk changes how far this spreads out. On AM, it basically just does something similar, but notice it's not uniform at all. It's not a uniform power level. Because of that, when it gets received, FM is noise immune. Static does not affect FM. Lightning strikes do not affect FM. Things like that. AM is very much affected by noise. Okay, so now we can take this AM signal and we can do some neat tricks with it. We can actually take it and make the carrier disappear. It's just a waste of energy. We can also, on AM, say, okay, well, the upper and lower sidebands are just mirror images of each other. Well, there's no point in doing that because they have the same information. We're just wasting power. We can just do that with it. So now what we've done is we've started with AM and we eliminated this carrier and we eliminated one sideband, and all of a sudden our signal went from 6,000 hertz wide to only 3,000 hertz wide. And we've used up, we've saved a lot of our power. FM is typically 10 to 15,000 hertz wide. So you can see that AM and single sideband are actually considerably narrower than FM. They take up less room. If they take up less room, that means you can put more of them on a given band in the frequency you have. For weak signal work on VHF and UHF, we typically use sideband, upper sideband in particular.
So the single sideband is only derived from AM, not FM.
Correct.
Okay.
It's an amplitude modulated mode.
Okay.
Okay. A single sideband signal can be upper or lower sideband. More often than not, on 10 meters, VHF, 10 meter HF, VHF, and UHF, upper sideband is used just by convention. There's no compelling reason why to not use lower sideband, but most people don't. Advantage of SSB versus FM for voice transmissions is, again, that it's a much narrower bandwidth, 3,000 hertz versus, let's say, 15,000 hertz. If you're trying to use the same amount of power, you'll be able to stuff a lot more power per hertz into your USB signal, which means that your signal will go further. The approximate bandwidth of a single sideband signal is about 3 kilohertz, once again, versus for a VHF FM signal is between 10 and 15,000 hertz. We're also allowed to use television, good old NTSC analog television. Okay, so here's our FM, here's our SSB, and here's our AM signal, here's our TV signal. This is 6 million hertz wide, 6 megahertz wide. If we look at our frequency chart, you will see that in order to place a 6 megahertz signal on the band somewhere, the only place you can do this is 420 megahertz and up, because it takes up so much room. So fast scan TV takes up 6 megahertz. This is also known as NTSC television. This is not digital television, although some people have been experimenting with digital television on the ham bands as well. All right, so now we're going to look at CW, Morse code. Okay, so what did we say for a single sideband signal? It's about 3,000 hertz wide. Morse code is 150 hertz. So that means that you can put 20 of those in the space that you can put one of those. Remember that bandwidth spectrum is a resource. So the more things you put in it, the better off you are. So when using Morse code, we're on 43, by the way. What code is used when sending CW in the ham bands? That would be the international Morse code, not American Morse. American Morse code went out of style, I believe, around 1910. So international Morse code. And an electronic keyer is a device that assists in manual sending of Morse code. All right, and now we are on page 46. We're talking about digital. Okay, so computer to computer, a digital communications mode. And let me unshare this. Okay, so digital communications mode. So a digital communications mode is basically just ones and zeros. A system sending a stream of ones and zeros over the radio. Things that do that are packet radio. And I'll turn on this radio and see if I can pick up any packets. There's also IEEE 802.11, also known as Wi-Fi. There's also JT65, that's another digital mode. There's another one called FT8. There are literally dozens and dozens of digital modes. Here we go. I'll leave this on. We'll probably pick something up. You'll hear it when it comes on. That didn't take long. Everybody hear that annoying screech? Okay, that's known as packet. Packet radio is one of the first digital modes. It's called packet because data to be sent from station to station are separated into packets. Things that are part of packets. There's something called a checksum. Packet radio uses error detection and correction. In order to do that, what you need to do is essentially send more information so that you can verify that what was sent actually makes sense on the other end. You contain a header that tells another station where the information is going. That's called a header. And then there's something called automatic repeat requests, which basically says, I didn't get it, please resend it. So that's also known as ARQ. ARQ is, again, a digital scheme whereby which a receiving station picks up errors and sends a request to the originating station to say, please send it again, I didn't get it. So that's ARQ, or automatic repeat request. Okay, APRS. This is one of the newer things in ham radio. And I say newer, probably in the last 10 years. So APRS is a system called the Automated Packet Reporting System, and providing real-time tactical data communications in conjunction with a map. So that's known as APRS. And notice here what we have weather stations. Notice that we have some tracks. So one thing that's interesting about this is that it can also be used for weather balloons. It can also be used for high altitude, long distance balloons. Back in June, we put up a balloon that hovered at about 28,000 feet, and it sailed around Canada and the United States for 13 days, continually beaconing its information and allowing us to track it as it traveled. And then it got taken down in a thunderstorm.
Was that one that came right back around in 24 or 48 hours after?
It did.
Okay, I saw that.
Yeah. Yeah, it made a big loop up around British Columbia and then came back.
Came right back down to Corvallis or something.
Yeah, and then it made another loop up around Hudson Bay, came down over Michigan, and then made a beeline for Texas. No, it ended up over Georgia, and then turned west and ended up over Texas, and then hovered over East Texas for like 4 days, and then disappeared.
And it's just floating up there. There's no one guiding it.
Nope. And it's carrying a 12-gram transmitter that contains an APRS transmitter, 2 solar panels, and a controller, along with some basic weather information. So
Doesn't the
altimeter.
FAA have concerns about that?
Nope. You're allowed to have any payload up to, I think, 4 pounds. 4 pounds, I think, is the limit at which they worry about an airplane. You also can't have a tether that can cause any damage. So basically, if it hits an airplane, it gets destroyed. So
not a lot of airplanes at 90,000 feet. Though.
Well, no, this was only at 28,000.
Yeah.
But what's the physical size?
About
6 feet across
total. The balloon, it's a 3-foot balloon. The balloon is essentially nothing. The whole transmitter is probably a total of half of the size of my phone, including the solar panels.
You know, it's not coming back.
Yeah, it's not. Well, it could conceivably
I mean,
land.
it can, but I mean, you you have to put it up there with the thought that you
Yeah, you're not going to get it
again.
back. You're not going to get it back. But that's okay. I mean, it was up there for 13 days and it cost $120. And it was
And
extreme.
random people like me got enjoyment out of it.
That's right. So, okay, let's see. Which of the following is used to provide data to a transmitter sending APRS? And that would be a global positioning system receiver. So basically your GPS sends your information to your radio. Your radio then sends out packet. The interesting thing in this particular case was that our transmitter was transmitting 20 milliwatts. 20 milliwatts, and it was picked up 200 miles away because it was line of sight from 28,000 feet. Okay, PSK is phase shift keying. There is a mode called PSK 31, which is essentially a keyboard speed mode for digital communications. So basically you can type and it will translate it about as fast as most people can type. And it only takes 31 hertz of bandwidth on the band. Incredibly narrow bandwidth and fast enough that you can actually type to other people. DMR is digital mobile radio, whereas my voice signal takes up about 10 to 15 kilohertz. DMR is digital and it splits each little time. It splits the time into two so that two separate transmitters can operate on the same frequency at the same time, thereby doubling the amount of bandwidth, the number of people that can use the radio. So that would be known as time multiplexing two digital voice signals on a single repeater channel. A talk group, because it is a completely digital thing, you can put information on your transmitted signal. This is actually a DMR handheld that I have. And unlike the other one, you notice that when it comes up, let me turn this off. Notice that it's a really cool looking thing. The display is considerably nicer than this one. The reason that this one has to be so nice is because I have to be able to program it with all kinds of digital information so that I can connect to other talk groups in other places. So a talk group is a way for groups of users, and they can be anywhere that they can access the internet, to share a channel at different times without being heard by other users on the channel. How can you join a digital repeaters talk group? You program your radio with the group ID. WSJT is weak signal Joe Taylor. And if you think that all hams are boring, this is one reason that most hams are actually not boring. So if yeah, go ahead.
How isn't this dangerously close to encryption?
On which side?
On the talk group that's not public?
It's still public. You can still decode it. It's just the other group can't hear it. It splits the time in half.
The other group.
Yeah, I mean, basically there's two separate talk groups, but you can certainly listen. You just have to enter the other group.
So two groups.
Like anybody from anywhere can join a talk group.
Okay, but it's not like simplex, duplex.
No.
Communication or anything like that. No.
Okay, so notice this guy, K1JT. He invented something called the weak signal Joe Taylor mode, or WSJT suite, which is used for Earth, Moon, Earth. Yes, we do moon bounce. We bounce signals off the moon. A few years ago, some hams in Germany actually bounced a signal off of Venus and were able to pick it up. Weak signal propagation beacons, such as that map that we saw on the screen that uses the WSJT suite, and meteor scatter. Meteors make little trails across the sky as they streak across the sky. As they burn up, they ionize the air. You can bounce signals off of those. His software is able to send data fast enough and in short enough bursts that you can actually bounce a complete signal off of a meteor trail. FT8 is another one of the things that is used in the WSJT package. And And it is used for exactly what I showed you guys in making that map that showed all the different propagation modes all over the place. Okay, finally, I would like to point out this guy who did it. Well, you know, he's just Joe Taylor, right? He lives in, he's at Princeton University, no big deal. Here's actually who Joe Taylor is. So notice American astrophysicist, Nobel Prize laureate in physics. So anyway, ham radio is one of his favorite hobbies. And so one of his gifts to the ham radio world was inventing this transmitting protocol, digital protocol. Which of the following describes broadband hamnet, also referred to as a high-speed multimedia network? Very much like the thing that I was showing Pat before with Arden Mesh. That's hybridization of ham radio and commercial Wi-Fi gear using modified firmware, because all that commercial gear is already on the ham bands. So, all right, the next section is electrical safety. We're now on page 49. Electrical safety. This is one of the big reasons why it's important to to take a class. And I mean, a lot of these things are really common sense. Don't do this, don't do this. But some people still do it. Every year, there are ham radio operators who die by either falling off towers or getting electrocuted when their antenna falls or something really dumb like that. So this is largely common sense. Okay. What health hazard is presented by electrical current flowing through the body? Well, basically, if you get electrocuted, it can heat your tissue and cook you from the inside. It can disrupt the electrical function of cells. Can cause involuntary muscle contractions. I once received, when I was 10 years old, a 250 volt DC shock from the inside of a radio, which I was stupidly operating with the cover taken off. I reached in to touch something and I went, and my arm ended up in somewhere up here, and I had no idea how it got there. So don't kill yourself using high voltage. In the United States, the green wire is the equipment ground. Green is ground in the United States. If you happen to be in Europe, it's green and yellow stripe, but it's still green. So green is ground. A good way to guard against electrical shock, use 3-wire cords. Does anybody have a house that only has 2-wire plugs? Every so often we get one. Older houses typically don't have 3-wire plugs. So 3-wire cords everywhere you can for all AC equipment. Connect all AC powered station equipment to a common safety ground.
I did remove all the tube and knob wiring.
Okay.
When I moved in.
Yeah, it's kind of amazing that there's still houses out there with 2 wires. And finally, use a circuit protected by a ground fault interrupter. Okay, so what does a ground fault interrupter do again? It senses an imbalance between the line and the neutral, and if it sees a difference, it turns off the circuit, because the current that isn't coming back the right way is probably going through somebody. Installing fuses in an electrical circuit is a very good idea. The main purpose of a fuse is to interrupt power in case of overload. Why should you never put a bigger fuse in place? Well, the 5-amp fuse keeps blowing, but I made it go with a 20-amp fuse. And the reason you shouldn't do that is because you can set something on fire because of excessive current. If you build your own equipment, and you are allowed to build your own equipment, it's always a good idea to put a fuse or circuit breaker in series with the AC hot conductor, so that if something goes wrong, it will blow the fuse rather than fry your equipment or kill someone. What type of hazard can exist in a power supply when it's turned off and disconnected? Okay, I love this part. So when I was 9 years old, my dad brought me a capacitor from a power supply, a computer power supply, 500,000 microfarads at 5 volts. Anyone know how much capacitance that is? That's a big capacitor. The thing was the size of this coffee mug. And it was rated 5 volts and 500,000 microfarads. That can hold a lot of charge, not a lot of voltage, but a lot of charge. Well, so I charged it up with a 9-volt battery and thought to myself, well, that was fun. It didn't do anything. I guess I'd better discharge it. So I took, in these terminals, I took one screwdriver here and one screwdriver here and went like this. At which point there was a huge flash between the two screwdrivers. And when I looked, each of the screwdrivers, they were not welded together, but it was clear that they had melted, that the metal had actually melted at the point where the screwdrivers touched and they arced. At 5 volts, there was enough current available to almost do arc welding. So that is the reason why you should not stick your hand into a power supply, because the capacitors might still be charged up, even if it hasn't been used in years. Capacitors can hold a lot of charge for a long time. Let's see, hazards of a 12-volt storage battery. A 12-volt battery. Okay, 12-volt batteries. What do they contain? All of them.
Acid.
Sulfuric acid. That's right. Now that can be in a gelled form. It can be in an absorbed glass mat form, but they all have sulfuric acid. So it's lead and sulfuric acid. And if you have a battery that is overcharged or discharged too much, you can actually cause it to generate hydrogen gas. And when you get hydrogen gas forming in there, the battery itself can go boom. If the battery explodes from inside, what you end up with is a shower of sulfuric acid. So then you have an explosion and sulfuric acid flying everywhere. Not a good thing. What can happen if a lead acid storage battery is charged or discharged too fast? It could it could overheat, give off flammable gas, or explode, none of which is a good thing. All right, page 51, antenna and tower safety. When putting up an antenna tower, look for and stay clear of any overhead electrical lines. Again, this seems obvious, but it is not. People every year get killed by this. The minimum safe distance from a power line when installing an antenna is 10 feet, so that if any part of the antenna falls, it's at least 10 feet away from an energized power line. Why should you avoid attaching an antenna to a utility pole? Well, first of all, you don't own it, right? Secondly, that actually typically has a high voltage on it if it's a utility pole. Does anybody know what voltages run in their neighborhood? Anybody?
1,000 volts?
Is it 408 or something?
Oh, it is not. If you're in a typical neighborhood, it's either 7,200 or 12,400 volts. That is enough to give you a really bad day. So, and the reason that that happens is because due to conservation of energy, if you jack up the voltage a lot, you don't have to deliver a lot of current. And by Ohm's law, if you don't have to deliver a lot of current, you don't lose a lot of power in the power lines. So in my neighborhood, it's 12,400 volts.
We had a power line go down at work during a snowstorm a couple of years ago, and it burned 2 holes in the concrete.
Yeah.
Where it came down and shorted.
Yep, 12,000 volts is enough to do that. Absolutely. And that's why they say, stay away from the power lines, stay away from the power poles if you can. Okay. Let's see. Let's see what can happen if a person accidentally touches an antenna while transmitting. Just like I got on my hand when I was the ground side of my antenna, you can receive an RF burn. RF burns really hurt. They sort of like make a little hole in your skin. They really hurt. When should members of a tower work team wear a hard hat and safety glasses? Basically, if there's anybody doing work on the tower, that means that somebody's probably going to drop something. And even something as small as a screw or a bolt or a nut can really hurt if it hits you in the head. So safety glasses, and a hard hat. What's a good precaution to observe before climbing an antenna tower? It used to be put on a safety belt. Now they actually recommend using a fall arrestor and safety glasses. A fall arrestor and climbing harness is something that is incredibly helpful. Basically, it's a full body harness. It goes around your legs, it goes around your arms, your shoulders, and it has a kind of like a bungee cord, so that if you do slip off, it doesn't just snag you super hard. It's kind of like as a springy thing that will basically keep you from accelerating and then suddenly stopping really hard. Under what circumstances is it safe to climb a tower without somebody around to help you? Pat, you have a tower. You're the only one here with a tower.
Yeah, it's not upright yet, but it's never safe.
Never safe.
Climb a
That's right.
tower without people around spotting.
But I only have, but I've only got a couple things to do up there.
Doesn't matter.
Doesn't matter, because every so often, once in a while, a tower will fall over. Once in a while, somebody will get stung by a bee. So once in a while, somebody will have a heart attack on a tower. And if you're up there by yourself, you are stuck up there. So nobody will be there to help you. Important safety rule to remember when using a crank up tower. You have a tilt over. A crank up is something that's basically telescoping. If you're going to be working on a telescoping tower, it is not designed to hold your weight when fully extended. So bring it down or put in locking devices to make sure it doesn't retract with you on it. What is the purpose of using a turnbuckle and a safety wire, Pat?
Turnbuckle?
A safety wire to be put through your turnbuckle on your guy ropes or guy lines.
So you don't unscrew it and have it fall over?
That's right. Because what can happen is not that you'd unscrew it, but if you're out in the wind, it vibrates and a turnbuckle will start to unscrew itself over time. So basically, if you put a safety wire through the turnbuckle so it doesn't get to the point where it can unscrew itself.
I gotta remember that.
Yeah. Let's see, a gin pole. What is the purpose of a gin pole? A gin pole, Pat, do you have a gin pole, or I've probably access to one, right?
I don't have a gin pole. I'm thinking you're meaning almost like the army mast.
Yeah, essentially a gin pole is it's essentially a crane section that goes up above the top of your tower that allows you to pull down on your rope so that your antenna comes up to you without having to physically lift it up by pulling up. It makes it a lot easier to get it into place, and then you can tie it off. So that's a gin pole. It's used for lifting heavy things to the top of a tower. Grounding is very important. Which of the following establishes grounding requirements? That would be local electrical code. Follow your codes. Grounding method for a tower: separate 8-foot ground rod for each tower leg bonded to the tower and to each other. When installing grounding conductors for lightning protection, don't bend your cables. Don't bend your grounding ropes, wires. Lightning likes to go around curves. It doesn't like angles. It will jump instead of following it. When installing ground wires on a tower, ensure that connections are short and direct, and again, no sharp angles. All external ground rods or earth connections must be bonded together with heavy wire or a conductive strap. Lightning can also come down through your feed line because your antenna is live. What you do is you use something called a lightning arrestor, which is essentially in between the center conductor and the outside of your coax. What it is a very high voltage tolerant gas that if the voltage gets above a certain point that you would normally experience, it will ionize the gas and conduct the energy from the center conductor to the outside. And then you take all of those and you ground them together and run those to the ground. And hopefully what happens is that your lightning does not come down through your cable into your station and blow up all your equipment. Now, What's an even better thing to do in addition to doing that? If you know
Disconnecting your radio,
if you know there's a thunderstorm coming, disconnect your radio.
all antennas.
Yep, everything.
Spark gap.
Spark, yeah, exactly. Okay, so when I was, we were doing field day when I was in Maryland one year. We're on 53, by the way. When I was in Maryland, we were doing field day. There was a thunderstorm coming. We knew it. We were inside a tent. We disconnected the radios from all the feed lines, and we were listening and heard zap, 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 zap. That zap, zap, zap was static electricity building up on the antenna and arcing between the center conductor of the cable and the shield. And that's, you know, a half an inch. That's, you know, at least 5,000 volts.
Jeez.
It's better to have that jump the gap there than be connected to your radio and blow it up. All right, here we go. RF hazards and radiation exposure. VHF and UHF. Does everyone remember what the frequency limits for VHF are in megahertz?
30 to 300,
30 to 300. And UHF?
300 to
wait.
3000,
Right. Okay, and HF?
3 to 30.
Excellent. Okay. So radiation, radio signals by and large are non-ionizing. That means they don't have enough energy to cause any genetic damage. They can heat things, obviously. A microwave oven does work, but they won't get into, they don't have enough energy to basically knock DNA apart. Whereas X-rays do, ultraviolet can, gamma rays definitely do. The maximum power level that an amateur station can use at VHF before doing an RF exposure would be 50 watts PEP at the antenna. So PEP is peak envelope power, which is essentially the most power that you will see.
So does that mean that hard radiation, ionizing radiation is also an electromagnetic field propagation?
Which one?
Any of them. I mean,
well, I mean, if you say like, you know, a beta particle, that's an electron. So that's no. I mean, if we're talking nuclear radiation, but if we're talking gamma rays, yeah. Gamma rays are electromagnetic. Yeah, hard X-rays, hard UV, you know, short wavelength UV, they're all ionizing. Which is why gamma radiation will, you know, rip your body apart. So okay, here we go. Let's see, how do you perform an RF exposure evaluation? The easiest way, okay, you can do calculation based on computer modeling if you really want to. You can use field strength. You can walk around with a field strength meter and test it. You can also do this, hint link RF evaluation. Here we go. And I'm going to share this because this is incredibly useful. Here, see this little calculator, little web-based application. This is like the best thing that's out there because you can say, what's my average power at the antenna? We'll say 50 watts. Antenna gain in dBi compared to dBd. That's dB with respect to an isotropic radiator, which is an imaginary, completely omnidirectional radiator, which does not exist in nature. So we'll say that it's a dipole, so 2.2, because it tells us to do that. We're 5 meters away, and we're on 28 megahertz, and go. So with those parameters, okay, we just did it. Here's my estimated power density in milliwatts per square centimeter. Here are my legal limits for a controlled environment, which means that I have a fence around it, or an uncontrolled environment, which means that somebody can just walk past it without knowing what's going on. So incredibly useful little thing to have. And just, you know, as far as safety goes, it's very, very good to have out there. It's awesome that somebody actually took the time to create it. And I just put the link out there. Duty cycle. What is duty cycle? Duty cycle is the percentage of time that something is transmitting. 50% duty cycle would be half on, half off. Duty cycle is used for time averaging of signals. So if we're on for 3 minutes and off for 3 minutes, we can actually use twice as much average power during that time, twice as much peak power during the time because we're only on for 50% of the time. It's used to used to measure the average exposure of people to radiation. Why do exposure limits vary with frequency? And that's because our bodies are a certain size and dimension, and we're actually resonant at certain frequencies more so than at other frequencies. And the peak occurs at 50 megahertz. So for that particular reason, our exposure limits are lowest at 50 megahertz, which is in which band, everyone?
HF.
Nope.
30 to 300.
No, well, it's actually VHF.
Yeah, VH.
But it's in the 6 meter band. So the 6 meter band is our lowest exposure limit. What factors affect RF exposure of people near an amateur station? Frequency and power level of the field, distance from the antenna to a person, and radiation pattern of the antenna. So here's a question.
So that's
yeah, go ahead.
That's that 50 megahertz is the frequency that humans are most least affected by.
No, most affected.
Most affected by.
Yeah.
So that gives. Why would that give you the
lowest possible, the lowest
allowable?
Yeah.
Okay. Most allowable.
So can everybody see this out here?
Mhm.
So notice 6 meters. This is actually really significant. So 6 meters covers again 50 to 54. And this is just something that you'll get used to seeing. It's also good to have this chart posted on your wall because it tells you a lot. Okay. Let's see, what should you do if your RF exposure evaluation shows that people are being exposed to excessive RF? So what I'm going to do is come up to here and we're going to say, okay, average power at the antenna is going to be 0.5 watt. But I'm transmitting with 32 decibels of gain, which is like a small microwave dish. And I'm, let's say in meters, I'm 2 meters away from it at 2400 megahertz, gigahertz, 2400 megahertz. Well, guess what? I'm transmitting with a 0.5 watt. This is a Wi-Fi router. This is a Ubiquiti Wi-Fi router with a 32 dB gain dish antenna. Well, guess what? If I'm the only one there, it's barely safe, but still legal. But if there are other people walking by that can get close to it, it is not safe. Even with only 0.5 watt. Doesn't it seem like 0.5 watt would be pretty safe?
Yeah.
Except it's a 0.5 watt, but I've got 30 decibels of gain, which basically is multiplied by a factor of 1,000. So that 0.5 watt turns into effectively 500 watts in that one direction. And that's why we have to take this class, to be able to understand things like that happen. Okay, so what should you do if you're in excess of FCC supplied limits? You can move your antennas. You can also lower your power or transmit less, or transmit when there's not going to be anybody nearby. All right, and when do you perform an RF safety exposure? The answer is whenever you change anything. Unless it's like, okay, I replaced a 100 watt transmitter with another 100 watt transmitter, I'd say that that's fine. But let's say I replace a 10 watt transmitter with a 100 watt transmitter. It's probably a good idea to go through it again. All right, that's all I got for today. Tomorrow is station practices, setup, all the rules and regulations and mobile operation and stuff like that. Does anybody?
Question?
Yes,
I got a question.
I was just going to say, does anybody have any questions? So
I
yes,
do.
please.
So RF, an evaluation for RF. Should you do one when you first set up your first station?
Yes, absolutely.
Okay. Should you have experienced hams along with you?
If you want to go through, if you want to verify it, I mean, but here, I mean, it's the most basic thing is, you know, we're going to just assume absolute worst case. So like, this is one that I did for our museum station. Average power at the antenna could run 100 watts, right? Average gain for the antenna, it's a dipole, we'll say 2.2. distance to the, okay, so that's from 10 feet above the roof down to head level. So we'll say 6 meters. And we're at 28 megahertz. So there you go. So this is our worst case. I basically assumed absolute worst case. So this is the estimated density based on all those parameters. And I even included, yes, include the effects of ground reflections, which actually raise those levels even more, essentially being over a perfect ground, which basically says that anything that's directed down comes back up and affects other people as well. So basically that showed, yeah, okay, it's safe. And I actually did this, and I tried it at different frequencies. I went up to 50 megahertz. And notice the uncontrolled environment level came down a little bit, still safe. I went down to 14 megahertz, which is the 20 meter band, and we're way below 21. So basically all the bands that we would typically operate on.
Right.
So we basically just redid it. And to be honest, we never run 100 watts ever. And it's going to be very rare. I'll even reduce this down to 4 meters, which is, 12 feet. And I don't remember if I ever found anything that was, okay, this one was close. That was close at 28 megahertz. And that was, but basically this is, notice it says average power, right? That means we're transmitting 100% of the time at 100 watts, which we don't do. And that's if somebody's basically standing on a ladder inside the building.
Now, I got another question.
Yeah.
If you add an amplifier to your system, will that change your RF exposure?
Oh yeah. Because
And how do you calculate that?
well, you just punch in a different RF. I mean, it's 500
okay.
watts.
Right.
And then
Okay.
everything else is the same. So now let's go back to 6 and calculate. And now we're not safe anymore because the power density went up by a factor of 5.
Okay.
Because we went from 100 watts to 500 watts. But yeah, being able to having something like this is incredibly helpful.
These are really good things to know. I didn't do an RF exposure evaluation when I set up my station, and yeah, that's going to happen.
Well, where do you have any? Do you have a significant property or anything?
No, not really. We got like a 1 acre piece of property.
But city lot or?
No, actually, we're out in the middle of the farm fields, just like the
Oh.
background picture. It is like we have no neighbors, half mile away.
Oh, you'll be fine. I mean, the only ones you have to worry about are you at that point. So,
Well,
and yeah, but I mean, let me where we can do a quickie exposure evaluation. I mean, whoops, wrong thing. Where'd it go? Where'd it go? There we go. So, I mean, let's say your antenna, let's say you're running a kilowatt.
We're done for the day though, right?
We are done. Yeah.
Bye.
All right.
sorry,
Thanks.
bye.
Just if anybody has any questions, that's all. All right. So let's say you've got a Yagi. Let's say you managed to put up a 10 dB gain over isotropic. And let's say your distance, let's say it's 8 meters to it. Like you're directly under it, and you want to see what it's like on 28 megahertz. Okay, but see that says that you're 8 meters to it, and it's pointing directly at you. So it's kind of a kind of a that's why it's important in some cases to say, okay, well, this is not a worst case, because if you were to look at it, your signal is basically in a beam like this, but you're down here. And that's when it helps to be able to figure out what the front to back ratio is and what the actual power up and down happen to be.
Okay.
So Yeah, I mean, that's one of the things that, you know, let's say you drop, and that's also a kilowatt average. Let's say that you average, you know, 250 watts. Well, then for you, it's still fine. I mean, you could actually be there, and because it's not an uncontrolled environment, it's controlled, you're still fine.
Yeah.
And that's if you transmit a kilowatt 25% of the time, which you're still not going to do. So
No, no. This is good. I appreciate it.
I got a quick question that's kind of unrelated to most everything we've talked about.
Okay.
But why is there a fee for a GMRS license and not for a ham radio license?
That's a good question. It has always been that way.
Huh. And GMRS is just for pretty local communication, right?
No, you can put up a GMRS repeater.
Yeah.
You
Why
have
would
a-
somebody want to get a ham versus just do a GMRS? Just because of the multitude of opportunities through ham?
Yeah, but yeah, I mean, basically, you're not an appliance operator. A GMRS user is an appliance operator,
Uh-huh. Okay.
and we are not. We have, you know, I mean, they can't just like spin the knob
Uh-huh.
and do whatever, wherever,
Right.
based on, you know, based on the license that they've earned.
Mhm.
So, and they also are not, you know, they're the part of their deal is, you know, that it can be used for business band, it can be used for things like that. It's, they can also make money using, and that's part of the reason why they have to pay for their licenses, because you can use it to make money.
Oh,
So,
okay.
so. Any other questions? Hi, Nate. You're late.
I thought the meeting was at 4. I saw it started at 4.
Yeah, no, it's definitely over at 4. But I did actually record it. So
Can you send me that?
yeah, I can say it's going to be huge, but I can try.
If you could send me that as well, I'd like to go back and review a few things.
Okay.
So would it be sent or are you going to post it like on a YouTube thing?
I haven't figured that out yet. It might be
Okay.
it might be like a Google share, doc share.
Okay. All right, great.
Google share, that would be great. I'd like a copy of it also.
Yeah. Okay. Any other questions?
Nope.
Hey, Pat, you know what'd be really hilarious?
What's that?
You finish your if you applied for the Anchorage Club.
I did.
Oh, but did you already fill it out? Do you already take the test?
I got to take the test. I was focused on you
Oh, okay.
and what you're teaching. So
That'd be hilarious if you could actually give the test tomorrow.
well, I've never given one remotely, so this is kind of a new experience.
Everybody would walk you through it. We use Discord server for chat, and Zoom for communications back and forth and between the examiners, and let's see what else. Oh, exam tools, which is basically the secure version of hamstudy.org.
Well, I'm kind of set up with like 3 screens, and
Yeah.
so I've been looking things up as you've been talking. So if I can get it done and Kent can take a look at it, that would be great. But
See, I've got my
I gotta see.
See, I've got my iPad and my
Yep.
computer and additional laptop. So
Yeah, I mean, everybody's got a setup, right?
yeah.
So
Well, and again, this is my wife's craft room, so this is not permanent. This is my teaching suite.
I'm in an unrenovated room. That's why I have a background on there. So.
Yeah. All right. Cool. Well,
Okay.
I hope this has been useful for everybody. I really do.
It has.
All right. And see you all again
right.
in the morning.
Thank you.
All right.
Thank you.
Good night.
Good night.